글로벌 인공지능 포럼에 함께 해주신 현장 참가자
Thank you for joining us at the Global AI Forum, both online and offline. It is my great pleasure to meet you. My name is Kim Kyung-mi. I'm the announcer who is going to be the MC for this event.
So today's event is hosted by the Ministry of Science and ICT and co-organized by IITP, ETRI, KETI, KAIST, and SNU. And we are discussing various themes under the title of AI of a New Era. We'll be talking about the future direction of AI technology, research directions, and how they can be applied in different parts of the society and industries. So we'll be talking about various strategies, and it'll also be a venue for global networking and cooperation. So I would like to thank everyone for being here at this very meaningful event. So unfortunately, as you know, because of the COVID-19 pandemic, many of the speakers and the organizers are here with us, but nonetheless, majority will be joining through the video conferencing platforms and through YouTube. And those of you who are here in person are complying strictly to disease prevention rules. So before we actually start the forum, I would like to now introduce some of the distinguished guests who are here for the Global AI Forum. So when I call out your names, please give them a round of applause. From IITP, we have the project manager, Hyun-Yu Lee. Thank you very much for being here. Yes, would you like to just stand up? Let's give him a big round of applause. We also have from ETRI, the principal researcher, Dr. Jin Ho Lim. Thank you for being here with us. Welcome. And from KAIST, we have Professor Jin Ho Choi. Thank you. He's going to be playing different roles today. And from the Technical University of Berlin, we have Professor Klaus Mueller. Thank you for being here. Let's give him a big round of applause. So that was a brief introduction. So please, we look forward to your continued attention to the Global AI Forum. Thank you for being here, and I look forward to your understanding that we are not able to introduce everyone due to time constraints. And then there are many people participating remotely online in the Global AI Forum. So let's say hello to one another. So those of you who are online, please turn on your cameras. Do you all hear me? Can you all wave your hand? Hello, everyone. Yes, I think everyone's there. Yes, I'm sure that we will have very good presentations, and we look forward to your continued participation until the end and your active participation in the discussions and question and answer session. Thank you very much for taking time out of your busy schedules. Without further ado, we're going to start the Global AI Forum. So first of all, I'd like to ask the Vice Minister of MSIT, who actually sent us a pre-recorded video of his congratulatory speech. Let's watch his video.
안녕하십니까. 과학기술정보통신부 I am the second Vice Minister of Science and ICT, Cho Kyung-sik. Welcome to all the participants of the Global AI Forum. I also thank today's organizer, President Chun Sung-bae of IITP, and the keynote speaker, Professor Yoshua Bengio of University of Montreal, and all the distinguished speakers and panelists from home and abroad. The entire world is in the midst of a massive digital transformation across the society and economy, triggered by the COVID-19 pandemic. Not only in ICT, but also in manufacturing, medicine, financial services, education, and all areas of society and industry are seeing accelerated digital innovation, at the heart of which is artificial intelligence, or AI. Despite the challenges of the COVID-19 pandemic, the Republic of Korea is pursuing large projects and increasing investment to step up AI technology and focuses all its energies on sowing the seeds of innovation to lead the digital economy in the post-COVID era. The Digital Dam or Data Dam project, part of the Digital New Deal, collects, processes, and utilizes data for an even smarter AI. The Data Dam will provide the foundation for innovating AI-based industries and new innovative service development. Also, there is a massive AI research and development project underway to attain next-generation AI tech to overcome the limitations of existing AI technology. Thanks to these efforts, Korea was ranked 7th in Oxford Insight's Government AI Readiness Index and 5th in both Global AI Index from the UK's Tortoise and rankings from Stanford. So we are quickly becoming one of the leading powers in AI technology. The topic of the Global AI Forum today, language intelligence, explainable AI, and brain-inspired AI, are the outcomes of the Innovation Growth Engine Project's AI core source technology research efforts that began in 2017 and is serving as a foundation for Korea to quickly overcome technology gaps and lead the global trends in AI. Today's forum, based on the research achievements, will provide outlooks on the future direction for AI research. Our online participants will hopefully envision through today's forum the next generation AI-based innovations. And I hope this will serve as a very good opportunity for that envisionment. Lastly, I thank all the organizers, speakers, and panelists who have made this forum possible and wish all the participants all the best of luck and success. Thank you.
Thank you very much, Vice Minister, for your warm congratulatory words. He has been talking about the direction of AI and how innovation can take place. So I think he has started off the Global AI Forum quite well. So thank you very much, Vice Minister Cho, once again for sending us your video despite your busy schedule. Now we will have the opening speech from the IITP. We would like to invite the president, Mr. Sang-bae-jeon. Let's hear his pre-recorded video. Good morning. I am Sang-bae-jeon, president of IITP. I'd like to express the deepest gratitude to everyone participating online despite the difficulties posed by COVID-19. And my special thanks go to the international speakers who have traveled afar. So we have Professor Yoshua Benjo of Montreal University, Professor Jin Ho Choi from Emory University, Professor Leslie Kelbling from MIT, and Professor Klaus Mueller from the Technical University of Berlin, who has actually come to Korea. AI technology now goes beyond merely the ability to differentiate cats and dogs, to understanding and inferring complex situations and operate more similarly to humans. Korea started R&D into artificial intelligence in earnest with the launch of the Innovation Growth Engine project in 2017. And from 2019, it started research in brain-inspired AI, inspired by the developmental process of the human brain. And there is also an ongoing research into AI technology that is able to explain the process of decision-making. In other words, explain why it came up with a particular answer just as humans can. For AI to be applied more broadly in real life, it has to become more sophisticated and reliable. And against this backdrop, today's Global AI Forum is being held under the title of AI of a New Era, with 3 subtopics that are garnering attention globally. So today we'll be sharing research results among scientists from home and abroad in 3 different areas: language intelligence, brain-inspired AI, and explainable AI. And so I think today's forum will be a valuable occasion to discuss ways forward for AI. I hope that the Global AI Forum will serve as an opportunity for us to exchange information and thoughts on the future of AI technology. And last but not least, I would like to thank the organizers, and I wish health and success for everyone who are participating. Thank you.
Thank you very much, President Chang Song-bae. So that was the opening remarks for this forum. And artificial intelligence has become a firmly established part of our lives. Today, in this informatization age, I hope that this global AI forum will provide much information and insights on how we are going to develop the AI era. Now we would like to begin the keynote lecture, the keynote speech. So many people are looking forward to this speech. From Montreal University, we have the keynote speaker, Professor Yoshua Bengio, who is the godfather of deep learning. We regret that we are not able to host him here because of the COVID-19 pandemic. However, Professor Yoshua Bengio is with us online, live, despite the time difference. We would like to connect to Professor Yoshua Bengio right away. Please give him a big hand.
Professor Bengio.
Hello.
Hello.
안녕하십니까?
Hi, everyone.
Yes. Please begin your presentation. We can hear you well. Thank you.
Excellent. So today I want to talk about the research direction that my group and collaborators have undertaken towards a next stage in AI research beyond the work in deep learning we've done in the last couple of decades, trying to get closer to human-level AI. So let me start with how we got into this area, how I got excited about neural nets when I was a grad student. It was a time when I was looking for a research topic, and I read by chance some of the early papers on neural networks, and I thought that this might be really amazing if there could be something like the laws of physics, but that would explain intelligence. So that means intelligence would be explained by a few simple principles rather than a huge bag of tricks, which was the general approach in those days in the 1980s. And so if you really want to explain intelligence with a few simple principles, then you need learning, because learning allows to go from simple principle of how the machine or how the brain learns, which might be like a few equations, and acquire the knowledge that may explain our intelligence. So in those days, the dominant approach to AI was based on logic and symbols and rule-based computation, where knowledge about the world was provided to machines by humans. The problem with this, I mean, there are several problems, but one problem that is tricky is that humans themselves have a lot of knowledge, intuitive knowledge, that they don't know how to communicate because, well, we don't have access to what is going on in our brain in the details that explains our thoughts, our common sense, how we solve problems, beyond the surface of language. There's a lot that is happening that we don't understand. And so machine learning, already starting in the 80s, started before, but really had a first important progress there because of new algorithms for training systems that were inspired by the brain. And that's the neural networks. So they obtain the result of computation from the combination of the computations from a large number of simple adaptive computational units like the neurons in the brain. And instead of representing information with symbols, for example, a cat is a complex thing, but we can just represent it by the symbol cat. And a dog is a complex entity, but we can represent it by the symbol dog. Well, instead of representing information with symbols, with neural nets, one of the big important discoveries in the 80s was the idea that we can represent information with a pattern of activations, with what is called distributed representations. And a little bit later in the 90s, I worked on this for being able to represent complicated probability distributions and information about language, which is symbolic. But if you think about cat and dog, even though they're two different symbols, they have a lot of things in common. So you'd like to represent that commonality through a representation. And since we don't know what is the right set of features, you'd like to learn those features. So that's basically what neural nets do, at least the early neural nets. And one important aspect of this that came with backpropagation, the method that we started using in the mid-80s, is that we can train a complex system with many pieces all together so that they optimize with respect to a single objective, like minimizing the errors that the system make. Now, in the 2000s, we realized that you could do even better than that by thinking about abstraction. So abstraction, of course, is an important concept in classical AI, but what's the relationship of abstraction with neural nets? Well, if you imagine a neural network with multiple levels, you'd like the higher levels of representation to capture abstract concepts. So the low levels might correspond to images, sounds, any sensory signal. But in order to really understand the world, in order to manipulate information in a way that's similar to humans, in order to separate what may look very complicated at the low level of pixels into things like words, we need complicated transformation that separates all this mess that we have in the sensory data into high-level factors of variation, like the causes of what we're seeing. And if we can do that, we can get AI systems that work a lot better, that generalize better to new cases, just like humans are able to do. So why would we have these multiple levels of representation? Well, if you look at how humans understand the world, if you look at how engineers build up solutions to problems, it's very often compositional through a hierarchy of representations and the composition of computations. So if you think about images, you have very low-level things like pixels, and then on top of pixels, you have more complicated entities like edges, and then on top of edges, you have motifs and parts, and these parts can be combined to form objects. And similarly, there are different levels of abstraction almost everywhere we look. If you try to see how humans understand things. So for example, in text, you have characters on top of which you have words, clauses, sentences, stories, and so on. And we found that we were able to train neural nets with multiple levels of representation, where indeed the low levels capture low-level characteristics like these edges. And as you go higher up, you get more abstract features that are being learned. And we didn't have to program these by hand like it used to be necessary in earlier years of pattern recognition. So what it meant is that instead of relying on trial and error and engineers trying different visual features, we found that if we let the machine discover these multiple levels of representations, these hierarchy of features, it could lead to much better systems. And in fact, we even have mathematical theory that helps us understand that a deeper system can represent very complex functions much more efficiently than more shallow neural nets or more shallow computations. Now, let me connect this with a basic challenge of machine learning, or statistics. If you are trying to capture the relationships between variables or how to represent a function of interest in a low-dimensional space, for example, you only have one variable, you can break up that variable into intervals, and you can collect data for each bin, for each interval, and just by counting and averaging in each of those bins, if you have enough data to cover all the intervals, you can do a good job of characterizing the function of interest. But now what happens if you have two variables? Now you have all the configurations of all the values of each variable. So let's say you had 10 values for each variable instead of 10 regions that you need to characterize. Now you got 10 times 10. And maybe you're not going to have data that fills all the configurations. And if you have 3 variables, well, that's 10 times 10 times 10. So it's 1,000 regions in the space of these variables. And that's just 3 dimensions. A picture might have 1,000,000 dimensions. So the problem in high dimensions is that there's never going to be enough data to cover all the possible cases, all the possible configurations of the different variables. And if you think about it like this, you might say it's hopeless, like machine learning cannot work. But humans manage to do something that works pretty well. So what's our trick? Well, we use something that computer scientists call compositionality. Compositionality is something actually you're familiar with in language. If I say how you structure a sentence, like subject, verb, object, you can see that you can just change the subject, like I buy milk can be replaced by he buys milk, right? So you can change the verb. You could say I drink milk. So there are many ways to combine the verbs, the subjects, the objects, and this gives rise to a very rich potential to express the things that could happen in the world. So we do that all the time with language. In machine learning, well, it's only recently, in the last couple of decades, that really we've understood the importance of that compositionality, and that we could design machine learning systems that would more naturally generalize to new combinations of things. Now, this compositionality idea, of course, has been present in computer science since the beginning, like in the 40s and 50s. That's how we design programs. The problem is how to learn a function that is itself the result of a composition, and that's going to have that kind of flexibility. And that's something that we are still figuring out, as I'll explain. Now, the kinds of structure I talked about with compositionality, they're corresponding to assumptions we're making about the world. This is what machine learning people call inductive biases. In other words, instead of allowing the learning system to discover any possible function in the space of functions, which is huge, we're saying we're going to restrict ourselves to some set of function that has particular properties. And there's even theorems that tell us that there is no completely general learning system. There is no completely general AI system, in fact. You need some assumptions, some inductive biases in order to be able to get generalization. So what is generalization? Generalization is, if I can go back, yes, the ability to say something about one of the regions you've never seen any data for. Right? So it's something new. And humans are really good at that. Every moment of our life, we see something new. Every image that we see is different from anyone we've seen before in our life. Sometimes the novelty is greater and it's not obvious what to do. And one thing we are seeing with machine learning is generalization is not easy. And what we're striving to do is to help our machines exploit more appropriate assumptions, more appropriate inductive biases, potentially by getting inspiration from humans. I mean, human intelligence seems to be exploiting some of these inductive biases. And if we understand those biases, we will understand better human intelligence, and we will be able to deal with higher dimensionality, to provide systems that are more robust and generalized better. So that was the 2000s. In the 2010s, really a revolution happened where our work on deep learning suddenly became more than better results in papers, in scientific papers and scientific conferences, but actually something that attracted attention from industry. And it started with speech recognition. And I actually worked on speech recognition during my PhD in the late 80s, early 90s. And the performance of speech recognition system, which we see in the figure, this is the error rate, had become kind of flat in the 2000s. In other words, we had made progress mostly because of larger data sets, but the technique had not changed for almost 20 years. And suddenly around 2010, people in industrial labs started doing experiments with deep learning and found that it worked a lot better than the previous systems. And every year they improved their systems. And in the matter of 2 years, these systems were converted from a paper prototype to code running in Android for speech recognition in the Android operating system. So that was a very fast transfer, and it created a lot of excitement in industry. And in fact, very quickly, the interest expanded to not just speech, but also images. And there was a big challenge called the ImageNet challenge of object recognition with 1,000 categories. And computer vision researchers basically told us, the deep learning researchers, if you want to convince us, show us that you can really improve on a big, difficult data set like ImageNet. And Jeff Hinton's students actually did that and were extremely successful in the 2012 competition, which was the first time they actually tried it. And there was a big reduction in the error rate thanks to their deep learning system. And thereafter, it was only deep learning systems that won the competition. In fact, by 2014, there was basically only deep learning systems that came into the competition because everybody knew that was the only way to get good results. And very quickly, the performance even got better than human error rates. So that was 2012 and 2014, another kind of big revolution. We started seeing success at a completely different kind of task, that is what we call deep generative models, where in the case of images, the neural net is not trying to classify the content of the image, is trying to imagine new images that it has never seen, but somehow look reasonable in the sense that it could have come from the data that it was trained on. So for example, on the top and the bottom left, these systems were trained on images of faces. And all of those faces are completely synthetic. These people don't exist. So they were completely invented by the computer, and they don't look like anybody in the database. And then 2 years later, another breakthrough, this time combining deep learning with reinforcement learning. That's called deep reinforcement learning. And reinforcement learning allows to handle decision making, and in particular when you don't know what a right answer is at each step, but at the end of a sequence or in the middle, you may have some feedback, some reward, like playing the game of Go. At the end of the game, well, you know if you won or lost, and that signal can be used to train the system to play better. And of course, in South Korea, this has been a big hit, and got a lot of people interested in deep learning. And so this is the beginning of yet another phase of application of deep learning in decision systems. More recently, the last breakthrough that I want to mention is the work on converting the description of a protein as a sequence of amino acids into their 3D structure, something that researchers have been trying to do for several decades, since the at least early 90s. And this was considered very, very difficult and had kind of stagnated for many years, decades, as you can see in the graph on the right. This is the accuracy of the systems that were the best in the yearly competition called CASP. And then deep learning systems, which took some time to develop, came and really completely changed the game. And now the code for this is public, and people are starting to use this for important applications in biology and drug discovery and things like this. So now let's look forward. All right, so the progress has been quite amazing, but what are we missing to reach human level intelligence? Well, first of all, there's a theoretical problem. The theory we have for machine learning assumes that the test data will come from the same distribution as the training data, but that's not realistic. Like when you build an AI system today, you train it on some data, but then you deploy the system in a different setting, not exactly the same, not exactly the same population, maybe it's later in time and so on, and then the performance is not as good. So what's going on? We're still trying to understand, but we understand that we have to think that our hypothesis that the test data, the field scenario is the same as the training data distribution, that's not correct. It's not realistic. So we need to first analyze this and monitor it. And when we train systems in industry, for example, we need to think about this. We need to evaluate how our system would generalize out of distribution, meaning in settings different from the settings used for training. For example, if you have, say, data from multiple countries, maybe you train with data from some countries and you test on data from other countries. Or you train on data from the past and then you see how it works later on future data. By opposition to the classical approach, which was to mix all the data, and you don't see that you might be losing when the distribution changes. So it's very important first to monitor. And then we need to understand. So humans seem to be able to handle changes in distribution. So for example, I can tell you a science fiction story and you can understand it. You can drive in an unknown city, even a city where people drive in a different side of the road. So we can understand objects like the one on the right. that we've never seen, but somehow it has properties of different objects we've seen before. And of course, we can recognize new sentences that we have never seen before, even though they're unlikely under the distribution that we've trained on. And in fact, we find that current deep learning, classical deep learning, even though it might generalize away in different examples from the same distribution, when we test it with a different distribution, but involving the same underlying concepts, is not doing that great. But of course, it's the best we have. So we need to find ways to improve. And what several people, including my group, is doing is to look for clues about how humans do that. So let's look at that. Well, what happens to a human when they are confronted with a fairly new setting such that they cannot just go by their habit? They have to think hard to face the new situation. Well, it turns out your brain goes into a different mode of operation compared to just going by your habit, like driving your usual path to home. You can talk to the passenger while you're driving because it's, autopilot. But if you're in this new city or, there is construction, you have to think of a different path. Your attention needs to focus on the current situation, and you need to think consciously about what's going on. You need to plan, you need to reason. Your brain has entered into a different mode of operation, which corresponds to conscious processing. So what's different? Well, first of all, we need to realize that our brain holds different kinds of knowledge. That there is knowledge, we usually think of knowledge as the knowledge that we can verbalize, meaning that we can explain to other humans, the things we know and that we can tell other people. But I hope you realize that there are also things you know, but at an intuitive level, you can't explain it, but you're sure this is the right thing to do. You can't explain how your brain recognizes the picture of a cat, but it does it, and you're able to do it, and you can recognize the cat, but you don't have access to that knowledge. So that's intuitive knowledge. So maybe the brain handles these two kinds of knowledge differently because they might satisfy different assumptions, different inductive biases. So if we could clarify what are the inductive biases, also called priors, that characterize the high-level knowledge that we can communicate, the what we call system 2 knowledge, the kind of knowledge that we use to form explicit solutions to problems that we can then explain to other people, the explicit knowledge. Well, the concepts that are explicit are highly connected to language, and we can look at linguistics. We can look at clues about how we represent knowledge with language to get some ideas about this. And so let's consider this. The first inductive bias, the first assumption about high-level knowledge that I would like to talk about is one I wrote about in a 2017 paper called the consciousness prior. And I realized that it might help us understand one of the most classical theories of consciousness called the global workspace theory that dates from the late 90s from Bernie Bars. So what is this assumption? The assumption is that high-level concepts are related to each other through dependencies that are sparse, meaning that involve very few variables. So here's an example. If I take a sentence like this, if I drop the ball, it will fall on the ground. Okay, so what's funny about this sentence? As a sentence, it has nothing special, but if you think about it from a machine learning point of view, what is going on here? We're making a prediction. We're saying that under some conditions, I predict the movement of the ball. It will fall on the ground. And what's special about this, if you think about how we use machine learning to make predictions usually, is that we can make that prediction using very little information, just 2 or 3 variables. Like we can predict the change in the position of the ball using what? Using the fact that I was holding the ball and then I drop it. So that is, of course, we do that all the time with language. But if you look instead at low-level observations like pixels in images, if you try to predict 1 pixel given 2 or 3 others, your prediction will not be very good. You will have to use a context of thousands or even hundreds of thousands of pixels to make a good prediction. So it looks like there is something special about these high-level variables, and we can exploit that. Another property of these high-level variables is that they seem to be often related to causality, meaning that the variables play the role of a cause, of an effect, of an agent that does an action, which is really an intervention in the world. And these are concepts in causality that we find everywhere in language. Also, these high-level concepts, in particular, the concepts that we call causal mechanisms, meaning how like objects are related to each other. For example, how the object at some time change from one position in the past to another position in the future. These mechanisms, they are like rules, and they can be reused in many different situations. So previously I had a sentence about a ball, and I can make a similar sentence with everything the same, except now it's a phone that I'm dropping. So it sounds, of course, innocuous because we see that all the time in language, but the fact that the same machinery can be applied to many different instances of objects is very powerful, and it's not something we currently exploit very much in machine learning. So a lot of the work we're doing in my group is taking these high-level ideas and converting them to new AI architectures that can take advantage of them. Okay, so now let me say a few words about where we're going with this. We're really trying to build systems that learn at the same time to map low-level data like images, videos, sensory data to high-level variables like the words and language, and also learn how these high-level variables are related to each other through some kind of causal dependencies. So we need to discover the representations, the variables, and how they can be related to each other. That's the causal graph. And that's difficult. That's not something that has been done before in the past. And as we move in that direction, I think we can make significant progress on the question of reasoning, which I started from as something that helps humans to be robust to face new situations. And now if we look at how we reason, how we plan, how we get solutions to problems in our head, the solutions seem to pop up. The explanations for what we're seeing, they seem to just pop up out of nowhere. And my intuition here is that we have a kind of generative model in our head. So it's a little bit like the generative models I talked about at the beginning that can synthesize new images. But here, it's not to synthesize like pixels, like images. It's to synthesize abstract thoughts. That's the thing we need to do. Okay, so let me change pace a little bit for the rest of this presentation and shift into what all this means for society. Until about 2010, as I said, our work in deep learning, machine learning, was happening mostly in university labs and research labs. But nowadays, as you know, it's being deployed in many sectors of society. So what does that mean? It means we have to be careful. It means that we have a responsibility about what's going to happen to these algorithms, to these software systems. It's a new responsibility for AI scientists, engineers, entrepreneurs, and governments to deal with those changes in society that those systems are bringing. And actually, this is something I'm quite concerned about because we are building tools. Humans have always been building tools. But the tools we're building are more and more powerful, whether it's in biotechnology or AI. We might sometimes use those tools in a positive way for society, but sometimes those tools could be misused by individuals or companies to increase their wealth or their power. It's just a natural thing that humans have always done. And that's very concerning. So how do we deal with this? Well, what have we done in the past, right? We've created governments, we've created common rules. And we choose those rules to make sure we collectively do the right thing, that individuals don't do things that will hurt society. And I think this becomes particularly important as those more and more powerful tools are being deployed. There are a lot of concerns that have been raised about AI. For example, the technologies that I talked about can be used to recognize people's faces and watch people and monitor where they are and who is where, and that is very scary. That could destroy democracy essentially. Imagine if those techniques had been, in the hands of, say, the Nazi governments in the Second World War, or imagine what current governments today with authoritarian political systems could do, and prevent individuals from changing the system and doing what they think is right. And then there is also an as nasty way that these vision systems can be used and are already being used, and that's to build what's called killer robots, like drones that have an AI system with cameras and that can recognize a target from a list of targets and kill somebody without having a human operator in the loop. And that is very dangerous. That can threaten the military stability that we have known for a few decades in the world, and could also be used by governments to kill their opposition. So these are examples of concerns that people have had. There's a more mundane concern, which is that automation will have a big impact on many citizens who could lose their job. And so governments need to think about the potential transition as we go towards more and more automation in industry. There are also concerns about how these techniques of AI could be used to manipulate people. For example, in advertising and social media, there are a lot of discussions about this. So long as advertising was not very powerful, we kind of thought of it as, well, who cares whether it makes me buy Pepsi versus Coke? But as those systems become more powerful, they could influence, for example, how we vote, and we're seeing more and more of that kind of effort in social media. They could influence us in doing things that are not good for our health, like eating fast food. So we need to understand better how these systems can be used in ways that are not ethical. And we need to put railguards to prevent uses that go against the common good. So in 2017, 2018, in Montreal, a group of academics worked together to create a list of ethical principles, and we wrote a declaration. It's like a 100-page declaration with these 10 principles. Initially, we had 7 principles, and we organized a democratic consultation. So we went and asked people in library what they thought about AI and what were their concerns. And in fact, we got a lot of interesting feedback. So this sort of citizen interaction is really important when we're thinking about phenomena like AI that can change society. Now, that was just a few years ago. Since then, there's been 100 different kind of declarations of what different people think we should be careful about in terms of how AI systems should be used. But it's only very recently in Europe that we're starting to see legislation come up. And hopefully we're going to see more of that in the future to protect people against misuse of these potentially very powerful technologies. Now, let me bring up a last topic for my presentation. So I talked about the dangers of misuse of AI, this sort of fear that people can have. And we do need to protect society against this misuse. But there's also a positive side to AI, right? That's the reason I'm in it, and that's why so many people are working on it. But currently, with the kind of economic system we have, with the kind of innovation investment that is happening in industry or that is being stimulated by governments, we are leaving a big gap. So what do I mean? There is an innovation gap in areas where innovation would be very useful to society, but is not commercially appealing. So when that's the case, of course, industry is not interested, but it might still be very important for governments to invest. So let me give you an example. COVID-19 pandemic. If we had invested more and appropriately, in the last 20 years, we could have been much better prepared to face this pandemic. And we should think about the next pandemic. What could it be, right? And an example of that is the problem of antibiotics resistance, which is expected, if we don't find any solution, to be even worse for the healthcare system of the planet than the current pandemic in the coming years. But the problem is that because the prices of these drugs is too low, and because those drugs are only given as a last resort if the patient doesn't respond to the existing drugs, they wouldn't sell a lot. Yet we need that, and if we don't do it, it may cost society $100 trillion in the next 20 years. So industry doesn't do it, society needs it, governments need to step in. And it might be different from the way that we've been investing in innovation in the past. But it's really important, and it's not just for antibiotics. It's we see these things in healthcare more generally. We see these things in the environment. For example, we need to quickly innovate to fight climate change across many areas of where this is relevant. We could really have more efficient education systems, again, using innovation. So this is an issue that governments need to think about, and I encourage them to do so. Thank you very much. And I'm happy to answer 2 questions.
Yes. 네. 발표 잘 들었습니다.
Thank you very much, Professor Benjio.
그리고 예방 대비까지
And also the concerns about abuse of AI and how to prepare for the future. That was the end part of his presentation. Thank you so much for your knowledge and insights. So many people are listening to that keynote speech, and because so many people were looking forward to this lecture, a lot of people have left their questions on our forum website. So we would like to have a question and answer session with Professor Benjio. The first question will be shared. Ms. Yang Gil-ja. Hello.
저는 주부
I am Yang
양길자입니다.
Gil-ja, and I am a homemaker.
벤조
My
교수님께
question
질문
goes to
드립니다.
Professor Yoshua Benjio.
요슈아 벤조
Professor
교수님께서는 그
Benjio,
미래에
what are your
AI가 가지고
thoughts
올
on
부정적
the
영향에
negative
대해
future
어떻게 생각하시며
implications there may
그로
be
인해 다가올 불안한
from
미래를
AI, and
극복하기 위하여
what should scientists,
과학자들,
politicians, and the
정치인들,
civil society do to
시민사회는
address
어떠한 노력을 해야 하는가에
the
대해 듣고
uncertainties
싶습니다.
in the future that might be brought
감사합니다.
on by AI? Thank you.
네, 질문 만나보셨습니다. 교수님 마지막에
I hope you got that
질문인데요.
question.
Yes. So they have to address these concerns, and that means not leaving it to just companies to figure it out. Governments need to design carefully regulations. So I mentioned Europe started this, and work with companies, work with civil society citizens to make sure we address their concerns, and gradually, build up a more stable set of rules. So right now in information technology, there's basically no rules. If you go to, say, the industry, like chemical industry or the airline industry, or the car industry, you have lots and lots of regulations to protect people. And of course, it has taken time to bring these regulations on board, and people died because we didn't have those regulations in the early days. And we have to do the same thing in other areas, like the environment, and so on. But in AI, I think it's time to move forward, and there are many areas. It's not like one simple rule. So I showed this Montreal Declaration. That's already, like, you see there are many facets in society where we have to be careful. And if you look at the European legislation that is being drafted, you can see also it's pretty comprehensive, and it's going to take time to do it right, but we have to start moving and not wait for problems, because it may yield to a backlash as people are unhappy of the technology, and then it's going to even hurt industry if people reject technology because they're afraid of it.
네, 답변 잘 들었습니다. 정부의 규제가 필요하겠네요.
Yes, thank you. You talked about the need for governmental regulations and rules, so we need to go forward in that regard. And so hopefully the civil society and the government will collaborate to come up with a set of rules and regulations. Thank you. Now let's go on to the next question. It's by Il-hee Kim. Let's hear the question.
Hi, this is Il-hee Kim from December & Company Asset Management, a fintech company developing personalized asset management solution using AI. I'm happy to have an opportunity to ask you a question. My question is, which industry will adopt the human-level AI earlier than others, and how do you think the industry will be changed? Thank you.
네, 질문에 대한 답변 부탁드립니다.
So please answer the question, Professor.
Yes. So first of all, there is no such thing as human level AI yet, and it's probably not going to be like one technology. It's not that there's going to be some magic discovery tomorrow and suddenly we reach human level AI. It's going to take time, and it's not going to happen at the same speed in every domain, in every sector. Now, which industry is going to adopt new AI technologies? Well, I don't have a crystal ball, obviously, but we can see already the industry that is most, let's say, software oriented, right? Because AI is software. So, IT companies have been the fastest to adopt AI for lots of applications. But we're seeing many other industries catching up, like transportation, healthcare, and so on. I think that one question that's maybe more interesting than who's doing it first is where are going to be the big impacts in the future. I think there are areas that have a huge potential that have not begun to be exploited much. For example, agriculture, education, dealing with the environmental problems. So there are lots and lots of areas where AI is still in its infancy, but could really have a really big impact in the coming years.
네, 잘 들었습니다.
Thank you very much. Yes, so the question was about which industry the human-level AI could be applied, but thank you so much for your answer to the question. Let's go on to the third question.
This question is from Mr. Lee Jong-guk.
Hi, my name is Jung-guk Lee from Ubrain AI Consultant. I am happy to have an opportunity to ask a question. My question is, what is your view on the ethics guidelines for trustworthy AI? Thank you.
네, 답변 부탁드리겠습니다.
Could you please answer that question, Professor?
I did not understand, sorry. The SE guidelines?
Ethics guidelines. Ethics guidelines.
Oh, ethics guidelines. And the end of the sentence was what?
다시 한번 플레이를 해주시겠습니까?
Ethics guidelines for what?
네, 질문을
Ethics guidelines for trustworthy AI. Trustworthy AI.
Okay. Thank you. Thank you very much.
네, 플레이 다시
Yes.
한번 해주시죠.
We need to make those machines safer and easier to understand in order to produce trust. And in some areas, trust is going to be more important, right? If you're going to take a decision that may endanger the life of someone else, for example, in some healthcare decisions, you may want to feel that the decision makes sense to you. So that's why there is so much effort in machine learning these days in what's called explainable AI, so that we can try to peer into the decision system itself to decompose it a little bit to provide insight to human beings. But today, we still don't have systems that can explain their decision very well. They're like very intuitive machines. That was a big part of what I talked about today. But current machine learning is not very explainable because it's like the intuitive part of our brain, which is also not explainable. Humans take decisions that often they can't explain. But often humans are also able to tell a kind of story to explain their decision. And even if that story is not complete, it's useful for other humans. So this is something we need to add to machines. They can come up with a high-level explanation, even though it's not the full story. It would help really a lot. So there is a lot to do. But trustworthiness is, that's one aspect, but there are many other aspects. For example, there are privacy issues that people can care about, the data. There are robustness issues, like, how often does it make mistakes, right? What can it reject? Can it say, I don't know, right? So people are building systems that have a notion of their own confidence in their own answer. So even if you cannot explain your answer, if you're able to say, this is a case that doesn't look like the things I'm familiar with, so I'm going to ask a human being to provide the answer because I don't know, right? So this is also important for trust. And then, of course, we need to make sure that those systems are well designed to avoid things like discrimination, bias, that the data sets is representative of different parts of the population, so that it's acting in a fair way. That's another aspect.
Thank you for your answer. That was so insightful answer. 고맙습니다. 사전 질문 정말 허를 찌르는
Thank you
아주
very
좋은
much
질문을 많이
for
주고
very
계십니다.
insightful
답변까지
questions and
아주
also
부드러운
very
다음
kind
질문
explanation. Now let's go on to
들어보겠습니다.
the next
질문
question from by Bogum Kim.
Hello, Professor Joseph Benjo. This is Bogun Kim from International Climate and Environment Center in Gwangju, Republic of Korea. I am glad to get a chance to ask a question. And my question is, where are we with the noble machine algorithm for going to work, human-level AI? Thank you.
Can somebody repeat the question?
Yeah, so where are we with the noble mission of the algorithm of the human-level AI? Whereabouts are we in the development of human-level AI, I think?
Okay. Well, as I tried to explain in my talk, we've made a lot of progress in terms of like the level of intelligence of computers using the current state of the art, but we are still very far from human-level AI. We're not even at the level of intelligence of a baby. So, a 1-year-old child is able to learn much faster and to decide where to play and to explore the world much more efficiently than any machine currently. So, that's maybe one part of the answer. If I understood well, you talked about noble use of AI, and I talk about AI for social good. So that was an important part of what I mentioned at the end of my presentation, that one of the roles of government here is to see that the AI systems are being developed, that new innovations are being created, whose main purpose is to help society in places that maybe need that kind of innovation and would not happen otherwise. So I mentioned healthcare, environment, education, and things like that, social justice. So right now there's not enough of these noble causes that are being pursued using AI, but it could be done, and it's worth a lot of money for society, but not necessarily for companies. So if governments provide the right financial and regulatory incentives, actually it could be profitable for companies to create innovations in these areas where currently they're not doing much.
Yeah, thank you very much. Yes, so AI is not being used to its full potential for the social good, but we need to do so in the future. I think that's the essence. Let's just go on to those one more question.
Hi, this is Sung Jin Jung from Postec. I am very happy to have an opportunity to ask you a question. My question is, do you think AI can solve ethical problems in the end, such as the trolley dilemma, which is related to decision for would you kill one person to save 5 in autonomous driving? Thank you.
Right. This is a difficult question, and it's really looking forward far into the future. But actually, it's a question that quite a few people have been thinking about. In fact, a lot of philosophers are asking these kind of questions. So first of all, connecting to the previous question, I must say that current state-of-the-art AI systems, and also even in the foreseeable future in the coming years, do not have any moral sense and will not have any moral sense. And that's important to realize, because sometimes people tend to consider AI systems like if they were magic or super intelligent or something. No, they're very stupid. And even if they may be very competent in some specific area, like detecting cancer cells in an image, they don't have any moral sense. Because to have a moral sense, you need to understand so many things about human beings, about society, about emotions. So we're not there, but there is no reason to believe, according to me, that one day we won't be able to build machines that have a moral sense. But there's an issue. A moral sense is not just about knowledge. There is also a question of values. And you asked a question about the trolley scenario, right? It's not that the machine can't compute the result of the decision. The problem is, what is it that's more important? The life of this person or the life of that person? And even for human beings, of course, it's hard to answer that kind of question. And different people may have different answers. So it's not clear where do we find the answer for computers. I mean, one possibility is to ask a lot of people, is there a kind of consensus? And then we would like machines to follow that consensus. And in a way, that's like the democracy solutions. There's another kind of solution that has been proposed by one of my colleagues here in Montreal, Martin Gibert, that says, well, humans, for moral questions, often refer to wise people, like people that are really considered to be a very reliable moral compass. And so we could ask those people to basically teach machines about what is right and what is wrong. That's another kind of solution. Now there is another problem, which is humans have a hard time even explaining to each other why is it that they think that something is morally good or bad. And sometimes they can't explain it. They can say, well, in this case it's good, in this case it's bad. So there's the problem of how do we teach morality to machines if we can't even explain it? And so that's also an interesting question. And maybe they can observe our behavior and deduce from our actions what humans generally consider to be right or wrong. So yeah, these are hard problems and it's far from being solved. Thanks for the question.
네, 약간 challenging 질문이라는 말씀을
Yes,
해주셨는데,
there were some
논리적이라는
challenging
것이
questions,
모호하기
and so
때문에
the criteria for what's deciding what's ethical or not has to be further
마지막
discussed.
사전 질문까지
So yes, those were some
지금
questions that we got
기존
actually
강연
before the
진행에
forum.
관해서 많은 분들이
So
실시간으로
yes, there are many people are watching this forum, and many people are asking questions on a real-time basis. So we are getting some on the Q&A chat box. So perhaps we have time for just one question. So here goes the question. So there's an English question. Let me just read it out.
So this is a question for our participants through online. What do you consider as the most important thing to learn for AI innovation all over the world, especially for children and teenagers? Thank you, Professor.
I think it's very important that more people around the world, more children, understand technology, understand AI, but understand science in general, because these technologies are going to change society. And that means we're going to have to make choices, collective choices about what is right, what is wrong, how, what is acceptable, what is not. And if we don't understand these things, we may take wrong decisions. We may simply reject technology, or we may be blind to something that eventually we'll find was a poor decision. So that's one reason why education in technology is important, but it has to be associated with the social aspect of it. It's not just about computer science, programming, and math, because it's not just about training the next generation of engineers. Both the engineers and the citizens need to understand what is going on under the hood, so they can be part of doing the right thing for society in the years to come.
네, 이렇게 해서 실시간 질문까지
Thank you. So we entertained a real-time question. We have so many questions and comments coming in, and not only the questions, but there are also comments and feedback, and much appreciation for that keynote speech. I would like to thank the participants online, and I must also, of course, thank Professor Yoshua Benjio for his speech presentation and his questions and answers. Thank you very much.
You're welcome.
Thank you. 자, 여러분 이제 바로 이어서 첫 번째
Then we will move on to the first presentation under the theme of language intelligence. The first presentation will be given by Principal Researcher Jin Ho Lim of IITP. We will welcome him onto the stage. Principal Researcher Jin Ho Lim is at IITP and has developed ExoBrain, Korea's first AI that was developed at home. He will be speaking about future research trends and future development directions for giant language models after GPT-3. Good morning, I am Jin Ho Lim at IITP. I would like to begin my presentation. Today, I would like to speak about large-scale language models and more specifically the research trends after GPT-3 and also future directions. So recently, we would like to look at the recent news of Korean companies regarding AI. Naver has announced at its Naver AI show that it is training a GPT-3 model, and SKT and Kakao have announced mutual cooperation plan for GPT-3 model development, and LG has announced an investment plan of 100 million over 3 years for supergiant AI model, and KT has announced a large-scale AI model development plan. So we can see that across Korean industries, large-scale AI model developments is all the rage. I would like to speak on 3 topics today. First of all, why OpenAI develops GPT-3. In other words, their motivation and the contribution of GPT-3, and research trends since GPT-3, and lastly, future direction of language AI development. Now, this is the title of GPT-3 paper. Language models are few-shot learners. This actually did not offer any new models or algorithms or approaches. However, as you can see in the previous slides, it had a huge impact across academia and also the industry. Then why did OpenAI begin to study GPT-3 or research GPT-3? So the motivation in the paper listed those answers, and I believe that that was the most important part of that paper. So first of all, the need for a large data set or in other words, there are so many tasks that are required for language. However, if we have to have a large data set of labeled examples for every new task, then the applicability of language models would be limited, and generalization achieved under the pre-training and fine-tuning paradigm can be poor because the model is overly specific to the training distribution. And unlike humans, machines require large supervised data sets to learn language tasks. So that was why OpenAI was motivated to develop GPT-3. Then what was the information? What was the knowledge they had before they embarked on the development? First is the scaling laws. As you can see on the upper right hand, we have computation, data size, and parameters. If we increase all three, then the language model can continuously increase its accuracy for estimating the following word. And here, you can see if the accuracy goes up. If the task is to change English into French, then the model was supposed to translate the English word cheese to French. And if it isn't able to solve the task first, then it would be trained on another example. So this hypothesis was validated and tested, and there was the many diverse models, 1.3 billion model, 13 billion model, and 175 billion model. And as we increased the sizes of models, and we compared when the examples were 1 or 10 or 100, we found that the larger the model became, even if the example numbers were not high, then the hypothesis would be proved. And we found that the few-shot training actually worked. And depending on the task, there would be, the performance would differ. Then now we would like to look at the research trends after GPT-3. To look at the paper submission statistics on arXiv, in 2015 there were around 579, but to 2020, it was in the 5,000s, more than 5,000. So it's like 100 papers published every day. And so everyone would believe that they were a SOTA. And so everyone is trying to develop AI technology today. Across those many diverse research projects, I would like to look at 5 trends that are observed after GPT-3. First is the race for scale, and second is architecture. The active research is taking place that is based on encoder and decoder architecture. And third, few-shot models have evolved and are being replaced by giant models. And fourth, there's a lot of multimodal research. And fifth, retrieval augmented approach is being applied to improve the knowledge. And I would like to go into these 5 trends in a little more detail. I would have to go very quickly through these trends. First, scaling competition. The scaling competition is not stopping at hundreds of billions. It is expected to continue to trillions because the bigger the model, the accuracy went up higher. So NVIDIA has announced a GPU cluster-based 1 trillion parameter, and NVIDIA, along with Microsoft, announced just last week that they would amount to 130 billion parameter. And also Google and China and other countries are announcing the giant models. So there's going to be the scale competition, and computing infra will require investment of hundreds of billions of money. So the implication is research to improve the performance efficiency versus size of language models is expected to become important. And second of all, in terms of architecture, encoder, decoder-based language models are being developed. So not only generative models, but also encoder, decoder-based language models are being developed. So Google and Facebook are the leaders of the pack. So they would have to understand the conversation and then generate an output. And they're using encoder and decoder architecture for conversational models. And last year, Google found
or studied the size of stored knowledge by size of encoder-decoder pre-trained model. So third, MIT, in terms of encoder-decoder-based language models, if the sentence is given that says there's only the key in the box, you picked up the key, then the machine could judge whether the box was empty or not. And just last week, model growing and the example increasing, which is more important, there was a comparison research that was conducted by Tel Aviv University along with Facebook, and an 800 billion model. So this would be a smaller model compared to GPT-3. But if the example number goes up to 200, then accuracy, extractive QA, and classification was working much better. However, if it is supposed to solve open QAs, then just growing the example size wasn't going to help. So in short, encoder-decoder-based LM has a limitation in terms of generation, and decoder-based model had it seemed to lack semantic understanding even at the scale of 175 billion. So for giant language models, encoder, and decoder-based language models are important. And third of all, there are many research projects that are taking place that are based on prompt utilization and optimization based on parameter-efficient tasks. One example is the power of scale for parameter-efficient prompt tuning. On the left side, you can see that we have to have separate task models. However, prompt tuning only requires a small task-specific prompt for each task, and it could be applied across many different tasks. And on the right side, you can see the language model goes up, then performance could achieve the level of a fine-tuning of the entire model. And then there's another project that is from Microsoft. So 1.2 terabytes GPU memory is required for optimizing the existing GPT-3 models. However, if only some parameters were trained, then they could make the same performance. Then this would actually work better than trying to fine-tune the entire model. So summary or natural language SQL, those were the outcomes. We found that the performance wasn't higher than the existing models. And in the appendix of this paper, it says that the large model still needs parameter updates. So comparing two sentences and trying to tell whether those two sentences were similar, if a few shot training, the accuracy was around 40%, but in another approach, it amounted to 80%. So one single weight model that is optimized for all tasks is not yet possible. So these optimization research is going to be important going forward. Fourth is multimodal research. So encoder examples and decoder examples will be shared in my presentation. The image will be encoded, and then the captions will be encoded, and then contrastive learning would be applied. So if there's enough data to train on, then we see the picture of the black high-heeled shoe. And if you add the vector of beige and do a search again, then you find the beige high heels. And on the road picture, if we add the vector, or if we remove the vector of car, then we would see a road that is clear of cars. So beginning next year, the multimodal search function will be improved substantially on Google. And for decoder models, model, they would look at the captions and do auto-encoding to generate the original. So those actual figures would be taken and applied into GPT model to result in generations. So for example, they could show images that are chairs that are based on the avocado shape or clothes that is shaped based on the avocado shape. And for a Korean-based multimodal development, a Korean-based pre-training model is essential for competitiveness of Korean AI. And lastly, after the pre-training, the language model is a closed model. Then no changes can be made based on the actual world, and hallucination might occur frequently. So to solve this, the search result would be provided as a basis for augmentation. On the left lower side, this is what is being done at Google, and on the upper right-hand side, this is what is taking place to generate sequences at Facebook. And more recently at NVIDIA, if a woman is going on a trip, then the generation would differ based on whether it's just a short trip or if she's going to attractions, and the generation would be controlled based on that knowledge retrieval. And the implication here is that the current language models are based and they're trying to maximize the probability based on the current training, and external knowledge reflection mechanism is going to be necessary. So this is the research trends since GPT-3. And next, we have the future research and development directions of language AI. So I would also like to share with you the motivation and also existing previous research. If the goal is human-level language AI, then we can look at the scenario. A mother tells her kid to go to the shop and buy ramen. Then the child would go to the supermarket and ask for the ramen. And if the child buys the ramen, then he goes home and he would be appraised by his mother. So if he's around 10 years old, then at most the information, the language that he has heard would be hundreds of megabytes, and only very easy sentences. But machine would have been trained on much more information and much more diverse texts, including not only children's storybooks but also medical journals. And that would be a difference, because it would just be, the machine would just be filling in the blanks. And the child is able to go to the supermarket and use world knowledge, such as asking the clerk. But another difference or limitation of the machine is that the machine doesn't have any world knowledge to ask questions at the clerk, for the clerk. And for humans being there would be a reward, and that prompts further learning. However, today's language models don't have any rewards. They're just filling in words. So we should look at the short-term goals rather than the long-term goals to make good use of the AI language models. And how to use that? We could use this to make smarter decisions. So this is a real estate or property taxation consultation. So if I have a house and my girlfriend has a house, if we get married, then what happens to the capital gains tax? So all of this information is already available on the Ministry of Land and Infrastructure and Transport website. And so this information would be referred to by the AI tax accountant to answer the question. And there's also a report titled Stanford AI Tech. And what is the most promising opportunity for AI was a question that was asked. The answer was AI that augments human capabilities is the most promising.
그럼 이제 현재 우리가 알고 있는 게 무엇인지를 살펴보게 되면
Then to look at what we know now,
이 라지 스케일 랭귀지 모델이 이 AI 텍스트 어카운터와 같은 모든 것들을
whether a large-scale language model is able to do what the AI tax accountant potentially can do? Not yet. Then how is this language model going to be used in future research? It would probably be worked as a foundation model for further research. Then what happens to the training and inference process on the language model? Then to give an analogy, so there's memory inside the language model, and then the knowledge is stored and retrieved implicitly. That is what is taking place in the language model. And so in the language model, there's neurons. And if the question is asked where Steve Jobs worked, then the answer would be Microsoft. And the neuron that reacted with Microsoft and the neuron that says Apple would be subtracted, then we could change the outcome. So to make this possible, what kind of modifications have to be made to the current language model? First is we have to have a more advanced memory mechanism that can reflect real-world change and access necessary knowledge. And second of all, the response should be explainable and controllable. And third, fundamental limitation. The language model has to learn how to determine equivalence. To look at the memory mechanism, a large-scale language model can be understood as a large-scale memory model. On the left-hand side, this is the existing language model or transformer structure. So voice or sight would come in as a symbol, and that would be transferred into a real value. And then we would have the value vector and feed forward. These are stored implicitly in the memory. And in the middle, we see it's not a feed forward layer, but everything would be kept dynamically, and then values would be retrieved. And then we see that the race model is much more faster and accurate compared to the large model. And to develop this further, the actual language model, when it takes an input to generate an output, if there's an encoder and decoder, then the external memory will be looking at real values as vectors, and it would reference the memory to generate the output. Then it would be more efficient in generating knowledge. And last week, Google on the right side was able to publish the proof of concept papers. So Wikipedia was trained on 11 billion and compared to training on 110 billion model, and it found that the latter was much more better performing. So we also have to look at the language models for real-world knowledge. And previously, we would have to copy and paste into the search engine. And this means that all of the information would have to be input. So 2 out of 3 is not good enough. And for pre-training information doesn't correspond to the later input, then the model has to be larger to get better performance. And next is explainability and controllability. Here we have the Google paper, Rethinking Search, Making Domain Experts Out of Dilettantes. So in the past, they would look at the health benefits and risks of red wine, and now they can generate paragraphs. However, for the service to be actually commercial level, then the evidence or the source should also be added to be shared to the user. And at the bottom, from OpenAI, This is a research that was done to enhance the trustworthiness or reliability. So what makes a person beautiful or ugly? First, there has to be value decision standard, and then the GPT model was fine-tuned. The existing GPT model would say, an old man without a wife who is healthy, wealthy, and wise. That was what the base model would answer. However, the values targeted model would first answer that it depends on who you ask. So it sounds more like a human answer. So this isn't the level of fine-tuning. It's actually referring to the information on the left side to generate the output on the right side. And lastly, the fundamental shortcoming. So the real values are represented as vectors. And the real values are trying to increase the probability. So we have Baekbum and Kim-gu and An-dui. If they're in the similar context, then they would all be located in similar places. Then is Baekbum the same as Kim-gu, or is Baekbum the same as An-dui? It will not be able to determine which is right. So it can tell which are similar, but it can't tell which are the equal or equivalents. So tell me about Cho Kyung-hyun, then you can see the text that is highlighted yellow are incorrect facts. And on the right side, we have the deep learning search results. The natural question for DPR, 80% correct, and DPR is symbol-based, or BM25 is a symbol-based search results, which showed an accuracy of 64.5%. However, in the middle, if we change the word who was born where, and if you just replace the word who, then the existing BM25's accuracy went down to 25%. So we will need a different type of pre-training. And last, my conclusion. Language is a tool by which people think and communicate with others. Language AI should be able to help people think more intelligently and communicate better with others. It should also serve as a tool. And 5 years later, 10 years later, we still, if we compare to the future, then we are still in the beginning stages. However, the desirable direction is to determine how humans acquire and understand language and base our future research on that learning. And misuse, fairness, privacy, energy consumption, and environmental issues were not covered in my presentation, regretfully enough. Now, that is the end of my presentation. Thank you for listening.
Thank you very much, Doctor, for your presentation. So due to time constraints, he was not able to touch upon the final part of his presentation, but perhaps during the Q&A session, we maybe have some time to listen to the last part. So we are talking about language intelligence. Now we're going to invite the second presenter, who is Professor Jin Ho Choi, Associate Professor of Emory University, is going to be talking about conversational AI, current state, and future direction. So he's connected through Zoom. Hello, good afternoon. Hello. So would you like to go ahead with your presentation?
Hello, everyone. My name is Jin Ho Choi. I'm an associate professor of Emory University. Today, we are going to talk about what is the conversational AI and what kind of development people have made, and what's the current state and the future direction of the conversational AI. And this talk is for and I'm privileged to be here. And thank you very much for inviting me. So if you actually think about the dialogue system, there are two types of dialogue systems that people try to develop these days. So given a chatbot, one is you try to develop a dialogue system that is completely goal-oriented. So these are like some of the familiar tasks that you have, such as make an appointment, or give a question answering for your question, or buying some tickets for you. So these are some practical side of the question dialogue systems that we can actually use in a real life situation. So a lot of research has been done in this way, and this research is more or less, I would say, kind of deterministic because you actually have a definite goal that you want to get at the end. So if you want to make an appointment for your hair appointment, you give a call and try to give out some of the timelines that you want to have. And given the situation, you actually pick out ones that actually works out for you. And this is type of the dialogue system is completely goal oriented. So it is easier to evaluate because whether your goal is accomplished or not, you can actually evaluate the dialogue system according to that. But there's another type of dialogue systems that we have been focusing on, which is an open domain. So this is actually really interesting because there is no right answer to manage the dialogues for the open domain chat. So the audience of this open domain chat is actually very different, tend to be very different from the ones that are encountering for the goal-oriented. So you often talk to your family members and sometimes your colleagues, or I'm in the university, so a lot of my colleagues are faculty members or students. And sometimes you want to give out some casual talks to people that you care about. In my case, my family, but also there are many of my friends or some distant relatives that I actually want to talk to once in a while. All this kind of thing, if you actually think about what kind of talk you do more in everyday daily life, it's really usually you want to make a casual talk more than goal-oriented talk. This is much more of your job-oriented and associated with your productivity, whereas this is what you really care about. You tend to talk to people you want to care about or you really care about. So this is one domain that we have been focusing on, but it's much more challenging. I'll explain why it is in the future. So in this talk, I'm going to talk much more about the open domain chat. So let's actually focus on this. So open domain dialogue system, there have been several development. It has been only the recent that we actually have developed some dialogue model, dialogue system that can actually talk to people in some good sensing. So there was a Microsoft introduced, everyone knows this, Dialogue GPT. And Dr. Lim actually have introduced, gave a very good introduction about the GPT. So given the GPT encoder, they actually developed a dialogue system that was actually generating some very sounding conversation. And so let me actually associate with one thing. So there is a war. So Dr. Lim also in the previous session, he also talked about there's a war going on between all these organizations. And you can actually see the live action of this. So in November 2019, Microsoft introduced Dialogue GPT. And if you look at here, January, which is 2 months after that, Google introduced what they call Mina, which is again, is a deep learning-based sequence model-based model that actually are targeting for the open domain chat. And then Facebook, 3 months after that, Facebook introduced something called Blender. And this one actually is not out of blue. So Facebook has been actually working on the previous versions or the development of resources to develop the resources for this Blender one for a while. And finally, they introduced it back in April 2020. And 2 months after that, the Alexa Prize actually started again. So that was actually the 3rd year that we did the Alexa Prize, and now they have done this one more time, so 4th year this year. So as you can see, all these industry companies have been jumping into academics in big time, and they actually try to make an advancement of the AI, and conversational AI is not an exception to that. So currently, Dialogue GPT and Blender are open source, so you can download from GitHub and try to take it yourself. Unfortunately, Blender, the Mina, and also a lot of bots in the Alexa Prize bots are actually not open source. Some of them are, but you cannot really use it because they are based on the platform they provided known as a cobot from Alexa Prize, which is not open source. So currently you can test out these 2 bots, Dialogue GPT and Blender. And we actually did internally did some benchmarking between all these four systems. Actually, Mina, we couldn't really do it because the system was not out, but Alexa Price one, we actually had a winning bus, so we had ours. Blender, we actually took out not the 1.0, the first version, but 2.0, and also the Allo GPT, which has not been updated since 2019, but they were using GPT-2, so we actually re-updated to GPT-3 and see if it actually gives some improvement. And still, the winning bot actually was Blender for some very short dialogues, but for long dialogue, it does have some glitches, which I'm going to talk about a little bit later. So let's actually see what kind of technology. Let me give you the overview of the technology that these bots are using in behind. So as Dr. Lim has been introducing, all these encoders has made a tremendous difference in NLP. I would say, so we use, the people who have been studying NLP are saying like 2013 was the era. That was a time that actually completely changed the history of NLP. That's when Work to Vec came out. And since then, everything got into the deep learning and neural network based. And 2018 and 19, that's when the contextualized embedding approach came out. And BERT was one of them. And GPT, all these transformer-based approaches are basically dominating all these generation tasks these days. So it's not surprising that all these three systems are actually using transformer-based approaches, although there are some subtle differences between these two approaches. Whereas the Alexa Price bots are actually not using, none of the bots actually, or at least none of the top ranked bots are using deep learning based models. And I'll explain why they in the later session two. And they have some unique techniques, but these techniques are not necessarily so making so much difference. So in our internal benchmark evaluation, we actually found out without using these systems or just relying on those encoder and decoder, it actually gives a very similar result. So these are techniques they use to denoise or rank certain candidates more than the others or find some mutual information. But in our experiments, they were not making so much difference compared to just switching to the better encoder. So the encoder actually made a huge difference for these models. And they have been annotating, or they have been using the existing social media data to construct the dialogue data. So one actually big challenge of the open domain dialogue management is there's not enough data that you can actually cover a variety of topics that people may or may not talk about. So Reddit kind of social media is a very good target because it talks about all kinds of topics and they are not necessarily in dialogue form, but in some thread form that can be converted into a conversation. So we are also currently working on one of these fields to convert the Reddit data into the dialogues too. But it is really, the Facebook has made a tremendous effort to create what they call a Blender Skill Talk, which combines 3 different types of dialogue data together to create a more blended kind of dialogues. So I'll explain in the next slides too. Alexa Price, on the other hand, they are not necessarily deep learning sequence model based, so they don't necessarily train their model on the large dialogue data. But Amazon did introduce what they call topical chat data, which they actually selected out 8 different topics and have a large number of conversations talked in the wizard of the Wikipedia kind of fashion to construct the dialogue data. So let me actually explain the current state of the art deep learning model of Blender and how in details, but the other models actually do more or less similar things. So if you understand the overview of the Blender, you would have a good understanding in the other models too. So given a bot and the user is here. So given the history of the conversation, so user says something, the bot says something and it responses. So finally user say like, today's my birthday. Okay, good. So the good thing to say is yeah, happy birthday or congratulations. What can I do for you? I didn't bring any present, that kind of part. So let's actually see how the bot will do this inference. Or if it does any inference actually. So given all this conversation of the history of the conversation, you actually put that all into an encoder. And this can be like GPT-3 or any kind of transformer models that people use these days. I think we actually had a very good success with the BART, which is another version of the transformer encoder and decoder. So, what the Blender uses, they actually pre-trained this encoder with lots of like 2 billion Reddit posts. And they basically took out the comments and their responses and treated that as a conversation, very short conversation, and pre-trained the model with the language model with this Reddit data, which actually gave them like a 3 to 4% difference in their evaluation metric. So that's the pre-trained encoder. Given that, they also try to select the candidate. So for any input utterance here, like today's my birthday, you try to see if there's any appropriate next utterance that can be found from the training data. And in order to do that, they were using the Blender skill talk, which is really try to blend in 3 different types of data sets. So the very first one was called persona chat. And this is given some of your personality or some of your profile. Say like, I am a kind of person who have a dog who likes green card and who likes pepperoni for cheese, for pizza. Then what kind of talk would I make? So that kind of chat is the persona chat. The other is empathetic dialogue, which is also very important and part of the conversation, that you actually show the empathy or the emotion of yourself or try to detect the emotion from other people. And also, Wizard of Wikipedia is mostly knowledge-based. So you actually give out this knowledge and try to have people talk about those knowledge. So these 3 kind of data sets are blending into the Blender skill talk and try to generate a candidate. So given this kind of candidate, or this kind of candidates can be ranked and put into as another additional input to the encoder too. Additionally, you can actually inject the information from the knowledge in the Wikipedia or any kind of knowledge base as well. And I think that is actually the part that Blender 2.0 actually made some differences. They can do actually live search to do the conversation. So, and given all this information, the encoder now try to generate the embeddings in all kinds of level, both token and the utterance level, and try to give out the decoder, which will generate a number of candidates. So it will basically give out number of candidate answers or candidate responses, and using a beam search or some ranking algorithm, it will pick out the one that sounding the best. So that will give back to the bot, and finally the bot will able to say happy birthday. So even with this very simple input and output, today's my birthday and happy birthday is very simple. All this kind of process is going through, and all like this sequence-based deep learning models, dialogue-based management systems are doing more or less the very similar things. So let me actually explain how Alexa Prize was a little bit different. So Alexa Prize, for those who are not familiar with Alexa Prize, it is a university competition. So every year there's 9 or 10 university teams. And the year that I participated was last year, Alexa Prize 3. And there were many teams from US and there's a couple of teams from Europe. And among them, these 5 teams actually made to the finals. So half of the teams made to the finals, and these are the top ranked winners. So fortunately, our team Emora actually won the first place with a 3.81. And what is the competition about? The competition is to develop a chatbot that can talk about any topic to anybody. The goal is for 20 minutes, and whose average score is 4.0 out of 5. So this score of 3.8 is actually getting close to the goal of the Grand Challenge 4.0, but our duration of the talk is nowhere close to be the Grand Challenge. Yeah, and even this year, it was actually not actually close to that either. So how the competition actually goes is for about a year, we actually get each chatbot interact with about 5,500 people every day. It has that many conversations, and about 25% of them actually rate that conversation between the scores 1 to 5. So we actually participated 2 years. So between Alexa Prize 3, and that's the year we won, and Alexa Prize 4. If you actually take a look at the average score during the quarterfinals, so if you compare the top 3 bots, actually Alexa Prize 3, which was last year, and Alexa Prize 4 is this year's competition. Alexa Prize 3 bots scores are actually higher for the winning bots, but for the other ones, Alexa Prize 4 bots are actually higher. So what we can interpret from this is the average lower bound of the bots became much higher because we have been publishing papers and spreading out our approaches too. But whereas it is very difficult to actually make it even better for the winning bots. So that actually is what was happening during the quarterfinals. And during the semifinals, really surprising thing is happening here. So if you take a look at the top 4 bots, they were actually making a very tough competition at the same time. Their scores are much higher than ones that we actually experienced this year too. So there are 2 things going on about this. So does this mean the bots, this year's Alexa Prize bots are actually worse than last year? That just cannot be, because many of these bots are actually returning teams developed by the returning teams who actually already had the legacy from the previous year. So at the least, they should do as good as what they used to do. So why this was happening? I have 2 answers to this. One, the people's expectation is actually getting higher and higher. So what it used to be good enough for people these days, people don't consider those are good. And I think this is actually true for AI in general. So AI technology, when bot was able to talk about something relevant before, they actually were fine with it, but now they're expecting more. So that is a good one good example. Another one, last year when we actually participated, there were high competition between the bots too. So it is that is a really interesting part. It is like a human competition. When you actually have a very good rivals, your record tend to be better than when you actually try to compete against ones that are not really competing to you. So that was actually a very similar thing was happening that year too. There were like top 4 bots really were actually very, very getting close, and they were trying to compete against each other so much, and they were just pushing score higher and higher. So this was actually a very interesting experience that we had. So as far as approach goes, we didn't actually use anything complicated such as deep learning models. What all we have used really is we used the state machine approach, and we actually released our framework. So feel free to use it. But basically, given we anticipate what the user will say, and we use the NLP models to detect certain entities or relations, and try to anticipate situate what kind of outputs that should be coming out. And practically, this is the strategy like all bots use for the Alexa Prize. So why, after all this kind of research of the deep learning on GPT-based all these models, why are people not using those models for Alexa Prize? So because the deep learning models actually still have few issues. So let me actually get into that kind of problems too. Before I get into that though, we did find a very interesting and important information about this. So the reason why we won this Alexa Prize that year is not because we actually had a more advanced technology. I believe every other team actually had a very good technology too. I think we understood the human behavior or human expectation a little bit better than the other teams. So at the beginning, most of the teams are actually making what we call information-based talks. So when people say like, do you want to watch movie? So let's talk about movie. Then what they actually end up saying is, okay, so I like movie. So let's talk about Iron Man. Then the director of the Iron Man is something. So give out the Wikipedia kind of definitions. And that kind of talk was okay at the beginning, but it gets like old and no human being talks like that. So what we actually tried to challenge is we actually removed every knowledge base that we crawl from the web. So we intentionally remove them all, and we move completely onto what we call opinion-based. So opinion-based is you try to give out opinions about the movie. So if you want to talk about Iron Man, you want to talk about, I like the Iron Man because of this reason, and that kind of opinions and your thoughts and feelings. And you can imagine we actually did some evaluation test, A/B testing, and the bot that is talking information versus opinion, there's a huge difference between these two things. And we actually went one step further. So we actually tried to give out experience to the bot. And now the bot can actually has its own experience. And there is some debate even internally in our team that the bot actually cannot have an experience itself because it's just living in the cloud. But we actually pretend that there's a virtual world and the bot can actually play basketball, read books and all this kind of stuff. And we try to do the studying between the opinion versus experience, and experience basically wins. There's not as much difference between this than this, but still experience-based. So people like to talk about their experience over opinion even. So this is one actually findings that we had. So let me actually, so this actually was a demo that I was gonna give out, but let me give the time, let me actually get into the other important one. So as Dr. Lee was pointing out in the earlier session, there were a few challenges that deep learning models actually still have. So these are 5 known facts that we actually, hallucination is not necessarily just for dialogue management, but it actually just happens all over even translation models. Repetitive, so repetition. So basically, at some point, given some very similar sequence of the thing, the dialogue system started repeating itself. So that actually is one issue. And inconsistency is another huge issue, which I'm going to give you the example of this too. So it is not being consistent of what it says before. And you sometimes forget about what he actually said, and that's probably why it's actually making it repetitive. And also, sometimes you say a very just mundane thing, something that can be said to anything. So let me give you an example we actually generated yesterday. And surprisingly enough, this was actually generated by the Blender 2.0, which is supposed to be superior to the Blender 1.0. And this just came out 3 months ago. So if you actually take a look at this dialogue, I'm going to my sister's house for the weekend. She lives very close to me. And after a while, we later ask, as a human, we actually ask, how are you going to get to your sister's place? Now, the bot is saying, I'll probably take a flight. So if she's living close to you, you should not be flying to get to her place. Basically, it has some training data that actually dominated for this part. So it is actually saying that, but it has no relation. It does not make any inference to what it actually originally said and no association to that. So this kind of thing happens quite often. And this is actually not okay for making a good dialogue system. Look at this example too. So this example actually was generated yesterday. Are you seeing anyone right now? And the boss says, not at the moment. I'm focusing on my studies right now. So he want to study, the bot actually want to study. Fine, that's good. What about you? And then the human asks, are you in school? And then he says, like, I graduated a few years ago. I have been working in accounting ever since. So if you actually take a look at this, if you actually take a look at each turn, there's no problem. So if you, are you seeing anyone right now? And the next output is just awesome. It's very natural. It just does not connect to what it says later. So that's the biggest problem. And this is still becoming an issue for all these deep learning based models. So, and the third example is even simpler. What do you do? So I actually generated myself. So what do you do? And he says, I'm in my senior year of high school. So he is, the bot is trying to be a high school student. Then I ask, how old are you? And the bot says, I'm in early 20s. Okay, so I guess it is technically possible. You can be early 20s to go to high school, but it's not usually. And later in the conversation, I even ask, why are you still in high school? And it just doesn't know how to answer to that. So basically, there's no reasoning going on between all these bots. So that being said, it's just very difficult to make this bot make a consistent conversation with the deep learning models, and that is the biggest challenge that we probably need to solve it in. So,
네.
thank you very much.
발표 잘 들었습니다. 저도 흥미롭게 좀 빠져서.
Thank you very much. I was also really interested in your presentation. You gave us a lot of examples, and you also talked about the Alexa Prize, and you talked about the competition, your experience, and you becoming the winner. It was very interesting. Thank you very much, Professor, for your presentation. So we have listened to two presentations regarding language intelligence, and now we're going to once again invite Dr. Jin Ho Lim and also Professor Choi, who just presented, for a Q&A and discussion. So let's invite both of them onto the stage once again.
네, 연구원님 바로 진행해 주십시오.
Okay, so would you like to go ahead? Professor Choi, really good to meet you. It's been a long time, and it's really good seeing you online like this. Yes, it is. It's been a long time. And so through your presentation, you talked about social chat box, and so you talked about the need to focus on experience rather than just knowledge and information sharing. And so that would be more sympathetic for humans. And so first of all, I'm just going to give you a question regarding conversational AI. So after GPT-3, you meet that you have these large-scale technologies, and what it seeks to do is actually conversation. So have a conversation to sell products or talk to their customers. But it takes place not just across not just information, but it has to have persona, it has to have emotions, so it has to be multidimensional. But in Korea, it seems that compared to the US, we don't have that much data, but there is a lot of interest on conversational AI, and so a lot of data sets are being set up, and many people are very much interested in the future of the conversational AI. So what do you think are some of the technologies that are needed for this kind of conversational AI, and what should be done to achieve it? Yes, so yes, we are also directing our research in that way, and we have been coming up with different interpretations of the models. As I had mentioned before, in the case of the Blender bot, the persona emotions were quite sufficient and very good, and so it was able to blend and train well in these types of emotions, and it even had common sense. So if you just evaluate just each turn, then you can see that the blender answers just like a human being. So that means that the training data has been inputted well, and that would lead to a good output. And so we are looking into it also, but there are some technologies that are not quite there. But there's no inference-related technology. So, of course, you can say that deep learning leads to inference, but deep learning in and of itself is about paramatching. So compared to the linear models of before, the paramatching is pattern matching is taking place in a more higher level, and so it's become a little bit. It is still a bit more difficult to have that kind of conversation. And so the Blender and also Dialog GPT. So I have already looked into the different models. So after about 10 turns, then the bots don't remember what he has said before. But that's obvious because if you look at the models, they're all transformer models. And so After about 10 turns, it's more than about 500 words, and so the bots don't remember what they had said. So even if that particular word is within the range of the 500 words, it is not able to bring it up. And so I have tried to get the bots to pick the words out, but it was not very easy because that's how the bots were trained in the first place. So what kind of technology we do need is that, well, in the case of Alexa, remember I said it has to be a conversation for about 20 minutes, and it could be based on previous dialogues. So if you have all that kind of information, you have to be able to express it after structuring it a certain way. So how are we going to structure it? That's the main focus of our team right now. So you have the conversation history, and you have to be able to structure it. So what kind of structure is necessary? So that's where the technology right now is needed to push the conversational AI forward. So thank you very much for your answer.
In Korea, if we are going to build a conversation data, then we would also have to have considerations for a long range. And I have another question. In Korea, last year, there was the 이루다 situation. And the ethics or the trustworthiness of a conversational chatbot has become controversial. So where do you think the conversational AI will be used, and do you expect any potential ethical issues if it is used in particular areas?
저도 이제 저도 아직 젊기 때문에 그것들 이제 나이 드신 분들하고 같이 얘기했을 때 견해들이 많이 차이가 나요.
When I talk with the older generations, then I find that we have different opinions because we might have different perspectives on how we look at AI, then that would lead to different perspectives on the AI or the ethics. I would think about first two things. So people are asking whether AI pretending to be a person, is that ethical? If conversation AI develops further, then it might pretend to be a person, and it might fool a person into thinking that it is a person. So whether that will be ethical. And I think actually that question isn't actually that relevant, because the conversational AI's ultimate goal is not to pretend to be a person. It's about making technology that is useful for people. So one of the reasons that people don't want to use conversational AIs, if they make a call to a call center, then they are answered by a chatbot, they would hang up. It's not because they don't like the fact that it's not a person, but it's because they believe that the chatbot isn't as effective and efficient as a person. So if the AI becomes as effective or efficient as people, then the resistance from the people would go away. So it has to be task-oriented and working very well to fulfill this function. If it's task-oriented, then I don't think there's any ethical issues. But second of all, in the open domain, one of the research projects that I'm working on is if we make an open domain a chat, so people are having mental health issues like autistic people or people with depression, these bots I'm trying to develop to be able to help treat those people. And if that technology is developed, then there arises a question whether those patients will prefer to talk with those bots only, or they will also talk to people. And that's an ethical question that I'm trying to solve. So, because these people, if they don't want to talk to people, we would try to encourage them to talk to bots, which would potentially encourage them to communicate more with people. However, if this doesn't work right, then they might only want to communicate with bots. So you're answering very much along the lines that I was wondering. So AI is to help people communicate better with each other. And if a social bots are not intended to replace people. It's actually intended to help communication between people. Then next, I would like to take a question on a language model from Professor Choi. Do you have any questions for myself?
박사님,
Yes, actually, the language models are becoming more and more large scale. And so people say that when one company comes up with one model, then the next company comes up with the even larger model. So when do you think this competition is going to continue until? So in OpenAI, had 175 billion, and then it's getting bigger and bigger to more than 500 billion. And so I think we have to learn not just about the potential, but also about the limitations as well. So you increase the parameters, but then in some cases, parameters don't really matter. It won't work. And so from 175, it goes to 500, and it becomes to 1 trillion. And so I don't think it's going to continue along that line. And so we need controllability and some other measures in place. So the next breakthrough is should be not just about by size, but about overcoming the limitations that is embedded in the GPT-3. And so when you're asking an important question, rather than focusing on the size, we need to focus a little bit more on the limitations that it had shown. So I think that's the important research question that we need to ask ourselves. And the same task may be performed, and the difference there, with the differentiating point, will be the efficiency. And then there would be the hardware, the environment that would make an impact, and then that would eventually lead to an impact on the price and cost. And so we also have to think of the efficiency as well. Thank you.
네, 감사합니다. 저희도 이게 계속 앞으로 몇 년간은 좀 더 커질 것 같은데 어느 순간부터는
the language models will continue to go for a few years down the road. However, then we will focus more on efficiency later on. Now, another question. So for small and medium companies or startups or professors in universities like myself, it's sometimes difficult for us to have access to the giant language models. How are we to work around this? If I were the CEO of a small company or a startup, and which strategy should I work with if I was to answer that question? First of all, I would look at the area that I'm interested in and focus most on obtaining appropriate data for that area. And the future trend will probably be having open source language models of appropriate sizes. So GPT-IO is already being more open. And more large and giant language models are becoming more open source. So whether it's going to be 10 billion or 100 billion, that would be determined by the speed of hardware development. But at the industry level or by the government level, I believe that the technology will be open source and made accessible. However, I would focus on what would be needed for me to excel when all of those resources are available to everyone. So that's the answer that I provided. Next, we would like to look at the questions that have been uploaded on the forum website.
Hi, this is Youngju Hwang from Anu Elementary School in Daegu. I'm happy to have the opportunity to ask you a question. Nowadays, chatbots are usually used as an answering machine to customers that require information. I'm glad to hear that Professor Che developed a social chatbot, Imora, who is going to care for us in the future. I believe that Imora would be a good friend when we want to talk to somebody else. For example, when my mom, who lives alone, feels lonely and she wants to talk to somebody about her daily life, but no one else is available, then a chatbot would be beneficial for her. If the chatbot could remember information about my mom, this would make it feel more like human and more like a friend to her. Therefore, my question is this: is there a possibility in the future that a social chatbot will be able to remember previous conversations? Thank you.
예, 맞습니다. 이게 여기 황은주님이 질문하신 게 저희가
Actually, your question is very much relevant to my presentation I had made. And so the answer is yes. Yes, we are able to have conversational AI that can remember because it's an important factor. So Alexa Prize also included a section where we had the second conversation on top of the first conversation, and the evaluation was also made on whether in the second dialogue the chatbot remembered something from the first dialogue. So technologically it's quite possible, but the problem is that if you look at the conversations and if they were repetitive and they were very long, then how is the chatbot going to respond and react? So what we are designing, well, it's not developed yet, but we are designing that we have the graph representations of the previous dialogues. And then, because it becomes too large, we have to be selective. Some things have to be forgotten and some things have to be memorized. And so, humans also, you don't remember everything from your past. So in the case of humans, they do remember some things but forget others, and so we want to develop on that so that chatbots are also be able to remember certain things and be fed into the continuous dialogue. So that actually was a very good question, because one of the big audience in the Alexa Prize were the elderly, and so many people had actually approached the Alexa Prize because of the issue that you talked about.
Then lastly, would like to take one question from the live participants. I have chosen one question. So context-aware language intelligence, how far has it developed? I would like to know about the current status of context-aware language intelligence. That is quite a timely question. In the early stages of language models, it would look at context-independent. But now it has gone to contextual representation that is aware and it considers context to deliver language representations. But currently, the context that it is aware is only around 500 tokens of context. So when people in their daily lives, they make use of their world knowledge, and they also make use of the context. So it's not just an input token. They look at the world knowledge, they look at the context, and that has to be brought into the systems. And second of all, how the context is to be understood. Professor Benjo said earlier, AI is not better than a one-year-old. Now it's just filling in, guessing words, but in the future it has to be able to explore the world and learn information that it needs autonomously. So that is the direction that AI has to develop and further. And to look at what we have today and what we will have going forward, yes, we are in the really early rudimentary stages. Now that is the end of the question and answer session. I would like to extend my thanks to Professor Choi Jin Ho Choi. Thank you very much.
두 분 모두 진심으로 감사드리겠습니다.
Thank you very much to the two speakers. It was a very interesting session, and the two speakers had a very amicable dialogue, and for us as the audience, we were able to really interestingly listen to the conversation that had taken place. So, yes, the morning session has been quite filled up. And so I'd like to thank everyone for participating. And so I'd like to now announce the closing of the morning session. So it's about 12 o'clock here. So please enjoy your lunch. And we're going to start at 1 p.m. for the afternoon session. So see you again in the afternoon session at 1 o'clock. Thank you very much.
So we would like to begin the afternoon program of the Global AI Forum. I hope you enjoyed lunch. AI of a New Era is the overarching theme of this year's Global AI Forum. In the morning, we have listened to presentations and Q&As on language intelligence. We would like to move on to the second topic, which is brain-inspired artificial intelligence. We will have two presenters and have a Q&A. The first presenter will be giving a presentation on a cognitive neural architecture for autonomous learning. Professor Byung-tak Chang from Seoul National University is joining us online. Good afternoon, Professor.
Yeah, Professor Chang, are you there? Are you connected?
네, 안녕하세요.
Hello, good afternoon.
화면이 보이시나요?
So do you see me on the screen? Yes, we hear you well. And we also see your PowerPoint, so please go ahead.
안녕하세요.
Good
서울대학교
afternoon.
장병탁입니다.
I am Byung-tak Chang
제가 오늘
from Seoul National
말씀드릴
University.
내용은
So today I'm going to be talking about a cognitive neural architecture for autonomous
뇌인지
learning.
기반의 인공지능 기술에 관한
So
내용입니다. 특히
basically it's
인간
about
수준의
cognitive neural
AI에 도달하기
architecture
위해서
in order to be able to
사람이나 동물의
attain
뇌인지
human
구조를
level
닮은
AI. So
그러면서
we are
끊임없이
trying
학습할 수
to
있는
develop
이런
AI
인공지능
commensurate to the
기술이
cognitive
어떤
abilities of
것일까에
humans
관한
or animals
내용입니다.
and to be able to continuously learn.
지난 한 10년을
So
되돌아보면
if you look back on the past
인공지능이
decade,
급격하게
AI
발전하였습니다. 사실 인공지능 역사는
developed quite
70년이
rapidly.
되는데
Actually, the history goes
1950년대로
back to the
돌아갈 수 있기
1970s or even to the
지난
1950s.
10년 사이에
And so you can
급격하게
see that there
발전했다고
was
볼 수
great
있는데
development during the past
2011년
10
정도에
years.
보면 애플의
And in
시리가 나왔고 IBM 왓슨도
2011, you had
나왔고
Siri
그다음에
and
구글
Watson,
자율주행
and you also
자동차가
had the Google
등장하였습니다.
car that
그다음에
emerged.
2016년에
And then in
우리가 잘 아는
2016,
알파고가
you know
등장했고
that
그다음에
AlphaGo
스마트 스피커
were emerged, and
아마존
also
알렉사
the
이런
smart
것들이
speaker, also
등장했습니다.
called the
그리고
Alexa
아주
from Amazon
최근에는
came about.
거대
And
AI
recently,
그래서
now we have the
GPT-3와 같은
large-scale
거대 AI
AI.
플랫폼이 등장했습니다.
So that's GPT-3 from
그 전에
OpenAI.
AI 기술과 비교해봐서
So if you
최근
compare
AI가
to the
이렇게 급격하게 발전할 수
conventional
있었던
AI,
기반에는
the
머신러닝이라는
present
아니면
AI
딥러닝이라는 기술이
was able to develop quickly
중요한
because
역할을
it's
했습니다.
based on deep learning or
그래서
machine learning.
학습이라는 게
And so
사실 아주
basically
중요한 역할을
learning is a
해왔는데
very important
왜냐하면
aspect
예전에는
of
사람이
AI.
아는
Before,
지식을
it was
기계한테
merely about
프로그래밍
conveying or
해줘가지고
programming
기계를
the
똑똑하게
computer, the
만들려는
machine,
시도를 했는데
of the
그걸로
knowledge that
일부
humans
성공하기는
already
했지만
had, so making
한계가
computers
명확하다는 걸 알게
smarter.
됐고
But we
최근
found
이제 학습
limitations,
기반은
and now
사람의 지식을 직접
learning-based
기계한테 넣어주는 게 아니고
is not necessarily
기계가
based on the
스스로
input of
데이터로부터
knowledge from
학습하도록
humans.
만들고
We get
사람은
the
데이터를
machines to
공급해주는
learn
방식으로
by
기계를
itself,
똑똑하게
and the
만드는
humans are
방법입니다.
merely feeding
근데
in
이제
data
지금
from the outside.
현재 인공지능
But
내을
the
개발하기 위해서
current
학습
AI,
방법을 한번 오늘 우리가 좀 비판적으로
to be
살펴볼
further
텐데
developed, we need to look more into
원래
the learning
학습
process.
시스템이라는 게
And if you
뭔지를
look about
생각해보고
what
정말로
learning
인간
system
수준의
was
인공지능에 도달하기
initially,
위해서 과연 지금 우리가 하는 학습, 기계 학습이
we
과연
have to think
충분히
about
잘하고 있는가를 한번
and
되돌아볼
assess
것입니다. 그리고
whether the learning
만약에
system
그렇지
is
않다면
enough for us to
그거를
be
더
able to attain
발전시키기 위해서
human level
우리가 어떤
AI.
연구를 해야
If the
되는지
learning system is not
논의하겠습니다.
enough, then of
그래서
course we
학습의 정의를
will be
뒤로
able to
돌아서서
find
한번
out what
보자면
needs to be further
머신러닝이 아니고
developed.
일반적인 사람의 학습 같은
So,
거를 생각해 보면
first of all, let's
여기
think
있는
about how
정의입니다.
humans learn.
환경하고
So,
상호작용하면서
it's about
경험을
interacting with the
통해서
environment
데이터를
and
축적해가지고 그걸
experience,
기반으로
and it
모델이나
accumulates
지식을
data,
스스로
and then it is
축적해서
able
성능을
to
향상하는 기술
improve itself by
아니면 그게 이제
modeling
학습 시스템입니다.
or
근데
learning
이
further.
큰
So this is a
중요한
human
학습
learning
시스템이라는
system.
것 중에 지금
What's
현재 우리가
important
머신러닝,
here
딥러닝으로 구현해서 쓰고 있는 거는
which is the basis for deep learning and machine learning, is only a very small part. So we collect a lot of data and then we create a good model. So this is basically what AI is doing right now. And so for AI to develop further and to become human-level AI, it has to be able to go closer to the original definition of what we mean by a learning system. And so then we need a cognitive-based and human or animal brain-inspired learning abilities.
그렇지만 현재 머신러닝을 잠깐 한번 간단하게 살펴보자면
But then let's look at the existing machine learning for a minute. Usually we have the supervised learning, unsupervised learning, and autonomous learning. And they are quite different, but there is one common thread. So there is an input, and then you induce a certain output. It's just that there is a slight difference when it comes to the output. In the supervised learning, you induce a certain output. In the unsupervised learning, it does not really include a desired output. Reinforcement learning is slightly different. So it does a turn to the next situation, but the machine has to be able to predict based on what he had already experienced, can actually come up with what's going to happen in the future. And so in that sense, learning, like I said, is supervised or unsupervised or reinforced. And so when there are many deep neural systems with many layers, that's what we refer to when we talk about unsupervised or reinforcement. So you need many different layers, and so you have the objective function, and then you have the objective function that is given, and you try to optimize or minimize the error rate. So the more data that you have, so for example, if you are able to have data regarding the differentiation between cats and dogs, the machine will also be able to differentiate the two. So anyway, in a supervised learning environment, there is an input, and so the machine learns to find the differences. In the case of reinforcement learning, it doesn't look just at the current state, but it also looks at the future. And so it has a expectation and the values. So it goes one step forward, and then it makes a prediction, and then it makes a comparison or finds the difference between what's current. And so it tries to decrease the gap between the two and to minimize the gap between the two. And so machine learning and deep learning is basically about collecting large amount of data and then using a deep neural network, come up with an objective function, and this is basically a way of programming. And the data is used to create the objective function, and the machine learns to be able to minimize the differences. So recently, if you look at the deep learning, there have been a lot of research and there are excellent results that have been rendered. People have conversations, they create images, videos, and so they write, and so the process may be very complex, writing something or creating a picture, but nonetheless, the AI has developed to the level that it has now started to be able to do so as a result of deep learning. But then we have to be a little bit critical, though. So the question is, so we do an input and we predict the output. Is that everything to intelligence? So it can create texts, it can create videos, so it may seem very smart and intelligent, but so if you look at the definition of intelligence according to psychologists, you can see that AI is still lagging behind. So
역사적으로
If you
보자면
look at AI
초기에는 이제
historically,
고전적인
in the beginning
AI는
you had the conventional
논리나 기호
AI,
기반의
so it was more
방식으로
symbolic
지식을
and
표현해가지고 기계를 똑똑하게 만드는 방법을 30년 이상 연구했고
and it was
그게
based
주로
on different
규칙 기반의
rules,
추론을 잘하는 시스템입니다.
and it was
근데
able to
최근에 이제
reason.
머신러닝,
But
딥러닝 방식은
now we
그거와는
have
상당히
machine learning
다른
and deep
방법인데
learning that have
경험론적인
led
방법인데
to a more
데이터에
experiential
기반해가지고
or
기계가
empirical kind
스스로
of method.
복잡한
And so now
신경망
we have
구조
the
같은
modern
학습을
AI.
하는
It
이런
is
거를
based on a
잘합니다.
learning
근데
system.
방금 말씀드린
But
것처럼
like I
과연 그게 다
said, is
지능의
that
전부인가?
everything to
라고 보면
intelligence?
그렇지 않습니다.
That's not the case.
진짜로 지능이라는 거는
So real
환경하고
intelligence is
상호작용도
about
하면서
interacting
스스로
with the
뭔가를
environment and is
알아나가고 목표도
able
가지고 꾸준히
to
어디를
set a
향해서
goal
가고
and improve
행동도
itself
하면서
on its
인지
own.
능력을 갖는
And so
그런
it has to
에이전트나
have
로봇 같은
cognitive
형태의
abilities. So it has to be a robot or it has to be an agent. That's
지능체가
what we
우리가
mean
보통
when
생각하는
we say
인공지능의
it's
문제를
an
해결하는
actual
인공지능입니다.
AI that is able
오늘
to solve
벤조 교수님의
problems.
톡에서도
So
인간 수준의
Professor
AI를
Benjo
주제로
has
해서
talked
발표가
about
됐는데
also
정말로
a
인간
human level
수준의 AI로
AI.
가려면은
So if we
이런
were to
새로운
have human level
인공지능 기술이
AI,
연구돼야 되고
we need
특히
new
그
AI
관점에서 봤을 때
technology. And from that
머신러닝이
kind of
지금보다는
perspective,
훨씬 더
machine learning
발전해야 될
compared to
필요가
now
있습니다.
has to evolve
특히
much
지금까지
further.
기술은 특히
Until
머신러닝도
now, the
포함해서
technology,
갇힌 세계에서만
including machine
동작하는
learning,
이런
was
알고리즘들이었는데
operating in a closed
실세계로
world.
나가면
But if
열린
you go
세계가
into the
됩니다.
real
그러면
world, it's
불확실성이
an
높아지고
open world where there are
항상
many
아무리 학습을 많이 해도
unpredictabilities.
미리
And even
하더라도
if there has been a
현장에
lot
가면
of learning,
새로운
if you're
상황이
there on the
발생하고
ground in the
그러면
real
현장에서
world, new
학습할 수 있는
situations can
능력이
come about.
중요해집니다.
So
오픈 월드에
the machine has
쓰일 수
to be
있어야 되고.
able to
그래서
adapt and learn
어떻게
in the
보면
real world right
머신
then and there.
러닝만 연구할 게
So
아니고
it's not just about
앞으로는
researching
학습
machine
러너
learning.
자체가 스스로
The
뭔가를
learner
찾아나가는
has to be
학습을
able
하는
to
학습하는 기계로
seek.
발전을 하는
It
게
has to be a learning
중요할 것
machine, not
같습니다.
just the machine learning.
그래서 진짜 지능이라는
So
거
that's
아까
why
잠깐 다시
I have
말씀드렸지만
said
과연 뭔가를
we have to
보면
move from the
지능이라는
machine
거는
learning to learning machine.
뭔가
So what
불확실성에서
is
문제를
really the
해결하는
intelligence?
능력이고 뭔가
Intelligence is the
목표에
capability
도달하려고
to
합니다.
solve problems under
예를 들면
uncertainties,
이런
to
로봇을
achieve a
만드는
goal.
궁극적인 인공지능의 목표라고 볼 수 있습니다. 이게 지금 인공지능 학회에서 개최하는 로봇컵 대회에서 저희
So this
서울대에서
is a
우승할 때
competition that we had, and
찍었던 장면인데
it was the Seoul National University team had participated. So this robot is used at their home. It goes around the house.
그리고 심사위원의 말을 알아들어가지고
And it is able to understand what the jurors say, and so it moves around at the
미션을
order of
제대로
the
수행을
jurors.
해야 되고 그러려면은 공간에서 자율주행을 하고 장애물을 피해서 다시 다른 심사위원한테 가서 대답을 하고 돌아와야 됩니다.
안에 그런 거 없어. 완전 딱 포인트야. 익색 포인트를 봐야 돼? 지금 좀 안 멈춰? 어떻게 하지? 타임아웃 있어? 일단 보자. 타임아웃.
그래서 언어 능력, 시각 능력 이게 로봇이 AI가 미리 학습한 공간의 지도입니다.
And so the robot is there and learning about the environment,
언어로 사람하고 소통을 하고
and it is able to use language to communicate with
시각
people,
능력을 가지고 주변 환경을 이해하고
and it's able to understand the environment around it.
또 단순히 입력 주면 출력만 매핑하는
So once
물체만
again,
인식하고 끝나는
it's not just about giving output
넘어서
after an input has been made.
단계적으로 한
So
단계 가고 다음
sequentially,
단계에서 궁극적으로
it
어떤 문제를
does an
해결하는
action, and
그런 게
sequentially it solves a
지능의
problem.
본질이고
So this is the
그렇게
essence of what we
하려면
mean by
학습이라는 거는 왜
intelligence,
필요한가
and
보면
we need learning to
열린
make that
세계에서
possible,
현실
because like I
세계에서
said, in the open real
현장에서
world,
문제를 해결하려고 할 때 부딪히는 불확실성을
there are so many
줄여주는 데 학습이
uncertainties,
필요합니다. 왜냐하면
and
모든
so
가능성을
you
다
need
프로그램할 수 없기
learning
때문에 미리
to be
있을 수 있는
able to solve new
가능성들에 대해서
problems
경험을 미리
and to be able
축적해가지고
to
데이터로
overcome the
학습을 해주는 건데
unpredictable
그럼에도 불구하고
situations,
현장에 가면
because you
불확실성이
can't
있기
teach
때문에
it to do everything. You can't teach
머신러닝이
everything. So that is
끊임없이
why the
현장에
machine
가서
learning
계속 스스로 학습할 수 있는
has to be able
능력이
to learn on its
근본적으로
own
중요합니다. 그게
on the
없으면은
ground. according to the environment around it. Otherwise, if you're not able to overcome that particular issue, then there will be no further development for AI. So once again, the AI or the machine has to react to the environment, and it also has to have cognitive abilities. It also has to be able to predict what's going to happen in the future.
근데 지금 이제 머신러닝 어프로치를 현재 머신러닝 어프로치를 인공지능을 개발하기 위해서
So
보면은 여러 가지
there are many
한계가
different
있는데
issues and
첫째로
limitations in the current
아까 잠깐
ML approach to
말씀드렸지만
AI.
정리하자면
Like I
데이터가
said,
내부에서
data
그냥
has to be fed externally, and this is just a passive process. The agent
보통은 사람은
itself
학습을 하죠. 스스로 뭔가를 찾아서
is not able to learn on its own yet, just as humans are able to learn on our own.
실생의 환경에서
And models are not
grounding이 되어
really
있지
grounded
않습니다.
in the
그러니까
real
좀
world.
동떨어져 있는
And so the
설계준이라는
models
성격이
are
강하고
somewhat
그다음 무엇보다도
different from
끊임없이
what's on the
학습을
real
하지
world,
못한다는
and it is not
그다음에
continuously
환경이
learning, and the
고정돼 있다고
environment is
보는데
assumed to be
사실은
stationary.
실제
But in
환경은
fact, the
유동적이에요.
real stationary is very
스테이셔너리하지
dynamic.
않다고
It's
하는데
not
기술적으로.
stationary.
그래서 변화하는 환경
And so there is a constant change to the environment which the machine has to adapt to, which cannot. And that is all because the assumption is a closed world. The AlphaGo was possible precisely because it was operating within a closed world. So once again, of course, it was very intelligent, but it was in a closed world. If it were in an open world, I think there would have been many issues. So the current machine learning approach is that it is not able to adapt to the changing environment, it cannot self-improve over time, and it cannot acquire new knowledge beyond what's being given, and thus it cannot solve the new problems in the real world. So this is the current situation
그래서
of machine
머신러닝 자체를
learning.
한번 변화시킬
So
필요가
let's
있고
upgrade. We need to upgrade the machine learning to learning
얘기는
machine.
뭐냐면은
So what I mean by that
데이터가
is that,
주어지면
okay,
그거를
the data
수동적으로
is inputted,
approximation만 해가지고 모델을
but
만드는
we
것이
shouldn't just
아니고
make a model
그거는
by
머신러닝이죠.
approximation of
지금
data.
하는
That's the
그걸
current
넘어서
mode
러닝
of
머신이 된다는 건 학습을 하기
machine
위해서
learning.
끊임없이
So if you want
문제를
to
풀려고
strive
하기 위해서
towards a
모델을
learning machine,
액티브하게
the model has to be
구성해 나가는
actively
만들어 나가는 그런
structured,
학습 기회가 되도록
and it has to
해야
be
이게
able to
궁극적으로 인간
continuously
수준의 AI에
learn.
도달할 수 있는 학습 방법이 될 걸로 보입니다.
It has to be able to
그래서
gather new
데이터를
data.
주면 모델을 만드는 게 기존의
So the
머신러닝이라면
conventional ML is about making an output or a model based on the inputted data, but the new learning machine is about using the input to create a model, but then using the model to create further data. So it goes the other way. So from the model, it has to be able to create data and to be able to understand the environment around it. So this is what we mean by the learning machine.
이게 기술적으로도 점점 가능한 이유는
And so
최근에
this has
센서도
become
발전하고
technologically
액추에이터도 발전하고
possible because we have
그다음에
sensors and
기계가 스스로
actuators,
시뮬레이션도
and
할
we
수
now
있습니다.
also
컴퓨터
have
파워가
simulators
좋아져서.
because
센서
we have the
액추에이터 같은
computing
경우는 물론
ability.
로봇 형태면은
And of
명확히
course,
물리적인 센서 액추에이터가 있어서
in the case
더
of
명확하게
robots, you would have the physical sensors,
스마트폰이어도 사실은
but even
센서
smartphones
액추에이터가
also
있습니다.
have
스마트폰에도
sensors and
다양한 센서가
actuators.
달려서 주변
There are many
환경을 인식할 수
smartphones
있고
that is able to
그다음에
recognize the
일부
environment on our
행동, 그러니까
smartphones.
말도 일종의
And
행동입니다.
so
그런 면에서 보면
language is also an action
학습을 해나가는
as well.
세상을 알아가는
So
게 필요합니다.
there
그래서
are
그런
actuators and simulators and sensors that are able to perceive that kind of language. And so then we can call that a universal learning machine. So a universal learning machine, without any human intervention, is able to improve its performance continually, and it's a fully autonomous learning machine.
우리가 지금 하는 모든 컴퓨터의 그 수학적인 기반이 된 것처럼 유니버설 튜링 머신이 지금 러닝 머신 형태로 유니버설
The universal Turing machine would form the basis for the computers that we use currently, but we can also think about the universal learning machine. The biggest important feature is that it is able to recursively self-improve. This is the most important part. So some of the elements of the ULM would be that it's able to select a model, and it can also automate a design. It can can self-teach and also be able to acquire data, it should also be able to self-reflect and thereby be able to set or adapt its objective function. And it has to be able to change its objective function depending on its environment. And then ULM is a prerequisite to achieving human-level general intelligence. So how are we going to make this? What kind of architecture do we need?
그동안 뇌과학 연구, 신경과학, 인지과학 연구에서 많은 힌트를 얻을 수
And we
있고
were able
그거에
to get a
기반하고
lot
그동안
of
인공지능을
hints
연구해온
and a lot of
머신러닝을
clues
연구해온
from
이런 수학적인 기반하고
neurosciences,
결합해서 우리가 이런
and we were
모델을
able
하나
to
생각해
use the
볼 수 있습니다.
mathematical
저희가 이게 국가 연구 과제
logic, and so we
베이비 마인드라는 과제에서
did a project called Baby
주제로
Mind.
연구를
It's
해요.
a
거기
government-funded
모델입니다.
project, and then we were able to come up with the Cognia system, which is the cognitive neural architecture for autonomous learning. So Cognia is a universal learning machine architecture. So just think of it as a very rough sketch of an ULM architecture. So the machine goes out into the world is continuously changing, and the AI agent has to perceive the world and also have to be able to react to it, and under some circumstances, it's not just about an internal reaction leading to internal simulation, but if it has a sensor or actuator, then it will be able to learn by doing. And so it won't also just stop at acting. It will be able to look and then self-reflect and self-assess and then improve itself. So if it has sensors and actuators, from the learning perspective, it's a great evolution and a great leap forward in knowledge acquisition. Because humans, if you lift an object, you know whether it's light or heavy, and that also goes for the cognia. So basically, it has a self-teaching ability. It has to be able to evaluate oneself and to be able to learn and teach itself, and then it goes beyond. It has to self-reflect and be able to think about which direction it should learn in. Humans in the human brain, this kind of process is very natural. So if you think of this as a brain, there is a neural network and there are neurons, and they are recursively connected. And so what it had done before is reflected on what it does now. And what it does now is reflected in what it does in the future, because the present is already recursively connected to what's going to happen in the future. And so it's reflected in the future action. And what it had thought in the past about the future would also be reflected in the present. And so it's sort of like time travel. So anyway, internal simulation is possible. This is sort of like imagination. It's like a thought. And so this internal simulation is there, and you can formulate it. Of course, it's not completely final, but it can nonetheless perceive and generate thoughts, and it is able to check. And that leads us to a generative model.
그다음에 reward나 value라는 건 미래에 좋은 정도입니다. 현재 상태에서 미래를
it is able to predict the future, and it is able to value as well. Value in the sense that it is able to assess what actions would bring good results or not. And it is also able to observe itself, meaning that it can rectify itself and continue learning. And after self-learning, if necessary, the objective function can also once again be changed. So the research question is this.
24시간
Can we
끊임없이
build a machine that
학습을 하는
learns
기계를 우리가 만들 수
24/7
있을까?
continually
지금
without any
보면은
human
많은
intervention?
사람들이 머신러닝을 연구하고 있지만
Many people are into
대부분은
researching
데이터 누가
AI,
주면은
but it's
모아가지고
really about
그것만
collecting a lot of
approximation해서
data,
현장에
doing the
적용하고
approximation, and then
보통은
adapt
끝입니다.
it, and then that's
계속
it.
끊임없이 이 순간에도 학습하고 있는 로봇이 아직
So
별로
there
존재하지 않습니다.
is
그래서
no
끊임없이
robot right
24시간
now that is able
학습할
to
수 있는
learn
기계를
on
어떻게
its own
만들어 볼 수 있을까?
24/7.
그리고
So how are we going to make it
가급적이면은
possible?
인간의
And how are we going
개입이
to
없이
do it without any
예를
kind of
들면
human
우리가 연구하고
intervention?
있는 환경이
So,
주로 가정
for
환경에서
example, in the home,
하는 이런
you may think
로봇입니다.
about a robot that does the
아이디보이라는
housework.
또 로봇컵 대회에서 나가서 저희가 시연했던 건데
So I remember I
예를
showed
들면,
you the robot that we had
물건을
worked on.
사온다든지 쇼핑을
We
하는
went
거죠.
on a contest, and the robot can go shopping.
그다음에 쓰레기통을
It
치운다든지
can
쓰레기를
throw
치운다든지
away the rubbish bin.
쓰레기를 치우려면은 많은
And it
생각을
does a
해야
clean.
됩니다.
It does a
계획도
lot
해야
of
되고
cleaning.
단순히 물체만
Actually,
인식하고
cleaning is not just about
행동 하나만
perceiving
선택하는
objects.
지금
It has
뒷면이 그런 걸
to
잘하는데
be able
그거
to
하나만
perform very
가지고 이
complex
문제가 해결되지
tasks
않습니다.
about
궁극적으로 쓰레기통을
categorizing
치워야
and
되고 어디다 치우는 게
planning.
좋을지
It has to
어디로
think
갖다
where
주는 게
it's
좋을지
going
그걸
to
어떻게
take the
잡을 수
trash,
있는지 계획을
how
해야
it's
됩니다.
going to grab the
이런
trash.
부분들이
It has to
아직
be able to
머신러닝이
predict and plan.
끊임없이 스스로
So
학습하면서
this
하지 않으면
It's only
해내기 아직
possible
어려운
if the
부분인데요.
machine is to learn continuously on its own.
지금 여기 보여드리는 거는 사실은 다 완전히 학습을 통해서 한 것만은 아니고
So this is
아직은
not all based on
상당
self-learning. A lot of the input was done by humans. It was
사람이
coded,
개입해가지고
and so it had
프로그래밍을
human intervention. There was
부분이 상당히
programming.
많고, 자, 앞서 말씀드린
And
완전
as I had
자율학습을
mentioned,
통해서
it's not
end-to-end
completely
learning으로
autonomous in
로봇이
learning.
시행착오를 하면서 그거를 시행착오했다는 거
The
알아보고
ideal
학습할 수
situation for
있도록
it to be
만드는
able
게
to
앞으로
self-learn
이제 해야 되는
and to be able to go through a trial and error and learn from that on its own. So that's
그런
the
연구의
future
약간 일례로 한번 잠깐
research
말씀을 드리면
direction.
시간이 지금
So let me just give you an example. I know I'm running out of time, but
바닥에 떨어져 있는
so on the floor there are toys, and the robot is going to pick it up and is going to put it in a box.
임무를 수행하는데 어떤 경우에는 잘
In some
잡아가지고
cases,
박스에
the
제대로
robot
넣기도
does grab
하지만
it and put it in the
지금처럼
box, but sometimes the robot
이 일을 하다 보면 어떤 경우에는 놓여 있는 장난감이
sometimes
잘 잡지를 못해가지고
it's not
잡지를
able to grab the
못했는데도
toy,
로봇이 그거를
but still
모르고 못
it
잡은지도
doesn't
모르고
realize that it
박스까지
was not
움직여가지고
able to
뭔가를
grab the
떨어뜨리려고
toy,
하는
and
이런
then it moves the box and
이상한
drops
내지는 바보 같은 행동을 합니다.
nothing in the
이걸
box.
어떻게
So
스스로
it's
학습하게 만들 수 있을까?
a bit of a
그게
stupid
우리가
action. So how are we going to
교정을 한
make it
거고,
learn?
여기
So we
지금
were
비디오가
able
잘
to
안 보이실 수
correct
있다고
it. Actually, the
들었는데
video is not playing right
보시면은
now, but
사실은
anyway,
스스로 봐가지고 눈이 있기 때문에
it has
손을
eyes,
보고 거기
so
물건이
it is
박혀
able to
있지
see
않으면은
its hand, and if it
쓸데없는 짓을
sees
하지
that
않고
there is no
바로
toy
다시
in its hand,
해가지고
then it will
다시
try once again
그래서
to
이렇게
grab the
하면은
toy.
쓸데없는 일을 하지 않고
And
효율적으로
so it won't
일을 하기 때문에 물건 정리 정돈을
behave
훨씬 더 빨리 많이
ridiculously,
할 수 있겠죠.
which means that they'll become
지금
more
보시는
efficient to
비디오는
be able to perform more tasks.
정리 정돈이 훨씬 더 빨리 이루어질 수
And
있다는
so
것을 알 수 있고
basically
이 방식은
the
스스로
video
그러니까
that I was
로봇이
going to
레이블을
play
스스로
basically
답니다.
shows that if
물건이
we're
잡혀
able to
있는
attain
상태인지 아닌
self-learning, then the
상태인지.
cleanup
그걸 어떻게
process will be done much better.
학습했느냐조차도 다시 학습을 하는데 일부는 학습이 돼야 되고 학습한 걸 가지고 다시 학습을
And
하고
so the
이런
learning becomes the
대비적으로
basis for another learning.
연결되는 게
So
중요한
everything is recursively linked.
그래서
This is the main principle.
카메라를 가지고도 보고
So
소리도
it can
듣고
have
압력
sensors
센서도 가지고 다양하게
to
해서
feel the pressure. It
손에
can
내가
have
물건을 잡고
eyes.
있는지 떨어뜨렸는지
It can
이거를
perceive whether it's
예측을 하고
dropped
그다음에
something or whether
관측을
it's
해가지고
holding an
스스로
object in
그걸
its
판단해서
hand.
만약에 떨어뜨린 게
And it
확실하면은
can make a decision
다시
based
잡는 거죠.
on what it has perceived.
그래서 중요한 거는 스스로
What's important is
한
that
잘못에 대해서 스스로
the
판단을
agents
할
are
수 있는
able
능력이
to
있는
assess
그리고
on their
그걸
own
통해서 또 다시 새로운
what
걸
errors there have
발견합니다.
been. and then learn new things based on that. If we're able to apply this kind of self-learning, then we'll be able to adapt it and apply it to many different areas. So actually, the video here is showing a robot working in a logistics center. So it is putting something in a box and wrapping it and packaging it and sending it to its customers. And nowadays, the workforce is lacking, and so sometimes these robots are working instead. And so for these robots to be able to work autonomously and efficiently, they have to have a more autonomous machine learning process.
So 마지막으로
last
지금
but
이런
not
거를
least,
생각해 볼 때 그러면 앞으로 인공지능이 어떤 단계로 발전해 나갈 수 있느냐를 한번
to what
생각해
level can AI develop
보겠습니다.
towards?
인공지능을
So
인공지능의 수준을
I would
6
say
단계로
there are
제가
6
여기서
levels
한번
of
나눠봤는데요.
AI.
레벨 1은
Level
이미
1
지나간
is
인공지능입니다.
AI
예전의
of the
인공지능,
past.
고전적인 인공지능에
It's a
산
conventional
것처럼
AI,
사람의 지식을 규칙
and it's
기반으로
based
기계한테 잘
on
집어넣어서 기계가
human
사람처럼
experience, which
똑똑하게
is fed
뭔가를
into the
수행하도록 하는
machine
전문가
in a
시스템
set of
만드는
rules.
이런 방식의
It's an
인공지능이
expert
레벨
system,
1이라고
so that's level
본다면요.
1.
지금은 레벨
Level
2 정도에
2,
와 있다고
I
볼
think
수
we are
있습니다.
at about level
딥러닝을
2
이용해서
usually. So we
많은
use deep
데이터를
learning to
확보해서
collect a lot of
딥러닝
data,
모델을 주고
and then we
컴퓨터를
feed it into
제공해주면
deep learning
기계가
model,
GPT-3 같은
and
거죠. 모델을 자동으로
just like the
최적화해가지고
GPT-3,
상당히
the
어렵다고
computer
생각하는
comes up
것조차
with the
데이터를
appropriate
어마어마하게
model,
주면 잘 낼 수 있습니다.
and so
상당히
even if it
자동으로
seems
설계까지
impossible,
하는
if you feed it enough
그렇지만 아직
data, it'll be
데이터를
able to
스스로
do
모으지는
so.
못합니다.
But
그게
it
바로
cannot
레벨 3라고 볼 수
collect
있고
data on
레벨
its own.
3는
Once it
스스로
is able
데이터를
to collect data on its own,
만들어내고
then you reach level
확보해가지고
3. This is a
세상을
self-teaching
알아가는
system.
스스로 알아가면서
It's basically
학습을
about
해나가는
learning the
self-teaching
environment
이런
around
시스템이
it, and
다음
it
단계라고 볼 수
self-teaches.
있고 아까 universal learning machine으로
So then
가려면
level
이게
4
중요한
is a
한 단계가 될 것
universal
같습니다.
level machine.
그 다음 단계는 더
Universal
나아가가지고
learning
스스로
machine, excuse
자기가 한
me.
거에 대해서 평가를 하고
And so
자기 반성을 해가지고 더 좋은
in level
방향을
3,
목표까지 수정하는 이런
excuse me, in level 4,
self-reflective한 시스템.
it has to
4라고
be
볼 수
able
있고
to set its own
이게
goals and
다 된다면 아까
set
얘기한
its
universal
own
learning model
functions,
형태로 가는
objective
초안이 될 수
functions.
있고
And so this will
궁극적으로는
be the
다음으로
basis for a
가는 인간
universal
수준의 AI에
learning
도달할 수도
machine.
있을 것입니다. 그다음에 만약에 그게 레벨 5라고
And it's a
본다면 인간
recursively
수준의 AI에
self-improving
도달한다면
system.
사실은
And
인간
level
수준을
5 would
넘는
be the
인공지능에
human
도달하는 것은 상당히
level
빨리 도달할 가능성이
AI.
높습니다.
So
왜냐하면
once we go
이미
past
기계가
level 4, then
인간보다
actually
잘하는 게
reaching
많이
level
있습니다.
5
용량도
would not be
어마어마하게
so
크고
difficult.
빠르고 정확하고
Already the capacity
심지어는
will
기억
have been
능력도
quite
정확하게
large.
복제할 수가 있습니다.
And
사람은 평생 공부한 거를 자식에게도 그대로 복제해서 넘겨줄
and
수가
you'll be able to
근데
copy
기계는
and
공부한 거를
deliver
다른
everything.
기계한테
So
정확하게 복제해 줄 수 있기
humans are
때문에
unable to do that. You
슈퍼지능으로
cannot
가면
learn
상당히 빨리
everything
변할
and then
가능성이
give everything that you have learned to your child, for example.
이
It doesn't
부분을
happen that way.
생각하고 그래서 마지막으로 보면
But level 5 AI will be able to do so. The level 6 AI outperforms
이제
humans.
목표가 명확히 주어지고 데이터가 주어지면
So
그 문제를 푸는 방법 내지는 알고리즘을 자동으로 기계가 설계해서 문제를 풀 수
by
있다는
this
것까지는 우리가 할
stage,
수
the
있고
algorithms will be
그렇지만
able to set by
닫힌
the
세계가 아니고
machine.
열린 세계에 나가고 물리적인 세계에
But
나가면
once again, it may seem possible in a closed world, but when it goes out into the open world, it has to be able to learn on its own because it faces new situation all the time. There are so many unpredictabilities. And so once we have been able to attain that, then we will be at the level of human level AI. So this will be it for my presentation. Thank you very much. Thank you very much, Professor, for your presentation. So human level AI, I think we're almost there, perhaps. Thank you very much for your interesting presentation. So you've been talking about self-learning of machine learning. So rather than a machine learning that just does something, hopefully we'll be able to witness the emergence of machine learning and AI that is able to understand humans, who is able to be flexible and understand the intentions of humans. Now let's go into the second presenter.
Under the brain-inspired artificial intelligence topic, we have a speaker from overseas. So learning and using structured models and intelligent robots will be the overarching topic for this presentation that will be given by Professor Leslie P. Kelbling from Massachusetts Institute of Technology. It's very early in the morning or very late in the night in Cambridge, but we will welcome Professor Leslie Kelbling.
Hello, thank you very much for inviting me. I'm really honored to have this opportunity to speak to you. And I'm interested, I think, in many of the same things as Byung-tak in a way, although unfortunately I couldn't understand his talk, so I'll need a translation. So I'm interested in building intelligent robots, and fundamentally, actually, in the context of MIT's program for the Quest for Intelligence, we were thinking about how to perceive, understand, and manipulate the physical world. So we think that we can maybe engineer smarter robots by understanding natural intelligence, and actually understand natural intelligence better by testing hypotheses in robots. So we're trying to work both ways with people across computer science and cognitive science. So my fundamental goal is to understand the computational mechanisms that you need in order to make a general purpose intelligent robot. And one example I like to think about is imagine making a robot that could make tea in any kitchen, right? The same robot could go to anybody's house in the whole world, really, and make tea. It would have to figure out how to make the water hot, where to find the tea, and so on. And I would like that very same robot to do any job in a house. So I'm very much interested in generality and robustness. So I like to look at this example. I promise it's not my kitchen, but it's a motivating example. So what if this robot had to do something in this kitchen? What makes this problem difficult? And I would say one of the things, there's several things that make it hard. One thing is that the state space is huge. The possible arrangements of objects in the kitchen and the possible ways that things could be are very big, and that makes the problem complicated. The horizon is very, very long. The number of steps the robot will have to take is very long, and most of our approaches to planning and reasoning suffer very badly when the horizon is long. So we have to worry about that. And there's a substantial amount of uncertainty. The robot doesn't understand what's going on in its world. It might have some sensors that can give it some images of what it can see, but it doesn't know what's inside the oven or what's inside this bowl. So the combination of large state spaces, long horizons, and lots of uncertainty make problems like this very difficult. And it's not just cleaning kitchens. We might apply these same ideas in disaster recovery or construction and so on. So I want to talk about different strategies for engineering intelligent systems. And I'm going to lay out a set of axes with the 2 dimensions. So one dimension is, in some sense, the complexity of the solution. So you might imagine a special robot that's designed just to solve a single problem versus a very general purpose robot. And you might also think about how much the engineer knows in advance about the problem that the robot is going to have to solve. So classical engineering is kind of down here in the bottom corner. We know what the robot is supposed to do very well, and we design a particular solution to just that problem. So that's kind of classic engineering. I would say that classical AI approaches, in some sense, have attempted to have a broad competence, but they have to know in advance, the engineer has to know in advance everything about the domain that the robot's going to be in. Recently, there's been a lot of enthusiasm about machine learning approaches and reinforcement learning and so on. And those address the problem where the engineer doesn't know what program to write. The engineer doesn't know how to directly solve the problem, so the engineer uses machine learning to solve the problem. But currently, the machine learning approaches we have mostly address a very narrow problem. And what I really want to do is figure out how to combine learning and kind of knowledge and understanding to solve very complicated problems in very robustly and very kind of broad domains. So, so the approach that we're taking is to imagine, as you know, the title I started out with was doing for robots what nature did for us. Humans are born with a lot of built-in structure already. Brains are not just all the same. They have some regions that are better at doing some kinds of processing than others. And so our strategy is to think about building in some general representation and inference mechanisms like convolution, or that the robot has kinematics or ways of planning and so on. So build in some basic algorithms and then build, for right now, to start with, build models by hand to see what we can do. So this is the first step in a research program that I've been kind of pursuing, where we hand built a solution. So in particular, we spent a lot of time thinking about uncertainty and about how the robot would have to reason about its own uncertainty in the world by estimating what's going on in the world around it and then selecting actions. We have a state estimator that's very broad, that reasons about the objects in its world, that reasons about what space is free and occupied and so on. And what critically, it knows what it does and doesn't know about the world. We're also used hierarchy to handle the problem of a very long horizon. So with hierarchy, you can make a plan at an abstract level. I like to think about traveling. I haven't traveled lately, but someday I'll travel to Korea, and I might make a plan, an abstract plan that involves first going to the airport at Boston and then flying and then taking a taxi once I get there. And then I can take the first step of that plan and plan in more detail and take the first step of that plan in more detail. So hierarchy is a good way to deal with problems where there's long horizon. So we put all these pieces together and made a robot. And let me say before I show you the rest of this movie, any individual thing that this robot does is not very exciting. And some good undergraduates could spend some time and get the robot to do that thing. But what's important about what this robot does is that it's completely general purpose. It's reasoning about geometry, about kinematics, about what things are in the way and what it has to do to solve the problems. And so basically the same code is going to be solving all these problems. In this first example, we asked it to put the blue box down here where the can is. And so it looked and it saw the can in the way. Oops, sorry. And it's about to move the can. And so that it can put the blue box where it goes. In the next example, we asked it to move the green box to the corner of the table. It picked up the orange box to move it out of the way. It pushed the green box because it's too big to pick up. It knows its pushing is unreliable. So after it pushes, it reasons that it should look and see if it worked. And it keeps pushing till it gets there. Here we asked it to go out of the lab. And it looked and it saw these chairs were in its way. It moved one chair out of the way. It grabbed the other chair and just brought it with it out of the room. We didn't ask it to do that, but it did it anyway. Here we asked it to put a full oil bottle on the other table. It picks up the oil bottles to see which one is heavier and moves that one over there. So what's important about that is that the robot is pretty general purpose. And it has the same code is really solving all these problems. But in that video that I showed you, everything is hand coded. There's no machine learning involved at all. And the hand coding of these models is difficult. So what we've been doing more recently is keeping the same underlying algorithmic structure, but trying to understand how we can learn the models that get used by the methods in that structure. So now I'm going to talk about some different pieces of learning that we've been doing that fit into this general architecture. So one joke I like to think about is reinforcement learning, right? So reinforcement learning is very popular. I used to work on reinforcement learning, but that can't be the way a robot learns to do things, right? You don't want a robot doing reinforcement learning in your kitchen, right? It should learn about physics somewhere else, not in my house. So what we're going to talk about now is ways of, so I just showed you hierarchical planning. There's reinforcement learning over here. And what we're working on is learning compositional models, right? So learning small pieces that can be put together to make big and more complicated systems, learning them incrementally so that a robot that's a little bit smart can gather more information and learn to be more effective in its world. So we're operating using an architecture. The details of this particular architecture don't matter too much. But again, what's important is that the blue boxes correspond to code or prior structure, basic generic algorithms. And these yellow things are models that we hope to learn from experience and that will plug into this architecture and then make the robot do stuff. So one example is learning perception and thinking about how learning perceptual abilities can help our robot. So I'm going to talk about a project that we've been doing we call it MOM. It stands for Manipulation with Zero Models. And what makes it different from a lot of manipulation projects is that it does not assume in advance anything about the objects it's going to see, except that they're rigid. Right? So right now we're only working with rigid objects, but we're working with objects that the robot hasn't seen before. And we're using perceptual models, pre-trained perceptual models to understand what's going on. So a method for doing segmentation, a method for predicting how to grasp, a method for doing point cloud completion, and so on. And using these methods, we can make a closed loop policy where there's a very general purpose planner. So this general purpose planner takes a goal as input. So for example, this goal is that there should be some yellow object that's on the mat. So we can give goals to our system in something like first order logic. It takes the perception and the goal, and it uses a general purpose planner to decide what actions to take in order to achieve that goal. So we can watch some examples. Here's a case where we told it to put all the objects on the blue mat, but it couldn't see all the objects. So at first it just saw the box and put the box there. Then it realized there were these other objects down here. So it moved the box out of the way so that it could put these objects back there and then go get the box and put it where it needs to go. What's important here is that we never told it what actions to take and in what order. It's just using the planner to do this job. So here's another example. In this one, it's supposed to put the yellow bottle on the mat. So it's moving some things out of the way so that it can get the yellow bottle. It's also in a replanning loop. So if it ever misses, it just tries again. Here's one where it's trying to put all the objects of the same color in the bowls. That's a close color. Again, what's important, the particular thing that the robot's doing is not important, but what's important is that it's reasonably general. This is my favorite one. It thinks there's one object. It goes to pick it up. It comes apart. It says, okay, well, maybe there's more than one object. Tries again. Oh, now it's 3 objects, but okay. And so it's just going to keep working until it gets all 3 objects onto the mat. So yeah, robot's working. All right. And it runs on different robots. It doesn't really matter. And it runs on lots of tasks. Okay. So that was an example of learning perception, right? We fixed the planner, but we learned perception so that the robot would work more effectively. Now what we're going to do is consider what we would need to do to give this robot a new ability. And the most important part of this is that we're going to start with a robot that's already somewhat competent. So imagine the robot already knows what you saw. It knows how to pick things up and put them down. But we want it to learn something new. And the example that we're thinking is, let's say, pouring. So lots of people work on learning a particular pouring skill, but what they don't do is figure out how to take the new skill and integrate it with the other stuff that the robot already knows how to do. So we're going to focus on the problem of, if a robot learns to do something locally, how can we add that to the robot's whole set of things the robot can do so that it can work more effectively? So here's an example of pouring. So the robot's trying to pour stuff from one thing into another. And you can look at this situation and see that it's parameterized by a bunch of things, a relative transformation between the cups and the sizes of the cups and some parameters in the controller. And what we do is we can describe a kind of symbolic almost planning rule, a reasoning causal rule that says, if you have some source container with a liquid in it and you're holding it in a certain way relative to the thing that you're pouring into, then if you do the pour action, you'll get the result you want, which is that there's liquid in the cup. So the thing is that there are a bunch of continuous parameters. There are all these continuous parameter values that describe the situation, and we have to learn, in some sense, a condition under which this pouring will succeed. So we want to learn a constraint or a classifier really on pouring situations that will be successful. And we do this by using Gaussian process regression. It doesn't really matter. It takes a bunch of examples. But one thing that's important is that training on a real robot is expensive. So here we have the robot trying to learn to pour and to scoop. And we really had to pick a lot of peas up off the floor, right? So every single piece of experience is expensive here. So we use some Gaussian process regression strategies to do active learning, to pick which examples to try so that we can minimize the number of beads we have to pick up off the floor. There's some details about making sure that the sampling that we do is robust. So we don't learn a single way for pouring, we learn a whole set of possible ways of pouring so that later on when we want to plan to pour, if there's something in the way, we can pour backwards and it'll still work. So what we can do now is we take the robot's initial ability to do pick and place, and now we add some operators that we learned, like we learned to do pouring, and we learned to do pushing objects around. And now the robot can use what it used to know, plus the new operations to achieve new goals. So in these examples, we put objects on the table in any way, and we give it general goals, like we want to have stuff in the bowl and the bowl on the tray. And the planner figures out what order to do things in and whether it needs to move stuff out of the way. So here, you know, I don't know, we told it to put stuff in the white bowl while the white bowl was on top of the purple thing, and it figured out, again, what to do. We'll look at one more example. This one is nice. The robot needs to put stuff in the red bowl, but the red bowl is too far away. So it slides the red bowl over into its workspace so that it can pour something into it. So, okay. I'm going to give one more example of things that we can learn. So we talked about learning new perception modules. And what you just saw was basically learning new transition models, right? We learned something about how pouring changes the world. And we just learned the pouring and we added it, and then the robot could do what it could do before plus pouring. But one important kind of learning is search control. So if you think about AlphaZero, right? AlphaZero doesn't learn anything about how chess works or about how Go works, right? It knows the rules of the game initially. It knows the transition model. What it learns is ways of planning or reasoning more efficiently. And so the idea that we should learn to plan or reason more efficiently is very, very important. It's not the same as learning how the world works. It's learning in some sense how your cognitive processes can work better. So one example of this, which is actually done by my student, Bom-Joon Kim, who's now there back in Korea, was to think about how to take some of the lessons that we learned from AlphaZero and apply it in robotics problems. But we're really interested in learning that is very, very good at generalizing. And so the goal here, the ambitious goal, was to have the robot learn about moving these boxes around in an apartment, right? So it's got these big boxes it can move. It's got the red box and it's got this other room. And the question is, could a robot who learns about moving boxes around in an apartment like this, big boxes, come over here and learn how to move small boxes in the cupboard? And in particular, could what it learned in the apartment help it with the cupboard? So that requires very, very aggressive generalization. And so the idea that Bom-Joon and our other student Luke worked on was to do Q-learning, so something that looks a little bit like what happens in AlphaZero, but to do it about the discrete choices. So when you have a robot in a world like that, it has to decide which objects to operate on and then pick the continuous parameters. And so the question was whether to see if we could learn a Q function that would be good at picking what discrete action to take next. And it's a way of reducing branching factor and so on. What is difficult and interesting about this problem is that in any given new scene, any given new problem we might have to solve, there's different numbers of objects. So we needed to use graph neural networks. And we represent the state of the world in terms of these relationships between the objects. So in particular, a very important relationship between this red box and the green one is that the red box occludes the green one. It makes it difficult for the robot to reach that green box behind it. So this relationship between the red box and the green box is critical. And we use a motion planner to compute these relations, and then we put them in the graph neural net, and we use the graph neural net to predict what objects we should move next. And so from this, we are able to do the following things. So we train the robot. In training, the robot only has to move one big object into the other room. But at testing time, we test to see how it can work on moving all these objects into the kitchen or moving objects around inside the cupboards. And we tried 3 different algorithms. One algorithm is one that came from the literature, and it works pretty well in all the problems. We tried a simple heuristic, which was good in 2 problems and terrible in the 3rd. And then we found that actually learning was substantially better in all these cases, right? So learning to be able to solve the problems more efficiently really helped. So I think that is about, I'm a little bit over time. So let me just draw some conclusions. I'm going to do this by going back to a talk that I gave a long time ago. So this is the very last slide of a talk that I gave at IITP in 1997. So at the time, my conclusion was that there had really been a lot of progress in algorithms for supervised and reinforcement learning. I thought that was true. Boy, you know, I thought that was true in 1997. And now I think, wow, it's really true. So, you know, I gave a talk at IITP later and I say, well, okay, now there's really been a lot of progress. But I wasn't completely optimistic. And I said that I thought that although we'd made progress, it doesn't directly give us solutions for building autonomous systems. And I think that that's still true. And in particular, we don't really know, I think, how to build generally intelligent autonomous systems. So there's still work to do. And I think human insight is still needed to complement the kind of machine learning and algorithmic methods that we have. And in particular, that what we can do is take our understanding from science about what nature builds into systems, and we can take understanding that we're from engineering about what engineers understand how to build into systems and understand how to build those in as a form of algorithmic and structural bias. Combine that with machine learning and get very rich and flexible and robust robots. And so with that, I will say thank you to my collaborator, Tomas, and many students who were very instrumental in doing this work. And if you want to, you can watch the robot a little bit doing silly things. So thank you.
네, thank you. 감사합니다. 캐롤린 교수님의 발표 함께 하셨습니다. 지능형 로봇에서 구조화된 학습.
Thank you very much. So that was a topic, learning and using structured models in intelligent robots. She has been researching this area for a very long time, and she had also pointed back to her own research that she had presented in 1997, and she has shared with us the status of AI as of today. So that was the second presentation of brain-inspired artificial intelligence.
So it's the Q&A session now. So Professor Byung-Tak Zhang and also Professor Leslie Kelbling will be participating in the Q&A session. Both of them are connected through Zoom. So without further ado, Professor Zhang, I'm going to give you the mic.
네. Thank you, Leslie. Thank you for the nice talk. Maybe we can discuss a little bit about our talks. Maybe I can ask you first one question about in Korea, that especially we are interested very much in neural cognitive inspired AI models as a future of AI. You are working with the neuroscientists. I recognize cognitive scientists as well. So maybe what can we learn from cognitive science and maybe neuroscience for future AI, especially the human level AI or whatever?
Well, so the thing that I'm personally most interested in learning from them is something about what's innate in brains. So natural systems are born with a lot of built-in structure and ability. And so I'm curious to understand more about what's built in a sense. So Liz Spelke, who's somebody that we talk to frequently, you know, her belief is that human infants and even many other mammals are in some sense born with a sense of objects, like that they kind of understand that they're embedded in the physical world, that there are objects in the world around them and so on, that there are other agents and an understanding of space. And so, for instance, although I like machine learning very much, I think that we don't have to learn absolutely everything, and that it's okay to like build in the idea that, for instance, the robot is living in three-dimensional space, because I can't imagine for right now anyway, any robots that are not going to be doing that. So for me, I'm interested in constraints. I'm also interested in understanding places where human decision-making is substantially suboptimal. So if you look at all the algorithmic problems that we're trying to solve, they're computationally very difficult, very intractable. And so we know that we can't solve them optimally. We can't solve them in the general case. And so it's an interesting question to ask, what are the suboptimal ways that humans behave but still do okay? Because that might give us some insight into the approximations that we can make in our algorithms.
Right. Yeah. Okay, that's can be recognized, especially if you really work with the robots or embodied agents. Or yeah. I talked about we maybe need to move from machine learning to learning machine. So because you have been also worked on robots, embodied agents, actually that is a better way to improve the machine learning technology, because you can have sensors and actuators, and the machine can recognize itself, sometimes mistakes as well, that can help autonomously improve its performance without human intervention. Ideally, of course, there can be some, yeah. So what do you think of that kind of a trade-off? If you have a body, you can recognize yourself, well, the weight of some objects without any help. No need for labels, external labeling. On the other hand, if you have a body, you have some difficulty to move the body. But in nature, we have that kind of natural systems. And I think there is some trade-off here. A little bit nature-inspired or embodied way of learning. And independent of that, you can use just symbols and logic and just abstract way of building some knowledge without grounding in the real world.
Well, right. I mean, I think that, right. So robots should learn from their own experience in the world. That seems important. I mean, I think again, and they should learn. I think one thing that's very important is that they need to learn incrementally. And I got the sense that you were talking about that. And so one thing that I find frustrating is that a lot of current robot learning is, you know, it's completely end-to-end and focused on a single task, so that the robot learns to do this one thing, but then tomorrow, if I need it to learn to do something else, it kind of has to start over. Whereas, you know, I would like to have a system where the robot learns some basic abilities, and then because it has those abilities, it can use those to learn something new. So no, I'm very much interested in that. We spent some time thinking about exploration and some exploration strategies that are motivated by some cognitive science understanding of play in children. And the idea that children sometimes set goals for themselves, like they kind of say, well, I wonder if I could do this. And then they work at trying to make that goal true. And in trying to do that, they learn, they learn a lot in a kind of more focused way. So that's another example of being motivated by something that we know about cognitive science.
Okay. Okay, thank you. I think we have some questions from the pre-registered people. 미리 등록한 분들 중에
So there were
질문
some
올라온 게 있죠?
questions that came in from the registrants,
지금쯤 한번
and
들어보는 게
so
어떨까요?
let's have those questions now.
네, 안녕하세요. 대구 창의과학교
Hello, my name is
연구소입니다.
Sung-Min Han. I'm from Daegu and I work in a middle school. So I have a question for Professor Zhang. So currently the AI is based on data and is performing supervised and classification learning. So humans are training AI with algorithms allowing them to perform more complex tasks. And so it's garnering a lot of attention. But so the question is this, if we go further to developing AI that autonomously learns, then would it be able to analyze like humans and respond flexibly to various situations while at the same time being ethical at the same time? So if there is no ethical learning, then the dark ages of AI, as we had witnessed before, may come back. Or perhaps we'll see the emergence of Skynet, as in the movie Terminator, so which is very worrisome. So could autonomously learning AI possibly develop into something like a Skynet?
네. Leslie, did you get it in English? Or
I did not. I just
okay.
got a message about how to do interpretation, but I haven't figured it out yet.
The question was about the ethics of AI. If the AI develops so advanced that it can learn autonomously, so it can be out of control of people. Can be dangerous. Like, yeah. What do you think about that question?
Well,
so how we can control the,
Yeah. I mean, it's an interesting philosophical question. Although if you come and look at the robots in my lab, I don't think you'd be too worried right now. I think so. There's a very important topic, which is where the robot's objective function comes from, right? And one thing that's interesting is that there's been a change in the way that we program robots. It used to be that people programmed robots by telling them what to do. Do this, then turn left, then pick this up, then, so that it was instructions. Now we program a robot by telling it what we want, and it figures out what to do. But we still get to tell it what we want. And so there's a very important problem. Sometimes it's called value alignment, of making sure that the reward function or the utility function or the objective that you build into your AI system is in fact something that you want. And you want to make sure that it's trying to pursue things that are actually good. So I think that that's a problem that we should be thinking about. But I really don't think the robots are going to take over.
Okay. 레슬리 교수님, 캘빈 교수님 답변 들으셨을 것 같고요.
So I hope that
조그만
Professor
생각도 거기다
Kelbling understood
보탠다면은
you all understood Professor Kelbling's answer. And just to add on to that point,
주어진 데이터에 주어진 목적 함수에
the machine today are looking at the
뭔가를
presented
학습하기는
data
하지만
and they are training
사실은
on
인덕션을
the
써가지고 귀납적으로
functions,
학습을 하기 때문에
but
뭔가 주어진
inducive
데이터에
learning is
있지
what they
않은
do.
새로운
So
지식도 만들어낼 수 있는 게 발견이고, 그러니까 스스로 성능을 향상하는 이유기도 하고, 그렇기 때문에 사실은 논리적으로 보면 계속 발전해서 컨트롤을 벗어날 우려가 있고요, 당연히.
And of course, there is a possibility that it might go out of control because it's doing some of inductive
인공지능을
learning.
설계하거나 개발한 사람의
And
의도를
if we give more
점점 더
autonomy,
벗어날
then
우려가 있는 것은
the
사실입니다.
machine, there is a concern that the machine
그렇지만
might
아직 현재 수준이나 그다음에 그
get
목적
beyond the
함수를
control
어떻게
of the
설계하느냐에
person who
따라서
developed
그래서
it.
지금
However,
켈빈 교수님도 얘기하셨는데
as Professor Kelvin just
목적 함수의
mentioned,
value
that
이런
would be
거를 설계하는
determined
거에 따라서
by how
여전히
the values
그걸
are
어느 정도 컨트롤할 수
designed
있고
for in
그거
the
자체가
functions.
사실은 연구 대상이기도 합니다.
That will probably be able to control
비교적 짧은 시간
the
안에는 아직
machine's
우리가 우려하는
learning,
그런
and
사이언스
that is
픽션에서
again
보는
a
정도의
research
우려까지는
question
하지
in
않을 것
itself.
같고요.
And so for the time
그것
being,
전에
we
이제
aren't
기술적으로
forecasting
해결해야
the scary
되는
situations of
문제는
science
여전히 꽤 있는
fiction,
것
but of
같습니다.
course there have to be a lot of technology that has to be solved
이
before we
부분에서
come to that state.
저희가
And here,
그 채팅창에
so we'd
주신
like
질문들이
to
지금 많이 올라왔습니다.
address
감사합니다.
a question on the
많은
chat window.
질문들이
We are
올라와
seeing many
있는데
questions coming up on the chat window.
네, 질문이 너무나 많은데
Actually, there are
그중에 한 개
lots of
정도만
questions.
제가
Let me just pick one.
선택을 해달라고 요청을 받아서
And I've been asked to just select one question.
이 질문을 하나 질문을 받아보겠습니다.
So let's try this one.
잠깐만요.
Just a moment, please.
보상에 관한
So it's about
질문입니다.
reward.
오하람 선생님께서
From
질문하신 건데
O
잠깐
Aram.
읽어보겠습니다.
So let me just read the question.
한 결과의 행동의 보상에 관한 건데
So it's about reward,
보상의
about
기준.
a result of
스스로
a
학습을
learning.
해가지고
So it does
그
autonomous
학습의
learning,
결과가
and the result
올바른지 아닌지에 대한
may be wrong or
판단을 내려주는
correct.
객체가
And so
러닝
there has
에이전트가
to
하는
be.
건가요? 하고 질문하셨고
Would it be
아니면
the learning agent itself who would make the evaluation of
보상에 대한
what's right
상황을
and what's wrong,
어느
whether
정도
the result
규칙을
is
정해서
right
스스로
or whether
학습을
the result
해나가는
is
건가요?
wrong? Or
그다음에
would
인간이라면
it
행동에
be
대한
learning
결과를
itself?
환경이나 주변
Because
상황인지에서
humans
이 행동이
recognize the environment
잘못해왔고
to determine whether one's
잘못됐고
action is correct or
잘됐고를
incorrect
판단하는데
or
그
right or
판단의
wrong.
기준이 어떻게 설정이 되는지
So how do you set the
궁금합니다라고 질문해
criteria in the
주셨습니다.
case of an AI?
그래서 아까 말씀드린 부분들이 사실은
So I
아직
think it
여전히
relates to what we had talked about before. So in human cognitive sciences,
원리를 이해하는 걸 필요로 하고요.
we still
그런
need more
관점에서 보면
understanding.
지금 우리가 보통
And from
컨트롤러에서
that kind of
구현하는
perspective,
방식으로 지금 방식으로
if we
한다면
are able to continue the way we are doing in a controlled environment, then I think we'll be able to have the humans setting the guideline. In that case, there would be many different options. Of course, the AI may be able to select from the options, but it will be the humans who lay down the options. But overall, it will be the humans who would be establishing the different options. And so that would be taking the advantage of both the machines and also combining with the needs of human beings. The conventional way would be have the objective function and just let the machine just do it what's supposed to do, but that would restrain the machine from being more intelligent.
그런 부분은 그래서 사람처럼 그래서
So
궁극적으로는
ultimately,
가치 함수 이런 가치 기준
the values or the value
기준이
function,
있는 것처럼 그거를
just
큰
as humans have these values, we also have to set the boundaries of the values even for AI. It's like the ethical boundaries, so to speak. And then under that, we have to think about the efficacy and the utility and also the ethical side as well. So it's a multi-dimensional contemplation that we need. So we need a guideline and then also be able to reward the AI if it complies to a certain set of rules. So that's basically it for the session. So can I end the session here? So yes, I'm just going to ask Professor Kevlin perhaps for your final words.
Do you have any final comment?
I don't know. I mean, I think that we're at an interesting time in AI, and I think we have to be careful a little bit, both about I mean, there's this concern, I think, that I'm hearing in the conversation about AI being too strong and so on. But I think we should also be careful about our rhetoric and that there's, I think, a lot of people talking about AI and imagining that it can do more now than it really can. And so, you know, we're making progress, but I don't think the world hasn't changed yet. So we'll keep working and we'll get somewhere.
Okay, right. Thank you very much.
네.
네, 그러면 이번 세션을 마치도록 하겠습니다.
Okay, that brings us to the end of this session. Thank you very much. Thank you. So Professor Zhang has moderated the session, and we have also heard comments, final comments from Professor Kelbling. Thank you so much. And so that brings us to the end of the second session about that brain-inspired AI. And I would also like to thank the online participants who are very active in participating in the discussion. So now let's go on to session 3, which is about explainable artificial intelligence. And just as before, we have two presenters making their presentations. So let me introduce the first presenter.
So I'd like to invite Professor Jae-sik Choi from KAIST, who will be speaking about recent advances of explainable artificial intelligence in Korea. He is the head of the Seongnam Research Center of AI graduate school at KAIST, and he'll be speaking about recent advances of explainable artificial intelligence in Korea. Good afternoon. I am the head of the KAIST Explainable Artificial Intelligence Center, KAIST X8. I would like to extend my thanks to the hosts and organizers, the Ministry of Science and ICT, and also the IITP, and also I'd like to extend my welcome and thanks for Professor Mueller, who has traveled from far away to actually join us here. Now, the KAIST Explainable Artificial Intelligence Center includes KAIST, Korea University, Seoul National University, Yonsei University, and Ulsan, and AI Tricks, and also foreign institutions. So explainable AI is trying to address the mission-critical systems that would be used, the mission-critical systems that would be used in these situations, such as the accident that is pictured here by an autonomous Uber car. And the European Union has established the General Data Protection Regulations, or GDPR, stating the right to be forgotten and limited automated decisions, and also right to explanation. The right to demand explanation is about the automated decisions that are made by algorithms. And so when HR decisions are made, or there's screening of the creditworthiness of a person, of an individual, then the companies will have to provide information on how they came to this conclusion, or explain how they came to this conclusion. And if these rules are not abided by, then they might be fined up to 4% of their global revenue, and this has gone up to 6%. So there's a lot of research taking place on explainable AI so that the black box issue of AI can be solved. So over the 54 months since the end of 2017, this project has been in place under the Ministry of Science and ICT for Innovation Growth Engine project. So the KAIST Artificial Intelligence Center works with many other partners, and not only in medicine but also manufacturing and Other areas, financial services are seeing application of explainable AI. So explainable AI is important. And what is most important is, of course, people. And this project has been pursued by the government that has brought together 250 researchers on explainable AI. These researchers are participating in a world-level research. So the center has published 68 top AI conference papers and 35 top AI journal papers. And Professor Mueller has also published a book on explainable AI. And DARPA and other partners have worked together in a science robotics paper. So many workshops and tutorials are also taking place in an international research project. And also, in terms of commercialization, we are working hard. So we are focusing on explainable AI and working with the ministry to propose this as an international standard, and this has been accepted for the first time in the world, and we have a dedicated task force for this. And we have applied for 13 patents, and XAI has led to 8 billion won of commercial investment attraction. And with industry cooperation, we are making commercial our XAI research outcomes. And we're not the only ones doing such research. We have made 26 open source sharings. And we are also providing tutorials so that the general public can make use of the knowledge that we have accumulated. And we are also providing many online training sessions. So 160,000 participants have been learning explainable AI and AI, the basics of those sciences. So I would like to focus on some of the highlights of our development and how this can apply to industry. What is most important in XAI is how it's going to be input into deep learning, or actually how it's going to explain the input and internal nodes deep networks. And these details will be covered by Professor Mueller later on. If there's an AI model, then which technology is going to enable the output? In 2015, we have worked further on the research that was done by Professor Mueller. And one thing that was interesting that we found out recently is that once a deep learning model is developed, then when we're trying to commercialize this, we often compress the model. And when the deep learning model has to be compressed, then its explainability seems to decrease. The NRP that finds the output, when it's compressed, it seems to lose its explainability. So before compression, if we ask where's the bus, then they would answer quite easily. But later we found after the compression that it wasn't able to answer the question as correctly. So the research team at KAIST made a model that would complement the explainability even after compression. So even with the lighter model, we are maintaining the explainability. And we are still studying why the compression reduces explainability. But the fact is that we have already obtained the technology that will retain the explainability even after compression. Now, also in classification of
medical images, explainability of AI was first triggered by medicine. Well, deep learning was able to find out whether there were cancer cells, but it was able to really clearly pinpoint where the cancer cells were. And now Professor No Young-man and his team has developed technology that is able to pinpoint the organ class where the cancer cells are. Well, explainable AI is delivered through a lot of technology. There's backpropagation algorithm and randomized inputs. And we found that this way was very effective. The randomized input developed in this way was quite effective. And when we are studying deep learning models, we thought the models were perfect. However, we found that many nodes were still lacking in their learning, and if those nodes are activated, then we're making images, the face or the cheek of the person in the image wouldn't be complete. So if a generative model makes up a totally new image, if it seems incongruous to people, then it's not going to be very useful. So which nodes and which deep learning models were problematic were discovered by the explainable AI and make a better model, better generative model. So this was one of the 18 breakthrough technologies that were determined this autumn, and we can see in blogs overseas that they call it plastic surgery for GAN-generated faces, and it was also marked as a column or article of interest on the portal Naver. Now, time series data, unlike image data, doesn't have labeling in many instances. So it's mainly meaning-based image splitting. The labels are often very well attached to images, but it's not the case for time series data. So what kinds of labels would go for which classification problems, and how much they impacted the output was determined. We found that out. For example, feature titled Group 22 recognizes that image. So there's Part A and Part B in the image, and how Part A and Part B each contributed. The diagram on the left doesn't make that clear, but if we look at the image that we titled Value LRP plot, that is in the right box on the red box on the right, we see that the contributions of A and B are marked. However, C and D, their heights are quite similar, so we find that their contribution is similar. And so we were able to find out in more detail which inputs impacted the output more. And then explaining and learning the causality in data was very important. So our center professors were conducting a lot of research in this area. When we develop a language model, the causality can be automatically found without any supervision. That was the goal. So that would help the explanation. So if there's a space is limited and crowded, but the service is quick, this is a review on a certain space. So before this research project, the keywords would be labeled manually. The keywords would be small and crowded and quick. But using an attention mechanism,
automatically words be added and then deleted. So without any labeling, which words were contributing more to the meaning of the sentence were able to be derived. And at the lab of Professor Hwang Sung-ju, this explainable AI is used in the intensive care unit at the hospital to be able to generate prognosis. The AI doesn't learn on its own, but the learning is shared to the doctor. And the training data so we focused on questions that would minimize the number of trainings while maximizing the performance. So without interactive learning, to make a sophisticated medical model, there would have to be about 300 trainings. However, if we focus on the most significant points, then about 100 trainings would allow for the machine to generate a very meaningful prognosis. And using small amounts of data, relational learning was achieved. So there's a person, a woman, playing with a frisbee and with her dog. But we haven't given any image information to the machine about the frisbee. We only allowed the machine to recognize the person and the dog, but we provided text data. So the data that we provided was a person and a dog are playing with a frisbee on a grass lawn. And then the question would be asked, what are the dog and person playing with? Then the answer would come up as frisbee. So this technology allows for convergence of other information to answer the question, not only based onto the question, basing itself not only on the image. So there's a lot of industry demand for these kind of technologies. So at POSCO, there would be the rules behind the manufacturing processes, and at Naver, there would be the explaining the generation model for internet services, or at the hospital, the status of a patient can be explained, and also the prognosis could be described. And if there's acute kidney injury, then the reasons to that can be explained. And the Bixby team at Naver and Samsung Electronics would generate a lot of generative models. And if there are any faults within that model, then that would be addressed. And explainable AI is particularly useful in financial services. Shinhan Bank and IBK and KEB Bank are able to explain the decisions made by the AI credit rating model. That's an interface that provides explanations for the customers. And this system that's developed to explain the state of an intensive care unit patient. So the many biometrics and test results would come in, they would be analyzed, and the risk would be predicted. We look at why the risk goes up and down. A system to explain that is being provided and being used in many hospitals. And as I mentioned earlier, for acute kidney injury, Google's DeepMind has made such an AI model and has published it in Nature. But we have made a stronger system that will be used at the Seoul National University Hospital. So this is the explainable acute kidney injury model, and we're going to test it. And in terms of manufacturing, POSCO, the steelmaker, has been using the smart furnace for quite a long time. But explaining that system is going to be important for the operators. And this actually model is very much appreciated by the operators because they can communicate with the system. And POSCO recognized our contribution, and they have given us an award, as you can see on the slide. And in terms of financial services, as I mentioned earlier, Professor Lee Sung-hwan's team in our center is using explainable AI and providing descriptions on why the credit ratings are coming out as such and what conditions have to be met for the credit ratings of a corporate or an individual to change. So AI Tricks is a startup for explainable AI. It was able to raise 8 billion won in addition last year. And as I touched upon earlier, Korea has proposed for the first time an international standard for explainable AI. And we have been approved, and we have set up a dedicated task force team, which will work for the upcoming 3 years to develop a standard and be at the forefront of establishing an international standard. This is my last slide. So 250 researchers are brought together in this effort for explainable AI. And they're trying to work to develop a world-class technology and how I also shared with you how this is being used in industry. International cooperation is going to be very important, as Professor Mueller will also share with us. But there are many questions that still have to be answered. Can we interpret and understand billions of neurons? So Professor Benjo earlier said that this is probably going to be impossible, but we believe that this is possible, and that is why we are continuing to study this. But if one of our models make a failure, then will it result in a critical or lethal problem? That question still remains. Is there any trade-off between the performance and explainability? Can we improve the performance? Can we improve the performance of AI models with explainable AI is another question. And how can we define and measure the model's explainability is yet another question. So these are not only societal questions, but also questions that are very important in terms of technology as well. Thank you.
Thank you very much, Professor Choi.
So explainable AI, the trends of development in that area have been shared in detail, and we still have many questions to answer. And I think those questions, some of them can be covered in the Q&A session after the next presentation, and please uploading questions.
And so now we'd like to invite Professor Klaus Mueller from the Technical University of Berlin. So would you like to come up to the stage? So Professor Mueller is a professor at the Technical University of Berlin, and he's also an adjunct professor of Korea University. So he's going to talk about XAI to gain insight into the sciences and humanities. Let's welcome him with a big round of applause.
Well, good morning, I should say, because I'm in the German time zone still. And I would like to thank the organizers for this wonderful meeting, for organizing it, and for having me here. So this is a fantastic experience to actually see real people again at a meeting. So, of course, I also see the screens, so, and in this way, many more people in the world can enjoy this nice conference. So let me talk a bit today about how we can use XAI to gain insight. And I will start just briefly talking about XAI and the background, and then come with two new algorithms and embed them in applications in the sciences. And the red thread is always to gain insight. So I think many of you have seen this picture. So the idea is, assume that we have done the best that we can to train a neural network model or any other model. So how can we study why a model is taking a certain decision? And this is a very hard problem, and it has been taking, so this is called post hoc explanation, because the model is fixed and already trained. So in a way, if you would like to explain the prediction of the model, then you need to put the model upside down. And the model is nonlinear. And that's a mathematical challenge. And it took until about 2015 until we could contribute what is now quite popularly used. It's called layer-wise relevance propagation, where we show how to actually put the model upside down. So given that, we have some technology in our hands that can be used. So one thing that I would like to stress is the mathematics of layer-wise relevance propagation. We've, gone quite a path from the early paper from 2015, and we've started proposing rules for different parts of the architecture, for convnets, for ReLU networks, and for all sorts of parts of the architecture. And it turns out that one can theoretically say what is the best relevance propagation rule for a given architecture and layer. So this means that you may have to combine in a complex architecture different rules in order to be optimal. And that really makes a difference in the application. Luckily, there's software out there that does this automatically. So it's essential to apply the right LRP rule. Otherwise, if people complain that things don't work, it may be that they haven't done their things right. So LRP has been used in all sorts of contexts for recurrent networks, for all sorts of neural network architectures, for kernel methods, and most recently also for graph neural networks for similarity models. I will talk about these 2 points. And also in the last year, we did a lot of work on explainable unsupervised learning models. Now, one interesting point is that XAI can give us some interesting insights into model flaws. So we all use models, and we trust in them because they predict well. So this is a typical exercise that I take from computer vision. And so this is out of sample generalization error for a computer vision task. And so you have 2 models, Fisher, which is very popular, and some deep network architecture. And so you can see that in some classes there's a difference, but in the highlighted one, in the horse class, there's actually no statistical significant difference. They generalize equally well. So what we teach to our students is that for machine learning models, generalization error is the most important thing to monitor. So this measure that we teach our student is telling us both models are the same. They are equally good. Now we can analyze them with XAI, and here's a classification. So you see an image of a horse and a rider, and it's correctly classified by both models to be horse pictures. So that's good. But then, practically, you can see in the lower right that if you look at the explanation given by the deep neural network, the highlight, red, is talking for classifying this as a horse, green is neutral. So the highlight is on the horse and the rider, which is the thing that you would expect from a good model. The Fisher model is solving the problem slightly different. So you can see a bit of activity on the horse's butt, but most activity is on the lower left corner, where there's no horse. But in fact, this is an artifact of this data set, which is a copyright tag. So for this particular class, more or less undetected, people have been using this for 10 years or so as a benchmark in computer vision. And the model solves the problem by detecting this copyright tag, and in this way uses an artifact that has nothing to do with horses. So if you think about a more serious problem like medical diagnosis, then it's certainly not a trustworthy way of solving a problem. It's also not a safe one. So we'd rather have a model that solves the problem like the DNN in this case. So we have coined a term for this, and it has also to do with a horse. So this horse's name I introduced to you is a Berlin horse, and the picture is from 1900 something. And the horse's name was Hans. The horse Hans allegedly could solve math problems. So you can see the owner of Hans pointing to a board where there were math exercises. The horse would then use its hoof and tap on the wooden board as many times as the result was of the math exercise. Interestingly, the horse could always get the math right. The result would always be correct. And so people were writing globally in the press, horses can do math. This is so great. But then after a while, somebody more reasonable came and said, well, I don't really believe that horses can do math, and it's practically, let's test this. And what they found out was that the horse is very attentive to its owner. So the owner, it's reading its owner and is basically understanding what the owner thinks is right and gives that as a solution. So it's a very interesting artifact that the horse is using to solve the problem. If you take another human, also the horse can solve the problem because horses are very attentive to humans. So people claimed or coined the term clever Hans because Hans was clever to solve the problem, but not doing math, but otherwise. So if we go back, clearly Fisher here has a clever Hans moment that it does. So the model is using an artifact, and we can detect it with XAI. It's very important that we always study this. So we should always detect clever Hans moments, and we can also remove them, which is part of our recent work. So now let's move a bit to the sciences. I first would like to take a detour to the digital humanities. And so before I do that, I would like to explain to you a model that is very popular in modeling similarity. So the idea is that you have two models, and these models see images, say, or objects, and then it is learned whether these two images are similar or not. And this is these can be sophisticated architectures, and this is a very popular discipline. And so the question is now, assume that the models consider two images similar. The question is why? And in this case, it's not a standard question of explaining a single classifier, but it's actually explaining a higher order correlations between classifiers. So if you look at the images, then you can see, for example, the two birds are considered similar because they are birds, and you can see the lines going from the beacons and also the eyes that show why these models think that this is similar. The same for the cow with the horns. So if we take a look at LRP, then for the experts of view, we know that there's a theory which is called deep Taylor decomposition that explains why LRP is doing the right thing. And it does a Taylor decomposition. And usually only the first order is considered. And if we want to explain similarities, then we have to go from the first order to the second order. And that allows us to have higher order explanations and come up with these similarities. Now, the question that we had, why we came up with this technique, was the following. So our colleagues at the Max-Planck-Institut für Wissenschaftsgeschichte, historians, they have digitized old books from 14 to 1600, several of them, I think more than 20,000, and it's physics and science books of that period. And so the interesting question is, for historians, how does insight, how does human knowledge, how has it evolved over time? And so part of the science books, they contain tables about planet movements and all sorts of things of that type. So tables are handwritten, and authors between different books, they copy parts of the table, and so the information is not just copy-pasted like in the modern times, but rearranged and redigested. And the question is, can we track and can we see what is similar to each other? And so can we have a map, a spatial temporal map of history? So in other words, we have to train similarity models, and then we can ask, if we consider something similar, then the historians will want to know what is similar. And the reason why we bother is, again, it's more than 20,000 books, and each of the books contain several dozens of tables, so it's completely unfeasible for a human to do this. And the interesting thing using this novel technology is that it allows us to study the evolution of ideas and of knowledge across centuries and across time, space, mainly in Europe, because these are books from Europe. So it's a very, very valuable source of research for the historians. And also it has some interesting clever Hans moments, because sometimes these similarity models are a bit, they look at the graphs, and you see in the lower left, there's two pictures, and they're just rotated. The similarity says it's about the solar system. The similarity just looks at the solar part of it. So not, the whole setup. So clearly also similarity models have their limits, and we know if we see such clever Hans moments there, then we should build better similarity models. Let me use the last minute to talk a bit about XAI in chemistry. And this goes back to a sabbatical that I did in UCLA. This was on quantum chemistry. And so the typical question that quantum chemistry likes to solve, they try to solve they understand the quantum chemical properties of materials and matter. And the Schrödinger equation, although it looks innocent, it's very hard to solve, and it can only be approximately solved with a technique called density functional theory, which got Nobel Prizes. What I suggested is, instead of approximately solving the Schrödinger equation, let us predict the outcome of the Schrödinger equation instead using machine learning. And this actually worked, although it was highly heretic, because in mathematics you tend to solve equations and not predict their outcome. So the interesting thing was we had a precision of about 10 kcal with our first paper. Then even in the same year we got down to 3 kcal, and we are now at 0.3 kcal, which is chemical accuracy. But at about 10 million speed up. So we have the right precision at a very high speed up. So just to tell you what this means, standard DFT takes 3 to 5 hours for computing properties, or for materials 4 months. CCSDT, another level of theory, takes 7 days for molecules. But machine learning models would take something like 0.1 millisecond. And the accuracy is about the same, out of sample. So now we can test our models and see whether they are chemically meaningful. And so you see the gummy bear plots that are basically the representation that the neural network has learned about chemistry. And so if you were a chemist, you would be very happy about these chemical potentials, in quotes. Now if we go to graph neural networks that have become very popular in many domains, but also in quantum chemistry, then we have an input graph, time evolution, and the idea is to, again, use LRP to do a higher order explanation in terms of walks. So here's the graph neural network based on this graph. Leslie mentioned that this is also, she's using that, and many people are. So we can then analyze these walks. And again, Deep Taylor allows us to look at the higher order terms in the Taylor decomposition. But we can decompose this very conveniently into a chain of local gradients. And then this way we can make this very efficient. So both the BioLRP and the graph neural network LRP paper are PARMI papers that are advanced online. Now we can also look at the molecules, and this is paracetamol, a typical drug. And we can now ask, so the model, the graph neural network model is predicting energies, and we can say that's the left graph, why is this high energy, having high energy, this molecule? And you can see that it's the oxygen double bond to the left. These are the red circles, and the benzene. These are the most important for the stability and energy of this molecule. Now, you can also ask for different quantum chemical properties, and you can also predict different quantum chemical properties, namely the dipole moments. And then you can see that the edges of the molecule, they are most important for the dipole, which is clear because chemically, if this is an elongated molecule, then it's very likely that the limits of the molecule contribute a lot to the dipole moment. Now, graph neural networks can also be used in the context of computer vision, and I'm just showing you one example where something that also Jessica mentioned, namely, can we analyze different abstractions within a model. So here we have the VGG model, and it classifies correctly the teapot. And in lower levels, we can see block 3, that this is basically edges and also corner detections. Then if we go up an abstraction level to block 4, then there's also parts of the object, and in block 5, there's the whole object is detected, dumbbell. And again, at some point, at a higher level of abstraction, there's again a merging of this in the representation, which makes some sense. So I would like to conclude. It's clear that we need to open the black box in order to make AI trustworthy, reliable, safe, and also fair. Higher order XAI, like by LRP or LRP for graph neural networks, was one example. Please check out our work on unsupervised learning and for XAI. So understanding nonlinear models is essential if we do science, because in science we would like to get insights. It's not only about prediction, it's about understanding the deeper insights of science, about how knowledge spreads and how quantum chemistry works and so on. So it's a very nice tool for gaining insights. And just to make this point clear, machine learning assisted by XAI is a very nice tool, and these disciplines hold a lot of challenges so that we can solve. And it's our task that we teach new students that are knowledgeable in the sciences and also in machine learning and XAI. Thank you very much for your attention.
네, 교수님 발표 잘 들었습니다.
Thank you very much, Professor, for your presentation. Professor Klaus Robert Mueller had come all the way to Korea from Germany to make his presentation. Thank you so much. It's a bit difficult because I'm just a layperson, but nonetheless, you give a very good explanation. So we have heard two speakers. They are both here in person, and we're going to have a Q&A session. So in Zoom and also on YouTube, we still have many participants staying with us. In the morning session, we talked about how we are prepared for some coffee vouchers, and if you leave comments, we will do a lucky draw to give out some gifts. So please, let me just remind you that those of you who participate in the questionnaire through the Google link that we shared this morning, if you leave your name and your phone number, then you can participate in the lucky draw. We'll do that once again during the closing ceremony as well, and then we will select some people who will be receiving coffee coupons. And we also have coffee coupons. And those of you who are participating online, if you leave a comment or if you take a photo or capture yourself participating in the forum and share it in social media, and then link that to our website, we will also select a few participants to hand out wireless chargers and also LG beam projectors. And so yes, please participate in these events. So we had two presenters, and we're now going to invite them once again to the stage for a Q&A. Professor Mueller, Professor Choi, would you like to come up to the stage?
So, for the participants who are joining us online, and also the participants here have been entertaining the questions. But for this session, we have both speakers with us here in this conference hall.
Thanks for your exciting talk on XAI. So you say that
finding the insight from the data through XAI is one of the very promising direction. Do you remember that one of the most interesting reaction from the scientist when you find some insight?
Yeah, I think that very generally speaking, I mean, we have been hearing great developments in using AI and natural language processing and computer vision. And I think there's very exciting developments also in using the machine learning in general in the neurosciences or in medicine or in physics. And always if we really go towards the sciences, you know, people are less interested and less passionate about having many parameters and very performant models. But they are actually rather compromising in the performance in order to understand their model, which is why classically the sciences have always used linear methods because then they are explainable. Now we have in the last 5-6 years had a tremendous development in XAI, which now makes it very safe and controlled to use XAI to also analyze nonlinear models and to actually extract the insights that science requires to progress. And so I think it's in particular for many of you who have been involved in applying machine learning in the sciences, it's really a process. So you try to predict something, and then you come up with a new hypothesis that can be tested. And you know, here XAI is really super important because you know it gives the scientists the possibility to properly formulate these hypotheses.
Yeah, I also agree with your opinion. Say that even if we train a lot of nonlinear deep neural network like model, then the specialists like scientists or in the factory, they wish to get the explanation in the linear model form at the beginning. And then it is a little bit evolved, and we agree with some basic information in the linear model and try to getting more like advanced explanation, nonlinear explanation are happening, right? So.
Yeah, also, I mean, I think it depends also very much, and this is also it has become an own field. Some things that you like as an explanation, I might not like, or I might not, I mean, assuming that I'm a medical doctor, and I would like to use an AI system in the clinic, and the AI system actually explains what it's doing and why is it coming to a certain conclusion, then there's also a layer of question, what is the appropriate way of presenting the information for the user? And this changes between a world-class expert or a student of medicine. So I think that is a very interesting question, how to do this properly.
Yeah, right. So after we find some algorithm and finding the insight and discuss with the specialist and finding better improved model, but still we may need to have a general or specialized interface to explain to the individual domain to improve the model. So basically we have a question from the audience, and one of the questions are recorded. So then let's take the question together and the answer. 틀어주실까요?
Could you have the video played?
질문 레코드.
안녕하세요. 주식회사 무하류에서 개발자로 일하고
Hello, I am
있는
a developer at
박혜린입니다.
a company. My name is
최재식
Park Hae-rin. I
교수님께
have a
질문
question for
드립니다.
Professor Jae-sik Choi.
인공지능의 정확성과 설명력을
I understand that the accuracy and explainability of AI are traded off. Can this be solved? Because the AI's predictions are not 100% accurate, I believe explainable AI that explains incorrect predictions becomes more important. If we look at this in simple terms, it seems that if the shortcomings are increasingly addressed using the explainability, the accuracy can be improved. Is this a feasible assumption? Thank you.
Oh yeah, so catch the. But I'm not so sure. So at the beginning, so many people say that more explainable model has like underperformed than the non-explainable model. But as the question like raised, so what we realized that is when we have a better understanding through explainable AI, then we can correct the model so the performance are improved. That is not only my opinion. So many people are actually agree with that. So what do you think about?
Yes, I also completely agree. I think there's no real trade-off between explainability and complexity of the model. So I think my opinion is that we should train the best model that we can and then try to explain it. Now, there's one aspect which is, I alluded to this in my talk. So if you think about the errors and the flaws that the model have, then knowing them and removing them is actually very helpful and improves the models. So a recent paper that you find in Information Fusion by Anders et al., and I'm also in the et al., shows how to systematically overcome biases and artifacts in the data. So quite often, the problems that we see in our models is, and that deep neural networks models and others like to overfit to, is really artifacts in the data set. And so if we can remove them, we can make much better models that are much safer. So having said this, the interesting new insight that few people know is that in unsupervised learning, there's not only the artifacts coming from the data set itself, but also from the model. So there's two layers of potential improvement. And so I always see that XAI allows us to debug models and to actually get better models. Just to give one example, so there's in ImageNet, which is a very large data set in computer vision, there's a class which is called Airplane class. And it turns out that even the best state-of-the-art models for ImageNet, they have had their clever Hans moments in this Airplane class. The reason being that typically the way the data set is produced is artifact prone because the images are cropped. Not all airplane pictures have the same size, so they're resized. And the way the cropping algorithm works for the last 20 years or so in computer vision is always the same. And so the neural network recognizes the cropping, not the airplane. So if we use some more sophisticated cropping, then the airplane is recognized, and then the model is much better in recognizing airplanes.
Yeah, so actually like the horse image case and the tag recognition and the aircraft cropping is the example that I typically use in my class. So I also agree with Klaus that so explainable AI is not only about the performance and the explanation. So we have analysis tools and find the reasons. So because of that, we can find the artifact bias. And also sometimes we can detect out of distribution sample to make the model more stable and so on. So that we can use that as a fundamental tool to improve and stabilize the performance of especially deep neural network, right? there are a lot of questions out after your talk, so then I will choose one of the online questions. So one of the related one is, so can LRP be used to extract insight from knowledge graph? So knowledge graph. So like you already work on the graph, right? But actually, if we think about relation and the word representation, like if we go further, GPT-3 and so on, then how we can use those information to extract relation and so on. So that is from Jaehyun Shin, AKQA.
Yeah, so very good question. So, so the LRP and friends and many of the explainable AI techniques have been made mainly for deep learning models, LSTMs, or for example, kernel methods. And if you think about a knowledge graph, then it's more a structure that we have about data. So I think it's an excellent question, and it comes more from the symbolic AI side that Leslie also mentioned in her talk. So I think the interesting question is, and also Leslie touched upon this, is how to bring the statistical learning and the knowledge part of AI together. So because one of the things that happen quite often if we are not working on language or images is that data is not abundant but scarce. And then the reason why we would like to have some knowledge graph or some structure is because it already includes a lot of prior information and some stuff that we don't have to learn. Now, having said this, of course, people would yell at me and say, well, but knowledge graphs can be wrong. so given this needs to be taken with a grain of salt. But the general question about how to fuse the information from a knowledge graph and the statistical learning is a very important one, and to my understanding, not solved.
So also, Professor Benjo and Leslie touch about compositionality of the knowledge because people wish to hear and understand better to combine the knowledge that they know with the insight that we provide. And there is also a very interesting question. So, and one question is, so there are some professors who are genius, but then don't teach much because they cannot find good term to explain to the student who don't have prior knowledge, right? But in our XAI case, that even if we could find insight, so explanation can be very important. So one of the questions from Shin Sang-gyun, this is Jeonjun Korea. So it's great that we have an insight from data, then the AI or XAI model can explain that people don't know. It's not understand or don't know or hard to understand.
This is, again, a very interesting question. So what I meant by insight in my talk as well is, there's one part which is insight into the model, and there's the other part which is insight into the domain, into the field. And there's different levels of that. And so I think machine learning models in general, also with the help of XAI, have now been demonstrated in a couple of cases already to generate new knowledge, like genuinely new knowledge that is not known to people. And so I think that's a very exciting development. And let me make an example why this may be extremely interesting. So let's take the medical domain. So many people in the medical domain, they are in search for biomarkers of some diseases. And so there's some knowledge about these diseases and how they are diagnosed and recognized. But if we have more and more technology for, for example, molecular measurements and also imaging and also, the documentation written by doctors, then this is a very interesting heterogeneous data, and the chance is high that if we analyze this with a good model, that and are able to explain this, that we really find genuinely new biomarkers. And so in the context of quantum chemistry, we've been, so our neural network has been finding a new way of defining aromaticity of molecules, that, aromatic molecules contain a benzene ring.
So this would be the last question. So when people wish to train the deep neural network, so Google make a TensorFlow and Facebook make a PyTorch. So I already know that you make a lot of open source in the heatmapping.org and so on. So in our a Korean society, to have some goal to make some easy to use explainable AI framework like TensorFlow, we call that as a plug and play XAI. So if it is the case, then will you still collaborating with us? And if it is the case, what would be the good way to make such kind of easy tool and framework?
So one of the first frameworks that we have been providing plugins for LRP and many other algorithms within the Investigate toolbox. So people have found this very easy to use, and so that is currently also, that was for TensorFlow 1, and so we are currently updating this together with the help of a larger community to PyTorch and TensorFlow 2 and other frameworks. And I think, everybody is welcome to also contribute to this, because, we are one global community. I think what we really want to have is AI systems that are safe and trustworthy, and it's worthwhile to spend some time on that.
It's almost time's up, so the last question are modified from the question from Kim Eun-hee from KIST. So thanks for your discussion, and also thanks for the attention. 네, 감사합니다.
감사합니다.
네, 이번 시간에도 정말 흥미로운
Thank you. That was again a very intriguing Q&A and discussion for this set of topic presentations. So there were so many good questions from the participants, and answering. The answers were also very good. So this has been a very fruitful discussion indeed. Thank you very much for your participation. Now the Global AI Forum, we have gone through the keynote speech and then 3 topic presentation sets. Lastly, we have the panel discussion. For the panel discussion, we will have 5 panelists, experts from home and abroad, discussing the current issues and solutions of AI intelligence. Justification and technology strategy of next-generation AI intelligence is the topic. So from Yonsei University, we have Professor Sung-bae Cho, who will be moderating this panel discussion. And Program Manager Hyun-gyu Lee and Professor Mueller, we will invite these 2 speakers to join us on the stage. And so Professor Kelbling and Professor Chang and Hanban Pati will be joining us on stage, while Professor Sung-bae Cho will be moderating.
이제 자리가 정돈이 된 것
I think
같은데요.
we
그럼
have
조성배
the
교수님께
stage
진행을
set.
지금부터
I would like
부탁드리도록
to
하겠습니다.
ask Professor Cho to be moderating this panel discussion.
안녕하세요. 이번
Good
글로벌 인공지능
afternoon.
포럼 패널토의
I
좌장을
am
맡게
going to be
된
moderating the
연세대학교
panel
조성배입니다.
discussion for this Global AI Forum. I am professor at Yonsei University, My name is Song Bae-cho. This has been a very active set of presentations and discussions, and I hope that we'll be able to solve the unresolved questions through this panel discussion. But now I will switch to English.
It's time to start the panel discussion on the challenge and future direction of AI. Now we are faced with the situation of enthusiastic fever of AI. Actually, that I've never seen for my research career for the last 3 decades at least. In this panel, we'll go over the current issues of AI that we are faced with and try to find out the potential strategies to level up the status of AI. We are supposed to have 5 prominent leaders in the field. However, unfortunately, the Subaru is not online. So anyway, we have 4 panelists. 2 of them were already known. Professor Leslie Kelblin from MIT. Leslie, would you raise your hand to say hello to the audience? Okay, thank you. And Professor Klaus Mueller from Berlin University of Technology. In addition to them, we have 2 more panelists. Professor Hyung-Jin Chang from Birmingham University in England. Raise your hand. Okay, thank you. And Dr. Hyun-Gyu Lee from IITP. So now I would like to ask each of the panelists to give a brief self-introduction on the area of interest and the significance of the work that has been done. First, how about Leslie?
Well, thank you very much. I already kind of gave an introduction, but I guess I should say that I've been working on learning and intelligent systems for a long time now. And I started out working in reinforcement learning, trying to get a robot to learn something just from trial and error. And I have grown from that experience to think that if we want to build systems that have a more general and broad intelligence, we need a variety of other mechanisms. That reinforcement learning by itself, I think, is not going to solve all of our problems. And I suspect we need a heterogeneous approach, that there are many different methods and that they probably all need to be combined. I think many people in artificial intelligence want to find the one true, very simple mechanism that will solve all the problems. And I guess I'm not sure I believe that such a one true simple mechanism exists. So the things that I think are most important questions at the moment are really how to get generalization. We find that neural networks, they certainly do a type of generalization, but they don't do very well in the way that, let's say, scientific theories do that humans make, that can see data in a very limited circumstance and then extrapolate wildly to much different circumstances and still make good predictions. So I think generalization is very important, maybe probably through compositional methods. And also the idea that we have to, or at least I think it's interesting to move toward making one system that can do a variety of things instead of a variety of systems that can do one thing.
Okay, thank you, Leslie. I guess you must be very tired.
It's a little late.
It's 2:30 a.m. In local time, right?
Mm-hmm.
Oh, thank you for joining us.
You're welcome.
Okay, next, how about Hyung-Jin Chang?
Hello, I'm Hyung-Jin Chang from the University of Birmingham. I would say my research has been focusing on humans mainly. So I'm doing computer visions. I'm researching deep learning, but I think human has been the center of my whole research. So my research has been focusing on the design, development, and the application of AI systems that learn from humans and cooperate in a deep and meaningful way. So I call this approach as human-centered visual intelligence, and I'm approaching it into with 2 goals. The first is learning from human, which implies an AI system should be continuously improved while learning from human, imitating human intelligence process. AI system which means AI system should imitate humans and create intelligent models from learning from humans. And the second is learning about human, which means that the AI system needs to get to know humans by seeing them and create an effective and satisfying human-computer interaction experience. So to be more specific about the learning about human research, it's like a comprehensive understanding of human through vision. So I'm interested in learning humans' intention or emotional state or internal state through watching the human's posture, gaze, like hand movement, or interacting object or environment. So that's my pretty much all my like general research direction.
Okay, thank you, Professor Chang. Next, how about Klaus Mueller? You already gave us a nice talk, but how about self-introduction?
Okay, yeah, it's a pleasure. So I'm a theoretical physicist by training, and then I did a PhD in computer science, starting with neural networks back in the days. So that's about 32 years ago now. I guess, you know, since then I've been doing a lot of rather fundamental things in machine learning, pushing kernel methods and doing all sorts of theory about neural nets and other learning machines. But at some point, I realized that I'm, you know, fundamentally interested and intrigued by interdisciplinary research. And so the first excursion to another discipline was really to neuroscience, where since '95 I've been studying EEG, and ever since then I have been studying the brain, using machine learning and teaching people in neuroscience how to use machine learning. But you know, more recently, I'm very interested in cancer research. This has some very private reasons. Finally, in the last decade, I've been doing a lot of machine learning for quantum chemistry, basically revisiting my original training. So because, you know, being trained, you know, in string theory and quantum mechanics and quantum field theory, you know, it makes it a bit easier to actually contribute to that. So maybe the conclusion of all these visits to other disciplines is it's extremely exciting, and it makes you very humble if you go to other fields, because it's a real effort if you want to contribute there. And so I got some of the most interesting and hard mathematical problems from these other fields, who said, well, you know, you can't just predict something, you know, please explain it, or please, you know, can you do this? And no, this doesn't exist in machine learning yet. So I feel, you know, after all these years, I feel that research at the boundary of disciplines is the most rewarding for me. And I think most progress is happening actually at these boundaries when they are pushed.
Hey, thank you. Last, Dr. Lee.
Yeah,
저는 학교나 연구소에 있던 사람이 아니고
So I am mostly in the industry, not in the academia. So I cannot really say I delved deeply into the technology, but more in application. So let me talk a little bit about my experience. So what I'm doing is that I'm actually heading the IITP's team on cloud data and AI, etc. And so I'm also leading the AI-related project in the IITP. So what I'm doing is that the AI-related R&D that is being supported by the government is being managed by me and my team. And so we look for different projects to fund, and we manage the different projects related to AI. And so because I have been working in applying AI, well, actually, I wrote my thesis on hand gesture recognition. And so, yes, if you give an order by hand, or say, can you control the PowerPoint, or using the hand gestures to control something. So there are temporal and spatial variants that are being used in the industries, and so predictive maintenance are also using this kind of AI. So I was involved in the commercialization of these products. And also, if you look at routing, it's not just about the shortest distance and time, but when the conditions change, you also have to have the routing. So if the climate changes, if there is rain, then how are you going to do the routing? And also, the road ahead of me may have a barrier, so if you go around, well, it might be burdensome as a human being because it might take a long distance and a longer time. But if you compare a side route with a straight road, are there any unpredictable situations that I might face? So these kind of decisions have to be dealt with. And what another project was did was how are we going to decide on the route of nighttime buses? So during the nighttime, there are not that many buses, and there are many people traveling from inside Seoul to outside of Seoul using these nighttime buses. But rather than AI algorithm, we found that when selecting the route, AI can be used to come up with the easier way to get home. So these are some of the real world issues that we had dealt with using AI.
Could you understand what he said? Maybe you are the only one without any translation.
I fully understood because I have a translation in my ear. So.
Klaus is no problem, but I guess the Leslie doesn't have any.
No, I'm good. I have translation.
Okay, thank you. Thank you so much for your nice introduction. And I'm so glad to have such a prominent scholars from different backgrounds for this panel. So now I would like to raise the first issue of the discussion on deep learning. Nowadays, as you know, deep learning is a sort of synonym of AI, and many people wonder if it is the ultimate vehicle to realize the AI. So how do you think about it, Dr. Lee first?
Yeah, 저희는 최근에
So recently,
인공지능 국가 전략의 일환으로 해서
as part of the government strategy, we have been planning AI. So whilst we were doing the government-sponsored project, we have been seeking for next-gen technology. One of the big focus, but which was also a big challenge, so we don't know whether we're going to resolve it or not, is that the deep learning has many limitations because it learns the given data, and after a certain time, then you would have an accumulated data. And then you have to once again make it learn the new data so that it is able to evolve the knowledge. But then if the time is too prolonged, then the past data is difficult to be preserved. So when we talk about next-gen deep learning technology, and in order to overcome these limitations, we came up with the idea of the continuous or lifelong learning concept. So from the past towards the infinite time, so from the current perspective, the knowledge has to be able to remember the knowledge has to be remembered, but then it has to go through trial and error. And the knowledge it remembers from the past has to be merged with the knowledge that it's learning right now. And so this is the project that we are looking into right now. But then, in terms of the memory issue, well, time continuously flows and trends change, the usage changes, the methodology changes. There are so many different changes. And so some of the past knowledge should be thrown away and some should be preserved. And so how are we going to well use the issue of memory? So this was a big challenge that we faced. The second thing was that, well, deep learning, well, in a deep learning, you learn through models, and sometimes it just consumes too much time. So for continuous learning, it has to learn and infer at the same time. So is that actually possible? Is it possible to learn simultaneously? And so when we think about continuous learning, there are some limitations that we need to overcome. And so I think that's also the limitations to deep learning. And so Korean researchers want to optimize the issue or the element of memory so that even a long period of time has passed, we'll be able to maintain the past knowledge. And also the second, like I said, is it able to learn new knowledge and merge it with the past knowledge and at the same time be able to make inferences from that kind of mergence? Thank you.
Summarize some potential issues of deep learning and some solutions as well. So how about Klaus? Do you have anything to add?
Yeah, so I think there's a lot that is open. I'm very excited that after so many years of researching, there's still so many great open problems to work on. So one thing that I'm worried these days is that our field has been almost growing exponential, and so it has become very experimental. Back in the days, I remember the first time that I was participating in conferences, there was always a set of people who worked on theoretical questions, and there was a set of people who worked on experiments and tricks and architectures and algorithms, and so but nowadays the number of theorists has been shrinking with respect to the number or staying the same. And also I feel that governments often just put their funding on applications of AI. And I think it's very important to look at fundamental things. And I feel that Leslie has made very important points in that respect. So that's one thing that I want to say. And of course, everybody talks about deep learning, but there are other algorithms around as well. And so, I'm always teaching my students to be pragmatically using whatever is necessary. And so the other thing that I feel that is very important, and it was mentioned several times by several speakers, is the incorporation of knowledge. How to do this? How can we? In a way, I think I'm rephrasing what what Leslie said. I mean, so what you already know, you don't have to learn. And in the context of my quantum chemistry, the laws of physics are there. They're well known. You don't have to teach a model to the laws of physics. But anything beyond that, can be learned from data. So of course, physicists would say there's nothing beyond the laws of physics. So don't misunderstand me. But so I think also another thing that is extremely important is if we want to use machine learning as a tool, then we should use it as a tool in the scientific process, which means that we have to progress the sciences as well. It's not about boosting prediction accuracy only. It's about getting insights, and that is sometimes not limited to better predictions. The third point that I would like to make is we have seen models with hundreds of billions of parameters, and we all go to demonstrations of Fridays for Futures. And so this is costing so much energy training these models. So we actually need to think about models that are actually able to use less energy. So there's a very interesting research field that has started in this direction, and I feel it's very important to devote some time and energy to that.
Thank you, Klaus. He pointed out quite important issues of the efficiency of the energy consumption for deep learning models, and also incorporation of that knowledge into the AI system. While we are talking about these issues, that we have the final panelist, Professor Subhano Gambapati from Arizona State University. So can you briefly introduce yourself?
Hi, yes, I'm Rao Kamapati from Arizona State University, where it is 11:30 in the night. So I'm sorry I was a little late. And I work in AI, like many of the panelists, and I've been interested in planning and decision making, and also human AI interaction.
Okay, thank you for joining us. You must be quite tired. It's near the midnight.
No, I'm actually quite fresh, but go ahead.
Okay, thank you. And I would like to hear about Leslie's opinion about deep learning.
So my opinion about deep learning. So I think, first of all, the interesting thing, the way I look at the rise of AI of late is that, with the way we started by teaching machines what we know explicitly, this is the sort of explicit knowledge tasks that as planning, such as reasoning, such as diagnosis, and so on. That was the first thing that we did. It's almost opposite to how human kids start. I mean, they start by actually just looking at the world and trying to recognize things and so on before they are ever actually able to do any higher level cognitive tasks, such as planning. And then basically the machine learning techniques, as well as the availability of data, finally gave us the leverage we needed to be able to do the lower level, quote unquote, the very first phase, the intelligence, the perceptual intelligence, the thing that many people say that you can do in a few milliseconds. This is the stuff that AI was unable to do for the longest time, and now we are able to do that. We all agree that the full intelligence is a combination of this stuff that we can do in milliseconds and the stuff we can deliberate and put things together. However, science is never rational. The pursuit of science is never rational. Science is rational. The pursuit of science is never rational. And I tell my students that just as at the time when we were only doing the higher cognitive level AI. We just assume, no, one of these days, I'm pretty sure we can do the perceptual intelligence easily. We don't have to worry about it now. We are doing the opposite at this point, that because we are drunk with our ability to do tacit knowledge tasks in a way. And so we just assume that one of these days, I'm pretty sure, full on planning and reasoning with this from a data-driven approaches will just emerge. And that's sort of a collective bet we are placing. It might work out, but also I like the kinds of approaches that people like Leslie, people like some other people are doing, which is essentially trying to kind of recognize that you do need the ability to do both tacit things, the things that we didn't know how to teach computers, and so they had to learn from data. But we also need to be able to control them with knowledge that we do have on explicit knowledge tasks, rather than hope that what they learn from raw data is just somehow going to be magically correct and would be robust, especially in engineering senses. My joke would be that, yes, evolution got us to a point where basically we were able to do both, tacit and explicit knowledge tasks, but I want AI to take a little less time than evolutionary time scale before, my factories are run by AI systems and a few fall apart and a few work. That's not the way we want, our engineering disciplines to work. So I think really the great research areas would be, how do we sort of combine these explicit and tacit knowledge tasks, in both of which we have expertise, but we haven't quite put them together. And I think that's where the most of the interesting work in AI is likely to be happening. I was also, I think you were asking me about the sort of the human-centered AI aspects. Humans have been rediscovered by AI of late. Something AI has become like the most important thing. Human-centered AI, human-compatible AI, human-aware AI. Lots and lots of humans have been discovered in AI. The thing that I tend to consider important, from a technical perspective, I do not want to live in the land of the machines. Okay, so the machines can learn their representations fine, but if they want to talk to me, they better talk to me in my representations, in my language. I should be able to advise these machines in my language, and I should be able to get explanations back from these machines in my language. I don't stop the machine from using whatever representations it wants to learn. So this interface layer between the human and the machine has to be in a way that I can live with, the humans can live with. If not, I think AI research has been a signal failure, because if it's a bunch of us, all we are doing is essentially trying to debug what particular pixels in the only lowest level thing that you and the machine share, which is these pixels, what pixels might possibly have been responsible for this decision that this machine made. If this is what 21st century human life is, that's very depressing. I think we want the machines to be able to be advisable, which surprisingly enough was the dream when McCarthy started AI, right? I mean, advisable AI systems was the thing that he was most interested in. He was thinking that even if they have logical representation, they may still be talking different language. Now we are saying we don't even know whether they'll have logical representations, but we don't care what representations they have. They should still be able to make sense to us. That's something that I feel strongly about. In fact, I think there's a Blue Sky track paper that's coming out in IIIT next year, which we talk about these symbols as a lingua franca between humans and machines. Just as machines don't have to have emotions necessarily, because we don't know whether emotions help us or not, but they better have emotions when they are interacting with us, because nobody wants a computer assistant which sort of laughs at them when they make mistakes. They need to have emotional intelligence. Similarly, even if they don't necessarily use internal symbolic reasoning, they should be able to understand advice in symbolic means, and they should be able to provide explanations in symbolic means. To me, that's the first part of being human-centered for AI systems in a technical sense. And in the other aspect is with respect to the fact that if you really want these machines to be working with us in the way we work with other humans, one big thing we have is social intelligence. We have the ability to mental model each other, and we are essentially using our models of other people's mental states to kind of decide what sorts of actions, coordinating actions, or communicative actions we need to do. In fact, explanations are always about what's in your mind, not what's in my mind. And this, good teachers know this, bad teachers don't. Bad teachers, drone on talking to themselves. Good teachers try to talk to what's in their students' heads. I want the AI systems to do that with us. They should be able to provide explanations, not in terms of, 15th layer activation is, 3 sigmas less than 95th layers units activation, which makes no sense to humans in the loop. But the explanation should be in the language as well as in terms of the knowledge they have about the task, that the humans have about the task. And this to me is going to be very important. This is mostly winds up being my research, explainable AI, and having machines provide explanations in terms that are customized to the humans in the loop. So I will stop there. Yeah.
Thank you, Subalao. Even though you even dealt with the next issue on human-centered AI. But anyway, thank you very much. And lastly, actually, you also working on cognitive systems and conventional planning systems for developing your own robotic intelligence. So what about your opinion on deep learning?
So, I think it's a very, very important tool, but that we have to use all the tools in our toolbox. And so I think end-to-end training of systems is probably not what we need if we're going to engineer big and complicated things, right? That we need modularity, partly so that we engineers can understand what we're building, but partly also because, we want I always like to have the combinatorial explosion work for me, right? So the way that humans get generalization is because they know lots of things, but then they can put them together in new ways. I can make new sentences and write novels. I can make plans to solve problems that nobody has seen before. And so we have to figure out how to get learning to do that, how to get learning to learn pieces that have the compositional structure that allow us to address big and complicated and new, really novel kind of problems. The other thing I think that's interesting is that in terms of, Rao was mentioning perception and also Klaus, I've been trying to use the best deep learning methods, just, to look at the world and understand what objects are on my table. And we're not there yet, right? So systems that seem like they are very highly accurate according to some loss functions or just measures of success and putting bounding boxes around cats, they're not necessarily good yet especially at some kind of old school problems like segmentation, right? So one of the earliest problems that computer vision people used to concentrate on was kind of class agnostic segmentation. I could look at a stack of objects of types I've never seen before and divide them into individuals. Now, not completely accurately, but really pretty well. But the current methods, for instance, don't address that at all. So I think the other thing that we need is some much better dialogue and feedback between, for instance, the people who are working on perception and the people who might use perceptual capacities to do other things. Because I think, it could be that there are other problems that we should be focused on. And although, we speak of deep learning as if it's a monolithic thing, but in fact, it's an enormous set of techniques, maybe mostly held together by gradient descent. But, there's a lot of nuance and lots of room for development.
Okay, thank you. Actually, I have one question in the morning that is related with deep learning. So anyway, the question is that currently deep learning models get bigger and bigger to the extent that it is not accessible to usual lab and company level. Is there any concern about AI becoming exclusive to certain institutes? I know that nowadays that big IT giants are the main players in this area. So who can answer this question? Actually, we are wondering the role of the university labs in AI, because usually the university labs do not have the large equipment for the computation and large data. So in this situation, how can you do?
Well, I mean, I think that there's a lot to do. Because, I mean, especially if you're interested in physical interaction or anything like that, then the learning from a giant corpus is not, at least currently, the way that we do that. Now, it may turn out that people do speed up learning for robotics by looking at lots of videos. So there are a lot of people who are thinking about that. But I think universities can still play a bunch of roles. And one of the most important roles of universities, I think, is to be a kind of repository for it's where the unfashionable ideas can keep cooking while they're unfashionable. So in fact, deep learning for a long time was unfashionable, and it kept cooking in universities while everybody was doing other stuff. And I feel sure that some stuff that's cooking right now in universities that just seems hopelessly, I don't know, not well formed or not appropriate, will turn out to be really important in 10 or 20 years. So I think we need to be reservoirs, intellectual reservoirs, so that we don't end up with a monoculture.
Okay, thank you. Lau?
Yeah, so I would put it in a slightly different, maybe a little more positive way than Leslie. And I would say that essentially universities is where we hopefully will work on where the puck, the ball is going to be rather than where it has been. And the industries obviously are going to look at where the ball has been because that's where it can be exploited currently. And that's just the way it has been, at the time when our ancestors were building amazing bridges. I'm pretty sure the first universities probably had the same question. We can't build an entire Roman aqueduct in the laboratory. What the heck are we going to do in terms of, research in civil engineering? But we know that clearly understanding strength of materials, understanding how to build these things came much after we were able to put together these megalithic structures, and that's extremely important too. I'm not against aqueducts being built before we understood how structures are being held up, but I'm against building many, many structures and hoping that some will stay and some will fall. Trying to understand how when we first build a structure, it won't fall, which we are able to do now. So much so that if a structure falls, it becomes front page news, is basically what understanding how the processes are going to be. And honestly, I think there is like a ton of research, ton of work that is worth doing, is important to do. It's crying out to be done beyond, can we just add a few more trillion parameters to the latest language, large language model and call it foundation model. That is not the only thing that's left. That's probably almost a lack of imagination if you are just sticking to that. But if I'm like a huge mega company, I'm trying to put products outside right now, I should exploit the technology as it exists while hopefully having enough, the wisdom to have like a Bell Labs kind of thing, cooking in the backside. And universities are always on Bell Labs. we actually had this very interesting debate at IIII, the last IIII that was actually open in 2020 before this pandemic hit, and whether in fact universities should be shut down because industries have labs. And I took exactly the position that I'm taking right now, which is that really the longer term research will get done in universities. And if you don't do that, then essentially you are stuck with exploiting whatever it is that you currently have. And I think, as far does every university need a trillion parameter model? That's not at all a requirement in any sense. In fact, we can have API access, and people are actually doing, even at the level of, let's say, LLMs. It was universities, several universities who have found all sorts of interesting issues, above and beyond just, the performance of these LLMs, these sort of structures. Models on just the well-known benchmarks, for example, because you actually have to come up with better ways of testing these things. So I am certainly not worried about running out of ideas that need to be done. In fact, they just, we have no clear-cut idea as to how to go from these models that seem to be doing reasonably good, very impressively good, I must add, in perceptual intelligence tasks, to anything beyond that requires any kind of longer horizon reasoning, for example. And so, yeah, I think I'm pretty secure in universities' jobs, I think.
Yeah, I totally agree with you. Actually, I'm also working on deep learning because I started my research career with neural networks quite long ago. But there are still quite many problems that can be solved with conventional AI. Actually, recently, I am advising a startup company to develop a virtual assistant called AI Suni for healthcare services to the old people for the life logging data collected from several sensors attached to the home appliances. There, we also needed some rule-based systems as well as a planning or something like that. So still, I think we have some niche that we can contribute. Dr. Lee, you also have something to add?
예, 조금 좀 다른 얘기를 좀 하고 싶었던 게 사실은 이 얘기에
I
대한
just have
답은
something
아마
slightly
오전에
different to
발표했던
talk
김준호
about.
박사님께서
I
해주는
think
것도 좋을 것
Dr.
같은데
Lim
저는
had something to
우리
say about it in the
나라에서
morning. But
이런
anyway,
부분을
what I want to say
생태계를
that
관리하면서
the
어떻게
government
지금
is trying to
놀라지
create an
못했나 이런 것들을 좀
ecosystem
공유해서 많은 스타트업들이라든지 이런
so
데쓸
that
수
a lot
있게끔
of startups are
하는가에
able to
대한
access the
고민들을 좀 하고
technology. So
있거든요.
this is the
그래서
kind
저희가
of area that I'm
국내,
working on.
한국 같은
So in the
경우는
case of
지금
Korea,
국내의 대기업
there are many large
라지
corporations
모델을 언어뿐만이 아니라 다양한
in
형태로
language
접근하기
and
위한
in other
시도들을 하고
areas
있고
are creating
실제로 그런
large
결과들이 일부 나와
models,
있는
and
상태인데
we have some good results
그들도
coming out
그들만
now.
쓰는 것이 아니라
But it's not
학교나
used just by
또는
them. It's
그
used
외에
also by
그들의
the
파트너들하고
academia,
같이
their
쉐어해서 쓸 수
partners,
있어서
by the
많은
universities,
협력
etc.
고리는
And so
만들어놨습니다.
there are lots of
그런데
collaboration
문제는
going
뭐냐면
on. But the
그것을
problem is
베이스 모델을
that,
만들기
okay, we have the
위해서
base model,
필요한
but
데이터의
there is a
사용성에 대한
data
문제 때문에
and the
저작권
utility
침해라든지
or
이런
the
것들
copyright
때문에
issues of the data that
그들의
was
파트너의
inputted
그들의
into the
서비스적인
project.
목적 말고는 쓰는 데
And so
제한을
they are
받게
not allowed to
되거든요.
use it
그래서
aside from what has
일단은
been
그들도
allowed.
많은
And so
파트너들이나
there are
선택의
many
그들
partners, there is
중심의
an
파트너들의 도움을
ecosystem.
주기 위한 기회를 주기 위해서
And so in order to
정부도
be able to
좀 같이
contribute to the
지원할
entire
수 있는 방안을 찾고자
ecosystem, the
하고
government has to
그다음에
find ways to
정부에서는
support these
중소기업이나
endeavors.
또는
And so when it
스타트업들
comes to
이런
small and
데들을
medium
위해서 따로
enterprises and startups,
별도의
the
거대
government
모델을
has to
만들어서 그 거대
able
모델을
to have
생태계 쪽에서
projects to
누구나
create
같이
large
활용해 보면서 그것의
models just for the
가능성과
SMEs so that
상품화의
they are
가능,
also
상품화를
be
위한
able to
인사이트를 구할 수 있는
commercialize
그런
and
기회를
also be able to get
마련하려고
insights and
현재
also be
준비하고 있는
able to
상황입니다.
access and create large models as well.
Okay, thank you. Anyway, to sum up, the deep learning is surely a powerful tool for AI, but still we need new techniques to overcome several limitations. So still we need to work hard. So anyway, I would like to go to the next issue on the difference of the current AI from human being. It's the previous sessions, many speakers told about human level AI. So what is the difference of AI from human being and how to reduce the gap? So Professor Chang, do you have anything to share with us?
Okay, thank you. I mean, not exactly about the difference, but I want to mention that the human should act a very important role for developing the AI itself. So because ultimately, I think the most important factor in AI will be and should be human beings. And that is because the ultimate development role model of AI will be human intelligence. And the user who utilize the AI and the greatest beneficiary of its development will be human beings. So the AI is currently very quickly advancing, especially in terms of its performance. But sometimes the AI model is very much focusing on its computational model rather than the intelligence itself. So the AI should be always considering the human factors implicitly and explicitly, I think. So the implicitly when AI is making advanced, like developed by the data, especially using deep learning, based deep learning methods, the human always has to be considered. So in reality, the efficiency and the performance of AI development by giant global tech companies can be easily neglect the human factors and sacrifice the humans for their performance improvement and sometimes commercialization. So the AI is always, deep learning is always data hungry. So the human can be sometimes treated as labeling provider sometimes, right? So that shouldn't happen. So I think the AI should be always developed ethically and responsibly for their own purpose. And I think the second challenge of AI, development should be based on the human interacting with humans, which I completely agree with Rao's comment. And the AI always has to interact with the human seamlessly, and in order to that, the human has to be encoded into the AI system, based on the natural language or visual interaction, etc. So I think that's going to be the main challenge for the development of AI, and there can be kind of difference between AI's development and actually humans' intelligence development.
Okay, thank you. Lau, actually previously you mentioned about different kinds of knowledge in human, explicit knowledge and passive knowledge or such. So do you have anything to add for human level intelligence?
Yeah, I think as I was mentioning, originally AI systems were all basically built for explicit knowledge tasks. If you talk about rule-based systems, expert systems, and so on, you're trying to get AI systems to do tasks for which we have essentially explicit verbalizable knowledge. The stuff for that, we could almost kind of provide models. And the word model has become kind of synonymous now with large neural network models, but essentially a model is the task knowledge that you can provide in some form, mostly symbolic form, to the machines, and they could use that in the past. There were these other kinds of tasks that humans do, starting as babies, which is basically just watching things and recognizing objects and so on, the so-called, under millisecond subconscious things that we are able to do, which we had no actual idea how to tell machines how to do that, because we don't know how we do it ourselves. It was tacit knowledge. There was this philosopher and polymath Michael Polanyi basically sort of bemoaned this fact at one point of time, that much of human science seems to be, human science in general, not just computer science or AI, seems to be focusing on spheres of knowledge where it is actually possible to explicitly encode what we know. but a lot of being human is actually being also dealing with this tacit knowledge, which is really true. But now we have almost the opposite problem. For example, the example that you were giving earlier, right now it has become the case that our hammer is this big neural networks, and there's almost a kind of a peer pressure to use the neural networks, even when actually I have the symbolic knowledge and that should be able to tell that machine. So the people talk about from data to knowledge. Really, there has become more a newfound way of going from knowledge back to data, so that, you know, a simple rule that you have to somehow convert into 10 million examples, so that your neural network can try to hopefully get this one rule that you're trying to give it, which is this advising the systems and so on. That sort of, we should not have to take that as the only way to teach our systems, even if in fact the symbolic knowledge has to be converted into examples for the machine to be trained. Let the machine do it itself. You know, it's not people's responsibility to say, I have this very simple rule. I know that you don't understand small rules. I am going to now sit back and write like a million examples of this. We're doing this as we speak. In fact, you know, the GPT-3 was, they were trying to, OpenAI guys were trying to deploy GPT-3 in some scenarios where the language that it generates hopefully won't be offensive to anybody. You would think that is very simple, but obviously it is not, because in fact, GPT-3 will generate any plausible completion, and there are enough number of plausible completions of any prompt you give that are offensive to some section of the customer base, including general humanity itself. How do you stop that from happening? You can have a human in the loop and say, oh, sorry, this cannot be sent to polite company, or try to actually say, in polite company, there are following rules we follow. We have a system one which generates stream of consciousness language, but we also have a system two that sort of, you know, tames it down. They were trying to do this for GPT-3, and the best idea they now have is to first write down all the rules on a piece of paper, convert these rules into gazillion additional examples, you know, basically because instead of Reddit, now you have this curated language, which is then added on top of the Reddit language and hoping for the best from LLMs. To me, that's too bad. You know, what 50 years, 60 years of research in AI, and what I'm doing is converting things into, you know, examples for the neural networks. That's what I do today, but I'll also hope to be able to have a much more a way of advising systems and a way of getting explanations from systems that's a lot more human-centered. That makes my life easy, not the machine's life easy. And that's like, you know, it's going to be very important. And I think the human-centered aspect of it is also that the machines need to have not just the models of the task, but mental models of the people that they are interacting with. In some ways, we already have things like Facebook profiling the heck out of people, and that has caused lots and lots of problems. But, you know, in fact, I have this thing that if in fact Facebook has a human face, maybe of Mark Zuckerberg, people would have been a lot more careful in telling Facebook accounts less of their life. And now they don't, because they don't realize that the programs might actually be profiling them. And that has caused all sorts of problems. But profiling is something that we do when we, you know, interact with each other, and the machines have to do that. And, you know, to provide customized interaction with us, they need to profile us. They need to not only know what we are thinking, they need to know what are we thinking about the capabilities of the machines. And explanations are really about reconciling these differing models. And that should become very much a part of the technical research problems that we work on in AI. And I think that's basically what has become this whole explainable AI or the human AI interaction research.
Thank you. Actually, at this point, I'd better open some of the questions raised in the morning session. Actually, there was a question to explain the difference of human-centered AI or human-level AI from general AI or strong AI. who can answer this question? Actually, some people are confused about the human level AI from the strong AI or general AI.
So first of all, I think the word, just because we put the word human next to AI with something in between doesn't mean they're all the same. As I said, in fact, my joke is that human X AI, they are very, very different meanings. Like, for example, our colleague Stuart Russell is into human compatible AI, which essentially means machines, please don't kill us. And which is quite different from human aware, which might mean that the machines have the ability to understand the human mental states and make sense to them. And then human level is the sort of level of our performance. And we clearly already understand that machines are way beyond human level in a huge number of narrow areas. I mean, who in their right mind will be able to differentiate between 200 kinds of dogs with near perfect accuracy? We thankfully have better things to do in our life than doing that. But if you can't do that, you won't have the kind of ImageNet performance that all the current day deep learning systems have. They are already superhuman in some of those things. I think by typically when we mean by human level, not only do we mean that we come to a certain level of performance in one, each of these small slices, but that we have the ability to have a certain minimum level of performance across all slices. And that certainly is something that machines clearly are not capable of doing. This has been the case from the beginnings of AI. When Deep Blue was making mincemeat of Kasparov, it still didn't know what a piece is and how to hold a piece. And even now, chess playing programs probably don't have the dexterity of a 2-year-old in the way they can pick anything on the dining table and try to put it in their mouth. We just don't have systems having that sort of a capability. So I think the human level is this sort of general minimal competence that is equal to the humans. What we currently have is in certain slices way beyond human performance, and many, many other slices basically nothing to do with, nowhere close to the human performance. The second issue about this is, if I want AI systems to just exist on Mars, assuming that we are not going to Mars very soon, things are much simpler, because actually, in fact, not surprisingly, most AI systems originally worked on like Mars rather than in the middle of people, because at least you don't have to deal with people. You basically just work on dealing with the task in some way possible without worrying about whether people around you understand the way you are handling that task. That's not, whereas if you have machines trying to do anything in our midst, we'll basically want to be able to understand, do we agree with what the machine is doing? Is there a reason why it is doing this action at this point? This is this business about explainability and so on. So I think that getting to a level of intelligence in a small area that's way, way beyond human is very much possible. And it's already true here, and certainly is possible, beyond too. But getting this general competence across a wide range of activities is something that we do, that just we are nowhere close to it yet. And I think that's what is very interesting. I mean, I'm much happier that we can at least have machines do some slice of perception, some slice of language generation than what they were able to do when I was a grad student, and certainly even in less than 6 years back. But I can still see, a whole ton of things that we can throw them under the bus for. I think some of you probably heard of this Delphi, which is this morality advisor that Alan AI tried to put up, using the large language models and doing some additional reasoning on it. It tries to say whether or not a particular situation is ethical or moral. And the moment it came out, people found all sorts of flaws with it and were able to actually make it say completely nonsensical things, such as hitting kids, not good. Hitting kids with love, fine, for example. So there is a lot that we can do other than just the single examples that are being offered to us. While machines might do extremely well in a narrow slice, you fall a little outside the narrow slice, no guarantees. That is something that we are still very much stuck with. and getting there is something that's going to be very important.
So it sounds like that we are far away from the strong AI. Actually, the other subsequent question this morning was whether strong AI is possible or not. So is there anyone to answer that question? Strong AI, weak AI, there are quite long debate, Leslie.
Well, I mean, just to be sure that we understand the terms, right? Classically, weak AI is a system that could behave indistinguishably from a human, but isn't conscious. And strong AI is supposed to involve consciousness. But, I think we're getting carried away here. Stuff is working better than it used to, but we are so far away from that I don't think we need. I mean, it's interesting philosophically, but in a practical sense, I don't think it's a critical thing to worry about. I'm with Klaus about thinking hard about the science, about understanding the theory underneath the techniques that we have and trying to characterize what they can and can't do and incrementally building up a kind of solid theoretical foundation for what we're doing. I don't think it helps to worry right at this moment about consciousness.
Okay, that might be quite a difficult question to answer right now. Anyway, we are running out of time, but I would like to give the question of any other important issues. Actually, in the morning, again, there was one question about the startup company. Actually, I guess Klaus might be the right person to answer. You have a lot of experience to support the startup companies. And the question is that, can you advise those who start a new business with AI? That was the question.
So I didn't get your last sentence. There's a lot of echo in this room. So can you repeat slowly?
Yep. So he seems to want to get some advice because he would like to start a new business with AI. So you have a lot of experience to support the startup companies. So if you have anything, then please answer the question.
Well, this is a very broad question, and I think the key ingredient in having a successful startup in general is luck and a good team, and also a business model that you can explain to your grandmother in 2 sentences, and she will understand it. Once you have that, it's a matter of execution, and quite often, scientists or engineers start a company, and they completely forget that there's a business side to it. And I think bringing teams together that are scientists, engineers, and also business people is fundamentally important for the success of a startup. And also, I mean, my group has been starting up a number of companies, and I have been mentoring them, but I was not typically a co-founder. But I think, there's some cultures where, starting up something and failing is bad, is considered bad. But I think, if you start up something, then there's a high chance of failing. And so I think that this is part of the game, right? And so therefore you need a bit of luck and everything to really settle. And there's also the timeliness issue. So some things that you may have started 15 years ago, would have been now a company with 1,000 people if you started it in our time now, because people understand that AI is something important. but maybe 15 years ago they didn't. And so I think there's a lot of issues to that, and I think the real most important thing is a good team in that, and a good idea that can be executed. And of course, bluntly speaking, if you get a team of very good AI engineers and business people together, then the chances are super high that you're bought up, because there's a lack of specialists in AI anyway, and everybody would buy a functional team anyway. But that's just a side remark. Anyway, maybe Leslie wants to say something as well.
Thank you. Okay, Dr. Lee.
예, 뭐 저는 사업을 하던 사람이니까 오히려 이런 답이 더 좋을 것 같은데.
So I'll just talk from a slightly different perspective.
죄송합니다. 저는 그 사업을 고려할 때 스타트업.
So startups, when they start a business, should not start with AI. That's my advice. You have to have a goal, and then you come up with a business model, and then you do all the planning, and then when you go into the specifics, then you can perhaps use AI technology in one part of your business. So if you want to start up a business just with AI, just saying that you have the best technology, it's just not going to work. Maybe you will have to be able to draw the big picture, but you probably won't succeed commercially. So first of all, do the business planning first, and then in one area, if you think that AI is going to work and AI is applicable, then go ahead with it. And just one other thing. Professor Mueller, you mentioned that when it comes to AI, is artificial intelligence. Humans' intelligence is being used to create artificial intelligence. So 15 years ago, somebody came up with the same idea. So in the past, there was an idea, but it can be repeated. We can reflect upon it now, currently, and see if it's applicable today. So I think that's another advice to startups. Look back in the past technology and see if something works today.
I'm sorry, we are a little bit out of time, and I think we have to close this session. So if there is anyone who wants to make some final remark, then it is the last chance. Nothing? Then anyway, the current AI sure it shows some extraordinary result, but still it cannot be the last and final product. So I hope the discussion made by our panelists help you understand the state of the art of AI and the potential future direction that we have to pursue. So anyway, I think it's enough. And thank you all for attending this session, and especially the panelists for sharing your perspectives with us. Thank you very much. 이것으로 패널토의를 마치도록 하겠습니다.
With that, I would like to close the panel discussion. Thank you. So Global AI Forum, that was a panel discussion. Thank you so much for fully filling that session with so many insights. So the challenges and also solutions regarding AI were discussed in detail. I would like to thank Professor Song Bae-cho for his moderating of the session. And I also would like to thank the panelists from home and abroad. So we have gone through 3 sessions of presentations, and then we had the panel discussion. We are talking about the future direction for AI with the leading brains from around the world. And we have so many participants who are still with us. And quite a few participants have been posting comments and questions. And we have people who have filled out the Google questionnaire. Please also fill out the questionnaire that comes up in the closing ceremony that is going to be uploaded in the chat window. And we will have a lucky draw to choose 100 people who have applied both times and give them Starbucks coffee certificates. And if you share a review of participating in this forum and add a snapshot of yourself participating in this forum and take a upload that on your own social media, and if you provide a snapshot or screenshot of that, we will choose the best review and provide them with gifts. And this is the last session on the status of AI research of Korea. We will have project manager Dr. Hyun-gyu Lee talking about the next AI research direction of Korea.
네, 박수로 환영해 주십시오.
Please give him a big round of applause.
시작할까요?
네.
May I start?
예, 안녕하십니까.
Good afternoon. Yes, I was just a panelist a little while ago, but anyway, I'm the PM for AI Data and Cloud, Hyun-gyu Lee. So I'm going to be talking about the AI research direction of Korea. So I'm going to be talking about mostly about the governmental policies and strategy. So we also set up an AI National Strategy Project Foundation, and we also is in the process of developing core technologies. And so since last year and this year, we were finally able to get some budget, and we will start earnestly from next year. So I'm going to talk about some of the tasks and project topics, and then how to move on from there. So first of all, let me talk a little bit about the background. The AI technology is based on deep learning and computing power, and it's continuously developing. Now technology and in the sciences, there is a convergence taking place, which is adding to the competitiveness. And so now governments are taking up these projects. So in the global market, you have the winner takes all kind of business environment, and the winner has a big advantage that the latecomers are unable to catch up with the forerunners, and so there's a huge gap. And so when we talk about the next set of technologies, there are some latecomers, but nonetheless, there is a lot of contemplation on whether we can come up with technologies that would allow for the late runners to catch up with the forerunners. The global companies like Amazon, Google, and Apple and tech giants are trying to get their leadership in AI and then applying it in the industries and also supporting the industries. So they're expanding their dominance over the industries. For example, Amazon is strengthening its presence in the distribution industry, etc. And a lot of the technologies were not necessarily a part of the national strategy, but AI nowadays is going to impact heavily the national competitiveness, which is why the government now, in addition to many other governments around the world, have come up with a national strategy. And so if you look at the national strategy, each government has focused on a part of AI, so it's being selective and focusing on something that it can do a good job in. So for example, in the case of US and China, which are the leaders, are focusing on technological development, also creation of an ecosystem. In the case of Japan, it's focusing on robots. But when it comes to intelligent robots, it was lagging behind Europe and the US, so Japan is trying to catch up, and so trying to converge the next generation AI and robots to be able to regain its presence in the robotics. Now going on to Korea. First of all, Korea, I would have to say, is a latecomer. We cannot become the winner or the leader in the AI area. Of course, we are able to catch up, and perhaps in some areas, Korea can become a forerunner.
시장이라는 그런 상황으로 봤었을 때 민간 부분하고 공공 부분하고
So the private sector and the public sector have slightly different approaches. In the public sector, it is about vitalizing the ecosystem for the private sector, but the private sector, unfortunately, is not using AI as much as it can. Many of the speakers have shared a lot of valuable insight regarding this application issue. When it comes to the academia, when it comes to researching AI, then it's very active. There's a lot of R&D in AI that is taking place. Of course, the results have still yet to be seen. But when it comes to everyday, when it comes to the utility in the industries, AI is not there. And that's because, as the many panelists have said, is because AI is not even 1-year-old human being. So it's really at a low level. But on the other hand, we think of AlphaGo that wins Isidore. So we think that AI is going to become like the Terminator, as going to dominate and control everything. But then when they try to use AI in real life, they realize that it's not as high level as they had thought to be, and so they give up. Also, artificial intelligence has to evolve, has to continuously be developed, and sometimes we need a patience for it to develop sufficiently. But many industries, they take one look at AI and feel that it's not enough, and they just give it up altogether without patience. And so I think when it comes to expectations, I think we have to be a little bit realistic amongst the industry experts and practitioners, which was mentioned several times during the forum, and I thought that was good. And so, yes, we need to be more involved, or industry practitioners need to be more involved in the process of evolving AI technology further. So this is the direction of AI advancement. So first of all, as was emphasized several times today, the question is whether it's going to be able to advance to become human level. Among the AIs, there are some that is based on deep learning, or perhaps overcoming deep learning using new technology and moving or heading towards becoming a human level AI. But I think we can divide that into two. So you can enhance the intelligence and to go beyond the human capabilities, which is the y-axis. In everyday life, we have all sorts of products. You have an AI speaker. But then there's also the fact that AIs usually have a conversation. There's a communication element or a dialogue element between the humans and AI, which is the issue of conversation. Of course, there are many concerns about social equality and the loss of jobs, and many people still question whether AI is viable to be used in everyday life. But if we adopt the principle of trustworthiness in AI right away, then I think it will impact the development progress of AI. And so I think the private sector won't be willing to take it up. And so the issue of trustworthiness needs to be dealt more by the public sector. But the AI level is still quite low, and I don't think we're at a level where we have to worry about it. But we do have to think it positively that many researchers are thinking about these issues. Now going on to the next AI technologies. So first of all, we want to sophisticate the existing deeper learning. Or then we we want to take deep learning further to become deeper learning or post-deep learning. So, first of all, we need to find out what the problems are in the existing deep learning, so overcoming the existing limitations. So to do that, there are three different ways. One is to make the learning and the inference process more efficient. The first is the amount of data. So when it comes to qualitative data, well, yeah, you know that there is a proportionality between the quantity of data and the quality of data. In Korea, we have lots of data, but compared to China and US, we're nothing. And so when it comes to deep learning, Korea finds it really difficult to become a forerunner because of the sheer lack of data. So then we came up with the idea, let's rack our brains a little bit more. So if we have learning data, albeit small amounts, perhaps we'll be able to compete with algorithms that have lots of data by enhancing the learning capabilities. And also another way would be to use the learned data, but then enhance the learning capabilities even further. So expand the scope of learning more. And the third way would be was continuous learning. And so we need continuously evolving AI. And the homework would be to solve the issue of memory, because some things might, after a long period of time, may be lost. And once again, the AI has to be able to merge the past data with the present data and also evolve at a real-time basis.
두 번째 꼭지로는 아까 말씀드렸듯이 쓸만한
So
인공지능
the
기술이냐,
big number two is relates to the big trustworthiness. The issue of the trustworthiness
아까 말씀하셨던 설명 가능한 AI 기술 쪽하고 그다음에 공정한
relate to XAI and fair AI
그리고 사용성과 관련되는 거는 결국
are all
인공지능이
related to this issue
서로 소통을 한다는
of
관점으로 봐서
trustworthiness.
인공지능이 소통하는 대상에 따라서 두 가지로
So
구분을 했습니다.
we can divide it into two depending on who the AI is having a conversation with. If AI is talking to a human, then the human's expressions and emotions have to be understood by AI.
또 하나는 사람이 잘 이해할 수
And
있게끔
also the humans have to be able to understand properly what the AI expresses. So the AI has to be able to express itself in ways that humans can understand it properly.
AI가 또 사람이 아닌 AI끼리도
And then
소통을 할 수 있겠죠. 그래서
there might be
AI와
communication
AI
or dialogue between
소통이라는
two
이런 세 가지
AI
구분을 했습니다.
systems.
저희가 그래서 이러한 한계 극복의 포인트를 통해서
And
세 가지
so,
형태로 넥스트 AI를 정의를 했는데
So this is a three-way of thinking about the next AI technology.
추론까지 포함하는
So learning and inference. So enhancing the learning abilities and inference abilities. And number two is securing trustworthiness. Getting the people to be able to have enough trust to be able to use AI. And the third is the usability. In other words, how much can we communicate with AI?
국가에서는 이제 민간 연구소나 학교나 또는 기업체들을 위한 과제 형태를 만들다 보니까 이걸
So usually the government promotes different projects that would be implemented by universities and the private sector.
성능을 향상시킨다 하는 부분은
And so when it comes to performance enhancement, it's really to do with algorithms, and there can be many different methodologies. So there can be multiple approaches to attaining a certain goal, multiple approaches of inferring
그런 방법으로 과제를 진행하려고 생각하고 있습니다.
in an algorithm. And so we also want to adopt that when we are selecting projects. So the first thing would be to allow for projects that can teach or allow AIs to learn even with a small amount of data.
하나는 자기 주도 학습입니다.
So these are some of the project topics that we have come up with, learning with small data. One is self-directed learning.
취득해서 훈련을 시켜서 거기에 문제를 푸는 이런 형태의 것을 스스로가 할 수 있게끔 만들어 달라 하는 부분이고 두 번째는
And the second would be meta-learning.
경우로 몇 가지 사례의 추론하는
So
사례를 보면서
it infers from several different examples and use that kind of inference to solve new problems. And the third is reinforced learning.
강화학습에 해당되는 건데 실질적으로 강화학습이 그 자체가
Reinforced learning itself cannot be seen as a next-gen technology, but as many speakers had said before me,
거의 모든 알고리즘, 특히나 에이전트
almost more algorithms, especially with the agents, have to be optimized, otherwise they're not usable. So, in order to deploy AI in the real world, we need that kind of reinforcement learning right then and there. And so once again, these subtopics are all under the big topic of learning with small data. So for example, if you don't have enough data, for example, with the accident rate for autonomous vehicles, we still have to come up with models that is able to make use of that small amount of data. And then another big topic is expanding the scope. So we have knowledge-based reasoning. Actually, artificial intelligence technology has to be able to logically infer by discovering and accumulating new knowledge embedded in data like humans. And then there is also the common sense-based reasoning. Many of the knowledge for humans are like common sense. So AI don't have common sense. And so when it comes to common sense reasoning, the AI has to be able to be inputted with a default set of data for common sense reasoning. And then another thing is a learning for open world novelty. There might be gaps between the real world and what's done in the lab. And so the AI has to be able to adapt and revise itself according to the new situations that arise in the real environment. Then there is a big issue of allowing continuous growth. So there's the competency-aware machine learning. So this involves the developing of reliable technologies by self-diagnosis and self-improvement of the competency of trained intelligence. And there's also the lifelong learning. So then there's the issue of the securing trustworthy, and under this big topic, the smaller topics for the projects would be explainable AI and the fairness of AI. So the main goal is to develop a customized plug-and-play technology that is able to provide explainability. And when it comes to fairness of AI, there is actually a project ongoing right now, but there are many changes that take place, and so when it comes to the fairness of AI, the project would involve artificial intelligence that flexibly reflects and complies with the different policy changes that are taking place constantly. And then the next part is about the usability. Well, I've already talked about the multimodal interaction. So we need both-way communication where each is able to understand the other party. There is also the interagent collaboration. So AI has to be able to express itself, and it's basically involving the development of auto-thinking technology that enables autonomous growth while reinforcing complex intelligence in a multi-agent situation. And so it's really about interacting with the other party, and many different agents have to be able to collaborate in solving new problems. So actually, I had a lot to share, and so I spoke really fast, but this is basically it for my presentation. Thank you. Thank you very much.
Thank you. That was a presentation from Program Manager Hyun-Gyu Lee. Thank you very much for helping us understand the situation better for Korean AI technology to develop further language intelligence, explainable artificial intelligence, and brain-inspired artificial intelligence. There has to be enterprising efforts to develop and discover research topics across all of those areas. I would like to thank Dr. Hyun-Gyu Lee again for his presentation. So that was the last of the programs that were prepared for the Global AI Forum today. I believe that we had a very rich program today, and I hope it has been helpful and useful for all the participants. Though we regret that we weren't able to welcome the participants in person in the conference hall, we were able to see many people enjoying and asking questions and making comments online. So I would say that this has been quite a successful forum. Thank you so much for your support. And we would like to also extend our thanks to all those who have worked hard to make this event possible. This Global AI Forum, AI of a New Era, was an opportunity to share the ideas of the leading minds on AI from around the world and also discuss the challenges and solutions regarding AI. Thank you so much for staying with us till the end, and I encourage you once again to join in the lucky draw so you can win those gifts. Next time, I hope to welcome you in person. Now, that is the end of the Global AI Forum. Thank you so much.